Hello everyone. Welcome to this full course video on Python for data science. In this video, we will cover everything you need to know to become a data scientist. Our experienced instructors with good industry experience will take you through this course. First, you will understand the basics of data science in 5 minutes from an animated video. You will then learn the important libraries in Python for data science such as NumPy, Pandas, and Matplotlib. You will get an idea about the data science concepts along with mathematics, statistics, and linear algebra. We will then focus on some of the essential data science algorithms such as linear regression, logistic regressions, decision trees and random forest, k-nearest neighbors, and k-means clustering. You will also learn about feature selection, cost functions, and principal component analysis. Finally, you will learn how to become a data scientist in 2021. So let's begin.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In her meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She's a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a genetic like for the chip, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, learning in data and scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data needs you.
Do you know how Netflix decides which movies suit your taste better? Or how Google Maps can provide routes with low traffic at given moment in seconds? This is all possible thanks to data science. The popularity of data science exploded in the 2010s, causing an approximate 15% year-on-year growth in the job market, and is expected to grow even higher in the coming decade. Now, what exactly is data science? Data study with data and derived various industries generate vast amounts of data, so its application range all the way from education, healthcare and entertainment to finance and marketing. When it comes to the subfields of data science, it comprises many technologies like artificial intelligence, deep learning, natural language processing, and deep learning. Each of them fulfilling different purposes and having varied functionalities. The role of Morpheus specific, it is problem-solving models involving massive amounts of data daily. This is why data science professionals are in high demand, with average salaries going as high as $1,864 per annum. With 2.5 million terabytes of data being transferred over the internet on a daily basis, the data science industry is slated to grow even higher, promoting further innovation for you. We learn which is
Today. So obviously already leveraging the power of Python every day. Hi, I'm Apeksha from Simplilearn, and well, after some thought and a bit more research, I was finally able to narrow down my choice of top Python libraries for data science. What are they? Let's find out. So let's talk about this amazing library, TensorFlow, which is also one of my favorites. So TensorFlow is a library for high performance numerical computations with around 35,000 GitHub commits and a vibrant community of around 1,500 contributors, and it's used across various scientific domains. It's basically a framework where we can run involves tensors, and tensors we can say are partially defined computational objects again, where they will eventually produce a value. That was about TensorFlow. Let's talk about the features of TensorFlow. So TensorFlow is majorly used in deep learning models and neural networks, where we have other libraries like Torch and Theano also. But TensorFlow has hands down better computational graphical visualizations. Also, TensorFlow reduces the error largely by 50 to 60% in neural machine translations. It's highly parallel in a way where it can train multiple neural networks and multiple GPUs for highly efficient and scalable models. This parallel computing feature of TensorFlow is also called pipelining. Also, TensorFlow has the advantage of seamless performance. As it's backed by Google, it has quicker updates, frequent new releases with the latest of features. Now, let's look at some applications. TensorFlow is extensively used in speech and image recognition, text-based applications, time series analysis and forecasting, and various other applications involving video detection. So, favorite thing about TensorFlow that it's already popular among the machine learning community, and most are open to trying it, and some of us are already using it. Now, let's look at an example of a TensorFlow model. In this example, we will not dive deep into the explanation of the model as it is beyond the scope of this video. So here we're using Amnes dataset, which consists of images of handwritten digits. Handwritten digits can be easily recognized by building a simple TensorFlow model. Let's see how. When we visualize our data using Matplotlib library, the inputs will look something like this. Then we create our TensorFlow model.
To create a basic TensorFlow model, we need to initialize the variables and start a session. Then after training the model, we can validate the data and then predict the accuracy. This model has predicted 92% accuracy. Let's see. Which is pretty well for this model. So that's the learning tutorial from Simplilearn. The interesting move on to full Python is computation in Python. It stands for numerical Python as the name suggests. It has around 18,000 commits on GitHub with an active community of 700 contributors. It's a general purpose array processing package in a way that it provides high performance multi-dimensional objects called arrays and tools for working with them. Also, NumPy addresses the slowness problem partly by these multi-dimensional arrays that we talked about, and functions and operators that operate efficiently on these arrays. Interesting, right? Now let's talk about NumPy. Large arrays nodes ND-array and attributes. ND-array provides for larger and repeated computations. NumPy offers vectorization. It's more faster and compact than traditional methods. I always wanted to get rid of loops, and vectorization of NumPy clearly helps me with that. Now let's talk about the applications of NumPy. NumPy along with pandas is extensively used in data analysis, which forms the basis of data science. It helps in creating the powerful n-dimensional array. Whenever we talk about NumPy, the mention of the array, we cannot do it without the mention of the powerful n-dimensional. Also, NumPy use learning model where it's like scikit-learn, etc. When you start creating the machine learning models in data science, you will realize that all the models will have their base as NumPy or pandas. Also, when NumPy is used with SciPy and Matplotlib, it can be used as a replacement of MATLAB. Now let's look at a simple example of an array in NumPy. As you can see, there are multiple array manipulation routines. Like there are basic examples where you can copy the values from one array to another. We can give a new shape to an array from maybe 1 to 2 dimensions. We can do 1 dimension where basic array, and for detailed explanation you can watch our other videos which targets on these explanations of each libraries. So first of all, whenever we are using any library in Python, we have to import it. So now this np is the alias which we will be using. Let's create a simple array. Let's look what is the type of this array. So this is an ND array type of array. Also, let's look what's the shape of this array. Here we can expand the shape of the array. So this is where you can change the shape of the array using all those functions. Now let's create an array using arrange functions. If I give arrange 12, it will give me a 1D array of 12 numbers like this. Now we can reshape this array to 3, 4, or we can write it here itself. So this is how arrange function and the reshape function works for NumPy. Now let's discuss the next library, which is SciPy. So this is another free and open source library extensively used in data science and it has around 19,000 commits on GitHub with an active community of 600 contributors. It is extensively used for scientific and technical computations. Also, as it extends NumPy, it provides many user-friendly and efficient routines for scientific calculations. Now, let's discuss about some features of SciPy. So SciPy has this collection of algorithms and functions which is built on the NumPy extension of Python. Secondly, it has various high-level commands for data manipulation and visualization. Also, the end-to-end function of SciPy is very useful in multi-dimensional image processing, and it includes built-in functions for solving differentiations, linear equations. So SciPy is used in multi-dimensional image operations. It has functions to read images from disk into NumPy arrays, to write arrays to disk as images, resize images, etc., solving differential equations, Fourier transforms, then optimization algorithms, linear algebra, etc. Let's look at a simple example to learn what kind of functions are there in SciPy. Here I'm importing the constants package of SciPy library. So in this package, it has all the constants. So here I'm just mentioning C or H or A, and everybody knows what it has. Speed of flattened. Scan the calculations. Data analysis is an integral part of data science. Data scientists spend most of the day in data munging and then cleaning the data also. Hence, mention of pandas is a must in data science lifecycle. Yes, pandas is the most popular and widely used Python library for data science, along with NumPy and Matplotlib. The name itself stands for Python data analysis, with around 17,000 commits on GitHub and an active community of 1,200 contributors. It is heavily used for data analysis and cleaning, as it provides fast, flexible data structures like data frames, series, which are designed to work with structured data very easily and intuitively. Now let's talk about the features of pandas. So the stacks various NA, which gives you the freedom to deal with missing data. Also, pandas provides a powerful apply function, which lets you create your own function and run it across a series of data. Now forget about writing those for loops while using pandas. Also, this library's high-level abstraction over low-level NumPy, which is written in pure C. Then it also contains these high-level data structures and manipulation tools, which makes it very easy to work with pandas, like their data structures and Cs. Applications. Pandas is extensively used in general data wrangling and data cleaning. Then pandas also finds its usage in ETL jobs for data transformation and data storage, as it has excellent support for loading CSV files into its data frame format. Then pandas is used in a variety of academic and commercial domains, including statistics, finance, neuroscience, economics, web analytics, etc. Then pandas is also very useful in time series specific functionality like date range generation, moving window linear regression, date shifting, etc. Now let's look at a very simple example of how to create a data frame. So data frame is a very useful data structure in pandas, and it has very powerful functionalities. So here I'm only enlisting important libraries in data science. You can explore more of our videos to learn about these libraries in detail. So let's just go ahead and create a data frame. I'm using Jupyter Notebook again, and in this, before using pandas, here I'm importing the pandas library. Let me go and run this. So in data frame, we can import a file, a CSV file, Excel files. There are many functions doing these things, and we can also create our own data and put it into data frame. So here I am taking random data and putting in a data frame. Also I'm creating an index and then also giving the column names. So PD is the alias we've given for pandas, random data of 6 by 4, index, which is taking a range of 6 numbers, and column name I'm giving as ABCD. Now let's go ahead and look at it. So here it has created a data frame with my column names ABCD, my list as 6 numbers 0 to 5, and a random data of 6 by 4. So data frame is just another table with rows and columns where you can do various functions over it. Also, I can go ahead and describe this data frame to see. So it's giving me all these functionalities where count and mean and standard deviation, etc. Okay, so that was about pandas. Now let's talk about the next library and the last one. So Matplotlib for me is the most fun library out of all of them. Why? Because it has such powerful yet beautiful visualizations. We'll see in the coming slides. Plot and Matplotlib suggests that it's a plotting library for Python. It has around 26,000 commits on GitHub and a very vibrant community of 700 contributors. And because of such graphs and plots that it produces, it's majorly used for data visualization. And also because it provides an object-oriented API which can be used to embed those plots into our applications. Let's talk about the features of Matplotlib. The PyPlot module of Matplotlib provides MATLAB-like interface. So Matplotlib is designed to be as usable as MATLAB with an advantage of being free and open source. Also, it supports dozens of backends and output types, which means you can use it regardless of which operating system you're using or which output format you wish. Pandas itself can be used as wrappers around Matplotlib's API, so as to drive Matplotlib via cleaner and more modern APIs. Also, when you start using this library, you will realize that it has a very little memory consumption and a very good runtime behavior. Now let's talk about the applications of Matplotlib. It's important to discover the unknown relationship between the variables in your dataset. So this library helps to visualize the correlation analysis of variables. Also in machine learning, we can visualize 95% confidence interval of the model just to communicate how well our model fits the data. Then Matplotlib finds its application in outlier detection using scatterplot, etc. and to visualize the distribution of data to gain instant insights. Now let's make a very simple plot to get a basic idea. I've already imported the libraries here. So this function matplotlib inline will help you show the plots in the Jupyter notebook. This is also called a magic function. I won't be able to display my plots in the Jupyter notebook if I don't use this function. I'm using this function in NumPy to fix random state for reproducibility. Now I'll take my n as 30 and will assign random values to my variables. So this function is generating 30 random numbers. Here I'm trying to create a scatter plot. So I want to decide the area. Let's put this. So it's just multiplying 30 with random numbers to the power 2 so that we get the area of the plot, which we will see in just a minute. So using the scatter function and the alias of matplotlib as plt, I've created this. If I don't use this, then I have very small circles as my scatter plot. It's colorful, it's nice. So that's one very easy plot. I suggest that you explore more of matplotlib and I'm sure you will enjoy it. Let's create a histogram. So I'm using the style as ggplot and assigning some values to these variables, any random values. Now we are assigning bars and colors and alignment to the plot. And here we get the graph. So we can create different type of visualizations and plots and then work upon them using matplotlib, and it's just that simple. So that was about the leading Python libraries in the field of data science. But along with these libraries, data scientists are also leveraging the power of some other useful libraries. For example, like TensorFlow, Keras is another popular library which is extensively used for deep learning and neural network modules. Keras wraps both TensorFlow and Theano backends, so it is a good option if you don't want to dive into details of TensorFlow. Then Scikit-learn is a machine learning library. It provides almost all the machine learning algorithms that you need, and it is designed to interpolate with NumPy and SciPy. Then we have Seaborn, which is another library for data visualization. We can say that Seaborn is an enhancement of Matplotlib as it introduces additional plot types.
So let's start with what is NumPy. NumPy is the core library for scientific and numerical computing in Python. It provides high-performance, multi-dimensional array object and tools for working with arrays. And I'll go a step further and say there are so many other modules in Python built on NumPy. So the fundamentals of NumPy are so important to latch onto for the Python so that you can understand the other modules and what they're doing. NumPy's main object is a multi-dimensional array. It is a table of elements, usually numbers, all of the same type, indexed by a tuple of position integers. In NumPy, dimensions are called axes. Take a one-dimensional array, or we have, and remember dimensions are also called axes. You can say this is the first axis, 0, 1, 2, 3, 4, 5. And you can see down here it has a shape of 6. Why? Because there's 6 different elements in it in the one-dimension array. And they usually denote that as 6 comma with an empty node on there. And then we have a two-dimensional array where you can see 0, 1, 2, 3, 4, 5, 6, 7. And in here we have 2 axes or 2 dimensions, and the shape is 2, 4. So if you were looking at this as a matrix or in other mathematical functions, you can see there's all kinds of importance on shape. We're not going to cover shape today, but we will cover that in part 2. Did you know that NumPy's array class is called NDArray for NumPy Data Array? Now we're going to take a detour here because we're working in Python, and 2 of my favorite tools in Python is the Jupyter Notebook, and then I like to use that sitting on top of Anaconda. And if you flip over to jupyter.org, that's jupyter.org, you can go in here. You can install it off of here if you don't want to use the Anaconda notebook. But this is the Jupyter setup, the documentation on the Jupyter. Jupyter opens up in your web browser. That's what makes it so nice, is it's portable. The files are saved on your computer. They do run in IPython or IronPython, and you can create all kinds of different environments in there, which I'll show you in just a minute. I myself like to use Anaconda. That's www.anaconda.com. If you install Anaconda, it will install the Jupyter Notebook with the Anaconda separate. And you can install Jupyter Notebook and it'll run completely separate from Anaconda's Jupyter Notebook. And you can see here I've now opened up my Anaconda Navigator. What I like about the Navigator, and this is a fresh install on a new computer, which is always nice, I can launch my Jupyter Notebook from in here. I can bring other tools, but you can see here if you put the variable down here, it will show you what's in that variable. And that has to do with the Jupyter Notebook inline coding. So that's not basic Python, that's just Jupyter Notebook shorthand, which you'll see in a little bit. So back to our NumPy array versus Python list. Python list being the basic list in your Python. Why should we use NumPy array when we have Python list? Well, first, it's fast. The NumPy array has been optimized over years and years by multiple programmers, and it's usually very quick compared to the basic Python list setup. It's convenient, so it has a lot of functionality in there that's not in the basic Python list. And it also uses less memory, so it's optimized both for speed and memory use. And let's go ahead and jump into our Jupyter Notebook. Since we're coding, best way to learn coding is to code. Just like the best way to learn how to write is write, and the best way. And so you can see down here, the output is an array of 1, 2, 3. And we could also do print. Just a reminder that this is an inline command, so that wouldn't work if you're using a different editor. You can see that it's an array 1, 2, 3. But we'll go ahead and leave it as A. Kind of a nice feature so you can see what you're doing really quick in the Jupyter Notebook. And just like all your other standard arrays, I can go A of 0, which is going to be a value of 1. So we do A of 1 has a value of 2 in it. So whether you're using the NumPy array or the basic Python list, that's going to be the same. That should all look pretty familiar and be pretty straightforward. Remember, the first value is always 0 and when we set on there. So let's take a look why we're using NumPy, because we went over the slide a little bit, but let's just take a look and see what that actually looks like. And what we want to look at is the fact that it's fast, convenient, and uses less memory. So let's take a glance at that in code and see what that actually looks like when we're writing it in Python and what the differences are. And to do this, I'm going to go ahead and import a couple other modules. We're going to import the time module so we can time it. And we're going to import the system module so that we can take a look at how much memory it uses. And we'll go and just run those. So this is imported. So that's fine. And so that's going to create a list of 1,000, 0 to 999. Remember, it starts at 0 and it stops right at the 1,000 without actually going to the 1,000. And let's go ahead and print. And we want system.getSize of. And we'll pick any integer because we have, 0 to 1,000. We'll just throw one in there, 5. It doesn't matter because it's going to, whatever integer we put in there is going to generate the same value because we're looking at the size of how much memory it stores an integer in. And then we want to have the length of the b. That's how many integers are in there. And if we go ahead and execute this and run this at a line, we'll see, oops, I did that wrong, comma. If we multiply them together, we'll see it generates 28,000. So that's like 2,000, about right. So let's go ahead and create this in NumPy. And we'll go C equals NP. And this is A range. So that's the NumPy command to do the same thing that we were just doing in a list. And we'll also use the same value on there, the 1,000. And then once we've created the value of C for np.arange, let's go ahead and print. And we can do that by doing c.size times c.item size. And that's very similar to what we did before. We did get the size of, so the C size is the size of the array, and each item size, just reversed. So it's the size of an integer 5 items is going to be the integers. See what that generates. And wow, okay, we got 4,000 versus 28,000. That's a significant difference in memory, how much memory we're using with the array. And then let's go ahead and take a look at speed. Let's do size. We tried this with lower values, and it would happen so fast that the NP array kept coming up with 0 because it just rounded it off. So size, and let's create an L1 equals range of size, and we'll do an L2. We'll just set up to the same thing. It's also range of size on there. There we go. And then we can do on A1 equals NP dot A range size. And then let's do 2 equals NP dot A range. We'll keep it the same size. And what we're going to do is we're going to take these two different arrays and we're going to perform some basic functions on them. But let's go ahead, actually let's just load these up now. We'll go ahead and run this so those are all set in memory. Except for the typo here. Quickly fix that. There we go. So these are now all loaded in here. And let's do a start equals time.time. So it's just going to look at my clock time and see what time it is. And then we'll do result equals, and let's do, let's say we got an array, and we're going to say, let's do some addition here. X plus Y for X, Y. And we'll zip it up here. Two different arrays. So here's our two different arrays. We're going to multiply each of the individual things on here. L1, L2. There we go. So that should add up each value. So L1 plus L2, each value in each array. And then we want to go ahead and print. And let's say Python list took. And then we'll do time dot time. We'll just subtract the start out of there. So time, whoops, I messed up on some of the quotation marks on there. Okay, there we go. Time minus the start. And we'll convert that to seconds. So we'll go milliseconds or time. This kind of view while we're doing this of some ways to manipulate the script. And as you can see also my bad typing. There we go. Okay, so we'll go ahead and run this. And we can see here that the Python list took 34. Actually, I have to go back and look at the conversion on there. But you can see it takes roughly 0.34 of a second. And we can go ahead and print the result in here too. Let's do that. And we'll run that just so you can see what kind of data we're looking at. And we have the 0, 2, 4, 6, 8. So it's just adding them together. It's pretty straightforward on there. Scroll down to the bottom of the answer. Different time on there depending on what core, because this is on an 8-core computer, so it just depends on what core it's running on, what else is pulling on the computer at the time. And let's go back up here and do our start time. Paste that into here. And this time we're going to do a result equals, and this is really cool. Notice how elegant this is. It's so straightforward. This is a lot of reason people started using NumPy is because I can add the two arrays together by simply going A1 plus A2. It makes a lot of sense, both looking at it, and it's just very convenient. Remember that slide we're looking at? Fast, convenient, and less memory. So look how we need to print the result again. So let's just go ahead and print the time on here. And we'll borrow this from the top part, because I really am a lazy typer. And this isn't the Python list, this is the NumPy list, or NumPy array. And let's go ahead and see how that comes out. And we get 2.99. So let's take a look at these two numbers, 46 versus 2.99. So we'll just round this up to 3. That's a huge difference. That's like more than 10 times faster. That's like 15 times roughly at a quick glance. I have to do math to vary a little bit, depending on what's running in the background on the computer, obviously. So we've looked at this, and if we go back here, we found out it's much faster. Yes, there's going to be different speeds depending on what you're doing with the array. Very convenient, easy to read, and it uses less memory. So that's the core of the NumPy. That's why a lot of people base so many other modules on NumPy and why it's so widely used. So we did glance at a couple operations when we were looking at speed and size. Let's dive into a little bit more into the basic operations. And these are always nice to see. I mean, certainly you want to go get a cheat sheet if you're using it for the first time. Look things up. Google is your friend. We did this for the most basic numpy.array or np.array. And we'll go ahead and create an array. Let's do pairs, 1, 2. And then let's do 3, 4. And if we're going to do that, let's do 5, 6. I'll go ahead and take this and run this. I can go ahead and do our A down here so it's in line, and it'll print that out. You can see it makes a nice array for us. So we have A, and if you look at that, we have 3 different objects, each with 2 values in them. And hopefully you're starting to think, well, how many dimensions or indexes is that? And you'll see 3 by 2. So let's go ahead and take a look, and let's go, how about a.nDimensions? Speaking of which, we'll run that, and we have 2 dimensions for each object. And then we can do the item size, so a dot. We saw this earlier, where we looked up how many items. It was up here, where we wanted to multiply item size times the actual size of the object. So the memory is being used versus the item size. And we should see probably is a good when you're working with data science and you're moving it from one format to another. So we have our shape. We just talked about that. We have 3 by 2. 3 rows by 2 objects in each one. Generally, I don't look too much at the size, but the dimensions I'm always looking up. And this is nice, you can automate it. So you might be converting something, you might need to know how many dimensions are going into the next machine learning package so that you can automatically just have it send that information over. So we looked at a shape. Let's go ahead and create a slightly different array, np.pair. And one of the features we can do, which is really important, is we can do dtype equals. In this case, let's do np float 64. And so what we've done is we're converting all of these into a float, and we type in A. And now instead of having 1, 2, 3, 4, 5, 6, you see they're all float values. 1.0, there's no actual 0 in there, just there's a 1 dot, or the 1 period, 2, 3 period, 4 period, 5 period, 6 period. And this, again, data science, I don't know how many times they've had to convert something from an integer to a float so that's going to work correctly in the model I'm using. So very common features to be aware of and to be able to get around and use. And we'll also do, let's just curiosity, item size. We'll go ahead and run that. And we see that it doubled in size. So it's not a huge increase in computers. Not a huge increase compared to what it would be if you're running this in the Python list format. And then we did the shape earlier without having it set to the float 64. Let's go ahead and do a shape with it set to 64. And it should be the same 3, 2. So it all matches. So we've gone through, and remember, if this is all brand new to you, according to the Cambridge study at the Cambridge University, if you're learning a brand new word in a foreign language, the average person has to repeat it 163 times before it's memorized. So a lot of this, you build off of it, so hopefully you don't have to repeat it 163 times. But we did manage to repeat it at least twice here, if not a little bit more. And let's go ahead and take this. We're going to go look at one more setup on here. And let me just take this last statement here on the converting our properties of our data. And instead of float 64, let's do complex. Let's just see what that looks like. And let's go ahead and print that out and run it. And so we now have a complex data set up, and you'll see it's denoted by the 1 dot plus 0 dot j. And if we flip over here and do a basic search for NumPy data types, better to go to the original web page, but pull up a bunch of these. You can see there's a whole list of different NumPy data types. Shorthand, complex, we have complex, complex 64, complex 128. Complex number represented by 2 64-bit floats, real and imaginary components. One option on there, float 16, float 32. float, shorthand for float 64, most commonly used, and of course all the different ones that you can possibly put into your NumPy array. So we covered a basic addition up there when we were comparing how fast it runs, but some very basic components, how to set up a NumPy. Dimensions it has, item size, data type, item, again we went to item size, and there's also the shape, probably one of the more used. I use the A shape all the time, very commonly used. And then down here you can see where we actually created a NumPy complex data type. So let's look at some other features in NumPy. One of them is you could do NumPy dot zeros, and we're going to do 3, 4. There we go. And we'll go ahead and run this, and you can see if I do np.zeros, I create a NumPy array of zeros. This is really important. I was building my own neural network, and I needed to create an array where I initialized the weights, and I wanted them all to be the same weight. In this case, I wanted them to start off as 0 for the particular project I was working on. And there's other options, like you can do NumPy1s, and we'll do the same thing, 3, 4. We'll run that. And you can see I've created an array of NumPy1s. In this case, it comes out as a float array. And then this is an interesting to note, because we have, let's go back to our Python and do L range 5. And we'll print the L. So there's our list. And if I run that, it doesn't create the range until after the fact, until you actually execute it. That's an upgrade in Python. Python 2.7 actually created the array, 0, 1, 2, 3, 4. This one actually creates the script, and then once it's used, it then actually generates the array. And if we do that in NumPy A range, remember that from before, and if we do NumPy A range 5, and let's do L equals, or we can just leave it as NumPy, that's fine. There we go, just run that. You can see there we actually get an array, 0, 1, 2, 3, 4 for the value of the NumPy A range 5. It generates the actual array. And for part 1, we're going to do just one more section on basic setup, and we're going to concatenation, do a concatenation example. There we go. We're going to do strings. Let's take a look at strings and what's going on with there. And let's do, let's see, print. Let's do an np character, something new here. And we're going to add, and then here's our brackets for what we're going to add. And let's say, let's do hello, comma, hi. And in the brackets on there, let's create another one. And this one's going to be ABC, and we'll do XYZ. So we're just creating some, randomly making some up on here. And then we'll go ahead and just print this. If we run that, you can come down here, and of course make sure all your brackets are open and closed correctly. And then you can see in here when we concatenate the example in NumPy, it takes the two different arrays that we set up in there, and it combines the hello with the ABC and the hi with XYZ. And if we can also do something like print, let's do np character dot multiply. So there's a lot of different functions in here. Again, you can look these up. It's probably good to look them all up and see what they are, but it's good to also just see them in action. And let's do hello space, comma, 3. And we'll run this one and run that without the error. And you'll see it does hello, hello, hello. So we multiplied it by 3. And we can also, and let's just take this whole thing here instead of retyping it. And we can do character center. So instead of multiply, let's do center. And over here, keep our hello going. Take the space out of there. And let's do center at 20. And fill character equals, we'll fill it with dashes. So if we run this, you can see it prints out the hello with dashes on each side. And we keep going with that. We can also, in addition to doing the fill function, we can play with capitalize, we can title, we can do lowercase, we can do uppercase, we can split, split line, strip, join. these are all the most common ones. And let's go ahead and just look at those and see what those look like, each one of them. Here we're going to do the hello world, all-time favorite of mine. I always like to say hello universe. And you can see here we did a capital H with the world, but so we want to capitalize. So capitalize is the first one in the array. So we get hello world on there. And we can also take this, and instead of capitalizing, another feature in here is title. And let's just change this to how are we doing? How are you doing? Instead of we, we'll do you. And let's run that. And you can see here, because we created it as a title, it capitalizes the first letter in each word. And in this one, we're going to do character lower. Two different examples here. We have an array. We have hello world all capitalized, and we have just hello. And you can see that one is an array and one is just a string. If we run that, you get an array with hello world lowercase and hello lowercase. And if we're going to do it that way, we can also do it the opposite way. There's also upper. And let's paste those in there. And you can see here we have character.upper, opposite there, python.data, and we'll do Python is E. Hopefully you're starting to get most of the Python, and the scripting is very simple. It's when you put the bigger picture together and starts building these puzzles, and somebody asks you, hey, I need the first letter capitalized, unless it's the title, and then you start realizing that this can get really complicated. So NumPy just makes it simple, and we like that. And so in this case, we did Python data. It's all uppercase. Python is easy, like shouting in your messenger. Python is easy. And then if you're ever processing text and tokenizing it, a lot of times the first thing you do is we just split the text, and we're just going to run this np.character.split. Are you coming to the party? If we do that, it returns an array of each of the individual words. Are you coming to the party, splitting it by the spaces? And then if you're going to split it by spaces, we also need to know how to split it by lines. And just like we have the basic split command, we also have split lines. Hello, and you'll see here the scoop in for a new line. And when we run that, if you're following the split part with the words, you should see hello, how are you doing? The two different lines are now split apart. And let's just review 3 more before we wrap this up. Commonly used string variable manipulations. We have strip, and in this case we have Nina, admin, Anita, and we're going to strip A off of there. And let's see what that looks like. And then you end up with nin, demin, nate. It basically takes up all leading and trailing letters. In this case we're looking for A. More common would be a space in there, but it might also be punctuation or anything like that that you need to remove from your letters and words. And if you clean data or join it together. So you see here we have a character join. We'll go ahead and run this. And it has on the first one, it splits each of the letters up by the colon and the second one by the dash. And you can see how this is really useful if you're processing, in this case, a date. We have day, month, year, month, date. Very common things to have to always switch around and manipulate depending on what they're going into and what you're working with. And finally, let's look at one last character string. We're going to do replace. If you're doing misinformation, this is good. Pulling news articles. We're just is with was. And you can see here, he was a good dancer. Hopefully that's not because he had a bad fall. He just was from 1920s and has gotten old. So there we go. We've covered a lot of the basics in NumPy as far as creating an array. Very important stuff here when you're feeding it in. How do we know the shape of it, the size of it? What happens when we convert it from a regular integer into a float value as far as how much space it takes? We saw that doubled it. Item size, you have your in dimensions, and probably the most used is shape. And we'll cover more on shape in part 2. So make sure you join us on part 2 because there's a lot of important things on shape in there and setting them up. We also saw that you can create a zeros-based array. You can create one with ones. If we do a range, you can see how it is a lot easier to use to create its own range as it is in NumPy. And you saw how easy it was to add 2 arrays. We saw that earlier, just plus sign. Then we got into doing strings and working with strings and how to concatenate. So if you have 2 different arrays of strings, you can bring them together. We also saw how you can fill, so you can add a nice headline, dash, dash, dash. We saw about capitalize the first letter. We saw about turning it into a title, so all the first letters are capitalized. Doing lowercase on all the letters, upper for all the letters, just lower and upper, nice abbreviation. We also covered how to split the character set, how to strip it. So if you want to strip all the A's out from leading A's and ending A's or spaces, you can do that very easily. Also how to join the data sets. So here's a character join option for your strings. And finally we did the character replace. Pandas really is a core Python module you need for doing data science and data processing. There's so many other modules that come off of it. There actually sits kind of on NumPy, so if you've already had our NumPy array, hopefully you've already gone through the NumPy tutorial 1 and 2. So today we're going to cover what is pandas. We'll discuss series. We'll discuss basic operations on series. And then we'll get into a data frame itself, basic operations on the data frame, file-related operations on a data frame, visualization, and then some practice examples. Roll up our sleeves and get some coding underneath there. And let's start with just some real general, what is pandas? Pandas is a tool for data processing which helps in data analysis. It provides functions and methods to efficiently manipulate large data sets. Now, this is a step down from, say, using Spark or Hadoop in big data. So we're not talking about big data here, but we are talking about pandas, and there is some connections. There's like an interface going on with that, so there is availability, but you really should know your pandas, because if you're working in big data, you'll know there's data frames. Well, pandas is a data frame primarily. It has a couple different pieces we'll look at here. And if you've never worked with data frames before, a data frame is basically like an Excel spreadsheet. You have rows and columns. You can access your data either by the row or the column, and you have an index and that kind of setup. And we'll dig more into that as we get deeper into pandas. But think of it as like a giant Excel spreadsheet that's optimized to run on larger data on your computer. And then I said that it's a data frame. So the data structures in pandas are series, one-dimensional arrays, and then we have data frame, two-dimensional array. And it really centers around the data frame. The series just happens to be part of that data frame. And here's a closer look at a pandas series. Series is a one-dimensional array with labels. It can contain any data type, including integers, strings, floats, Python objects, and more. So it's very diverse. If you remember from NumPy we studied, they had to be all uniform. Not in pandas. In pandas we can do a lot more. And pandas actually kind of sits on NumPy, so you really need to know both of those if you haven't done the NumPy tutorials. And you can see here we have our index 1, 2, 3, 4, 5, and then our data A, B, C, D, and E. Very straightforward. It's just two columns, and we have a nice index label and a column label for the data. And then a data frame is a two-dimensional data structure with labels. We can use labels to locate data. And you can see here we had, if we go back one, we had our index 1, 2, 3, 4, 5. So in each one of these series, they would share the same index over there, the row index. So you have your row index df.index, and then you have a column index df.columns. And this would look, like I said, this would be really familiar if you've done any work with spreadsheets, Excel. So it kind of resembles that. This does make it a lot easier to manipulate data and add columns, delete columns, move them around. Same thing with the rows, so you have a lot of control over all of this. Now, we're of course going to do this in our Jupyter notebook. You can use any of your Python editors, but I highly suggest if you haven't installed Jupyter and haven't worked with it, it is probably one of the best ways for easily displaying a project you're working on. I skip between a lot of different user interfaces or IDEs for editing my Python, and it's just simply jupyter.org, jupyter.org. And then I always let mine sit on Anaconda, anaconda.com. And just real quick, we'll open that up for you. Oops, offline mode. Don't show me that again. But you can see here that I have different tools that I can actually install in my Anaconda, including the Jupyter Notebook, which comes by default. And then I have access to the environments. And again, that's anaconda.com, named after the very large, one of the world's largest snakes, and then Jupyter Notebook. In this case, jupyter.org. And when we're in I'm going to go in here to our Jupyter Notebook, and we're going to go ahead and just do new and a Python 3. And this will open up a Python 3 untitled folder. So diving right in, let's go ahead and give this a title, Pandas Tutorial. And we'll go up to Cell, and we'll change the cell type to Markdown so it doesn't execute it as actual code. One of those wonderful tools when you have Jupyter Notebook so you can do demos with this. And let's go ahead and import pandas. And usually people just call it PD. That has become such a standard in the industry. So we'll go ahead and run that. Now we have our pandas has been imported into our Jupyter notebook. And then, we can go ahead and let me do the Control Plus. Since it's Internet Explorer, I can enlarge it very easily so you have a nice pretty view. Whoops, too big. There we go. And whenever you're working with a new module, it's good to check your version of the module. In pandas, you just use the, in this case, pd.__version__. That's actually pretty common in most of our Python modules. There's different ways to look up the version, but that's one of the more common ones. And we'll go ahead and run that. We get 0.23.4. And if we go to the pandas site, we see 0.23.4 is the latest release. And of course, a reminder that if you're going to your environment, you need to install it. So you'll need to do pip install pandas if you're using the pip installer. We'll go and close out of that. And the first thing we want to do is we're going to work with series. A lot of the stuff you do in series you can then do on the whole data set. We need to do what? Create one. We need to manipulate it, take pieces of it, so query it, delete, so you can delete different parts of it. So we want to do all those things with the series. And we'll start with the series, and then almost all the code, in fact all the code does transfer right into the actual data table. So we go from a series of a single list of one column, and then we'll take that and we'll transfer that over to the whole table. And we'll start by creating, there we go, creating a series from list. And let's just call this ARR equals, and we'll do 0, 1, 2, 3, 4. If you remember from our last one, we could easily do R equals range of 5, which would be 0 to 4. But we'll do R equals 0 to 4, and we'll call this S1, and we'll go PD, and series is capitalized. This one always throws me, is which letters do you capitalize on these modules? They're getting more and more uniform, but you got to watch that with Python. And we're just going to go ahead and do ARR. So we're just going to take this Python list and we're going to turn it into a series. And then because we're in Jupyter, we don't have to put the print statement. We can just put S1 and it'll print out this series for us. And let's go ahead and run that and take a look. And you'll see we have 2 rows of numbers. So the first one is the index. Now it automatically creates the index starting with 0 unless you tell it to do differently. So we get 0, index row 0 is 0, 1, 1, 2, 2, 3, 3, 4, 4. And because it's a series, it doesn't need a title for the column. There's only one column, so why title it? And this also lets you know that it's a data type of integer 64. So we print this out. This is our series, our basic series we've just created. And let's do a second series. PD, and we'll use the same data list. And let's go ahead and do order. We'll give it an order equals, let's do it this way. Let's go index equals order. And it helps if we actually give it an order. So we'll do order equals, and let's do 1, 2, 3, 4, 5. So instead of starting with 0, we're going to give it an order starting with 1. We're going to run that. And we'll go ahead and print it out down here, S2. And we'll see that we now have an index of 1, 2, 3, 4, 5. And that represents 0, 1, 2, 3, 4 in the series. And we're still data type integer 64. And very common as you're messing with NumPy arrays is we can import our NumPy as NP. Remember that from our NumPy tutorials. We can go ahead and create a NumPy out of random with the random numbers of 5. And let's just see what that n looks like, so we can see what our NumPy looks like. So we have some nice random float values here, 2.33, so on. And that's from our last tutorial, the NumPy tutorial 1 and 2. And instead of calling it order, let's call it index. And we're going to set our index equal to A, B, C, D, and E. I want to show you that the index doesn't have to be an integer, so it can be something very different here. And then let's go ahead and create our, we'll just use S2 again. And here's our NP for NumPy. Series, capital S, and N is our NP for NumPy. PD for pandas. There we go. Switching my anachronisms. So we have PD.series of N, and we want to do our index equals our index we just created. And then let's go ahead and see what that looks like. S2 is to print it, and let's run that. And we can see here we have a nice series going on. A, B, C, D, and E for our indexes. So instead of it being 0, 1, 2, 3, or 4, we can make this index whatever we want. And you can see the numbers here going down that we randomly generated from the NumPy array. So we used NumPy to create our Panda series right here. And so continuing on with creating our series, this one I use so often, we create a series from a dictionary. So we have our dictionary. In this case, we went ahead and did A of 1, B is 2, C of 3, D 4, E of 5. So each one of those is a key and then a value. And then we're going to use, let's use S3 equals PD for pandas, series, and then we want to go ahead and just do D in here. Print out S3 here, and let's go ahead and run this. And you can see we got A is 1, B is 2, C is 3, D is 4, E is 5. And it's still of integers 64 because the actual data is 1, 2, 3, 4, 5, and it's all integers 64, type 64. And the last thing we want to do in the creating section of our series is to go ahead and modify the index, because we're going to start modifying all this data. So let's start with modifying the index of the series. And if you remember, let's do a print this time, S1. I'll go ahead and run this. And the reason I did print is because it only prints out the last variable. So if I put S1 up here and we're going to do another variable back down lower, it won't print the first one, just the last one. And we're going to go ahead and take S1, the index, and we're just going to set it equal to a new index. And obviously, the number of objects in our index has to equal the number of objects in our data. And then because it's the last variable, we can go ahead and just do an S1. And let's run that, and you can see how we went from 0 to 0, 0, 1, 2, 3, 4 as our index. We've now altered it to A, B, C, D, and E. So this would be much more readable or might be representational of a larger database you're working with. So cool tools. We've covered creating a database based on a basic array, Python array. We've showed you how to reset the index. Then we showed you how to use a NumPy array. So you can put a NumPy array in there. It's all the same, pd.series, NumPy array, and then we can set the index on there. And the same thing with the dictionary. So it's very versatile how it pulls in data. And you can pull in data from different sources and different setups and create a new series very easily in the pandas. And then we looked on changing your index. So now we have a new index on here. And then we want to go ahead and do some selection. Let's do some basic slicing, most common thing you'll probably do on here. And we'll just do S1. This notation should start to look really familiar. Again, this is going to put an output, so it doesn't change S1. This just selects it. So we might do A equals S1 and then print A. And you'll see that it just looks at the first three, 0, 1, 2. And we can do the same thing by not having the A in there. I'll go ahead and take that out, but it's just a reminder that it's not actually changing S1. It's just viewing S1. So simple slicing on here. And we can likewise do an append. Oops, before we do append, let's just do a quick kind of fun one. We'll do to -1. And you'll see it covers everything but the E. Of course, you can do -2 on this side. So another way to select it is to go how far from the end. And likewise, we can do a 2 here, CDE to the end. So it starts at the second one. And another way we can do this is we can do a -2 over here. And that looks at just the last 2 in the slice. So you can see how easy it is to slice the data. And of course, there's no reason to do this, but you could select all of them if you wanted to view all of them on there. Oops, 32. There's not 32, so it's just going to show the first 3. There we go. And then we can also append. So I can take and, let's create another series and append one to it. And if you remember, we had S3. There's our S3. And we have our S1. We'll go ahead and do S1. And let's go ahead and do, let's call it S4 equals S1 append S3. So we're just going to combine those two into S4. And if we go ahead and print S4 on here, you'll now see that we have A, B, C, D, E, A, B, C, D, E, 0, 1, 2, 3, 1, 2, 3, 4, 5, because we started the data at 1. So very easy to append one series to the next. And if we're going to append one series to the next, we need to go ahead and drop or delete one. And drop is the key word for that. And let's just do E, or index E. And so if I run this, you'll see that it'll print it out, and A, B, C, D, there's no E. And remember, all these changes, if I type in S4 again, you'll see that S4 still has E in it. So this change does not affect the series unless you tell it to. So I'd have to do like S4 equals S4.drop E. And there's another way to do that, which we'll show you later on. Let me just cut this one out. There we go. All right, so we've covered all kinds of cool tools here. We have appending, we have slicing, we did all the creating stuff earlier. So you can see here on the setup how easy it is to manipulate the series. So next what we want to get into is we want to get into operations that happen on the series. Let me go ahead and change this cell to Markdown. There we go, and run that. So series operations, what can we do with the series? And let's start by creating a couple arrays. We'll call it array 1, and we'll do 0 through 7, and array 2, 6 through 6, 7, 8, 9, 5. I don't know why we threw the 5 on the end. Let's go ahead and run those so those load up into Jupyter. And we'll do this a little backwards. We're going to do S5 equals a panda series of array 2. So I'm doing this in reverse. And then when we do S5, you'll see that we have 0 to 4. It automatically assigned the index. 6, 7, 8, 9, 5 for our series. And let's go ahead and do the same, and we'll call this S6, and we'll set this equal to PD series for our first array. And if we do an S6 down here to print it out, we'll see something similar. I got 0 through 6, 0, 1, 2, 3, 4, 5, 7 for the data. So those are two series we just created, series 6, 5, and 6. And one of the first things we can do is we can add one series to the next. So I can do S5.add S6. And let's see what that generates. And just a quick thing, if you've never used pandas, what do you think is going to happen with the fact that this only has 5 different values in it, and this one has 7 values? So let's see what that does. And we end up with 6, 8, 10, 12, 9, and it goes, oh, I can't add this. There's nothing there. So it gives us a null return. Very different than the NumPy that would have given you an error. This instead tells you there's no value here because we couldn't generate one. So we can easily add S5.add S6, and likewise we can do S5.sub for subtract S6, and we'll run that. And on the add, the subtract, and you guessed it, we're going to do multiply and divide next. Again, you can see there's null values where it can't subtract the two because there's no values there to subtract. We can also do S5 multiply, MUL. They're all 3 letters on these. That's one of the ways to remember how they figured out the code for this. So remember, these are all 3 letters, mul. We'll go ahead and run this. And you can see how they're multiplied together. And then we can also do the S5 div, 3 letters again, S6, and run that. And you'll see here, this goes to infinity because we have 0 in the wrong position. So it actually gives you a whole different answer here. That's important to notice. And then in the null values, because there's no data and it can't actually produce an answer off of missing data. And since we're in data science, let's do S6 median. So let's look up the median data, which is simply median. Sorry for those who are following the 3 letters because median is not 3 letters. And you can see in S6 is 3.0. And let's do a print here. And we'll do median or average. S6. And let's print max, comma S6. And just like median, there's max value. And if we're going to have a max value, we should also have a minimum value. So let's pop in minimum. We'll go ahead and run this. And you're starting to see something that would be generated like, say, in R, where you're starting to get your different statistics. We have a median value of 3, max value of 7, and a minimum value of 0. And what it does when it hits these null values, if there is null values in there, because we could still do that, we could actually, you know what, let's go up here and do, let's pick this one where we multiplied. Let's go S7 equals, I'll go ahead and print the S7 just so I keep it nice and uniform, so I still have my S7 down there and run it. And then I want to take the S7, because S7 now has null values and an infinity value, and let's see what happens. This is going to be interesting, because I want to see what it does with infinity. And we end up with a median of 6, maximum of 27, and minimum of 0, which is correct. It drops those values. So when it gets to there and it doesn't know what to do with them, it just drops those values and then it computes it on the remaining data on there. So that's important to know when you're making these computations, you're looking at min and max and median, you're not going to know that there's null values unless you double check your data for the null values. That's a very important thing to note on there. So just a real quick review on there. We've created our PD series, and we've gone ahead and done addition, subtraction, multiplication, division. All of those are 3 letters, so sub, min, div, add. And then we looked at median, maximum, and minimum. So we're going to go ahead and jump into the next big topic, which is to create a data frame. So now we're going to go from series, and we're going to create a number of series and bundle them together to make a data frame. There we go, cell type, markdown. And we go ahead and run that. So we have a nice title on there. It's always good to have a good title. All right, so our first data frame, we'll jump in with some stuff that looks a little complicated, but we'll break it down. First, I'm going to create some dates. And you know what? Let's just go ahead and do this. I want you to see what that looks like, what I'm creating here. I've created a series of dates, PD date range, and we're going to use these for the index. Okay, so when you look at this, you'll see that it's just, basically it comes out kind of like a basic Python list or a NumPy array, however you want to look at it, with our different dates going down. And we've generated 6 of them. And it's going to have whatever time it is right now on the thing for the date, for the time. That's that time stamp right there. And then you'll see we have 11/19, 2008, 11/20, 11/19, and looking into the future there. So that's all this is generating a series of dates that we're going to use as our index. And this is a pandas command, so we have a date range, which is nice. That's one of the tools hidden in there in the pandas that you can use. And next we're going to use NumPy to go ahead and generate some random numbers. In this case we'll do the np.random.random in 6,4. You can look at this as rows and columns as we move it into the pandas. And of course you could reshape this if you had those backwards on your data. But we want the 6 to match the rows, and we have 6 periods, so our indexes should match along with the rows on there. And then, you know what, before we do the next one, let's go ahead and just print out our NumPy array so you can see what that looks like. Here we have it, 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6. 4 by 6. So it's a nice little setup on there. And since working with data frames can be very visual, let's give our columns, we have 4 columns, and we're going to give them names, A, B, C, and D. So now we have columns on there also. And then let's put this all together in a data frame, and we can actually, you know what, let's do this. Since I did it with everything else, let's go ahead and do columns. And you can see there's our columns on there. And we'll go ahead and do df1 equals pandas dot data frame. And note that the D and the F are capitalized. Series, it was just the S, and I always highlight this because you don't know how many times these things get retyped when you forget what's capitalized on there. It's a minor thing. You'll pick it up right away if you do a lot of it. And the first thing we want to do is we want to go ahead and take our NumPy array, because that's what we're going to create our data frame off of, is the NumPy array. And then we want our index equal to our dates. So there's our index in there. And then we also have columns equals columns. And then finally, let's see what that looks like. Now remember, we had all that different data that just looked like a jumble of data. We have our column names and everything else. Our NumPy array, kind of just a jumble array over there, 4 by 6. You could sort of read it. But look how nice this looks. I mean, this is, you come into a board meeting, you're working with your shareholders. This is pretty readable. This is, you know, this is our date. This is our A, B, C, D, whatever it is. Maybe each one of these dates has your leads, closures, lost leads, total dollar made, you know, whatever it is, if it's in a business. Maybe it's measurements on some scientific equipment, weather searching material, you know, where this is like high of the temperature, low of the day, humidity of the day, whatever it is. So you can see that we can really create a nice clear chart, and it looks just like a spreadsheet. You know, we have our rows, and we have our columns, and we have our data in there. Now this one I use all the time. If we're going to create, we can create it like you saw here with our NumPy array. Very easy to do that and reshape it. You can also create it with a dictionary array. So here we have some data, and let me just go down a notch so you can see all the data on there. We have an animal, in this case cat, cat, snake, dog, dog, cat, snake, cat, dog. We have the age, so we have an array of ages. We have the number of visits and the priority. Was it a high priority? Yes, no. And then we're going to take that, we're going to create some labels. We have A, B, C, D, E, F, G, H, I. And what I want you to notice on this is we have a title, animal, and then we have basically a Python list. And these lists, they don't necessarily have to be equal because we can have non-data, you know, np.nan, NumPy array, null value. But we want to go ahead and create labels that are equal to the number in the list. So A the first cat, B the second cat, C the snake, D the dog, and so on. So we'll go ahead and create our labels, which we're going to use as an index. And we'll call this df, let's do it this way. We'll call this df2 equals PD for pandas, data frame, and then we have our data, just like we did before, and then we have our index equals labels. And if we're going to go from there, let's go ahead and print it out so we can see what that looks like, df2. So let's go ahead and run that. Again, you have a nice, very clean chart to look at. We've gone from this mess of data here to what looks like a very organized spreadsheet, very visual and easy to read. Animal, age, visits, priority, and then A through J, cats and all your different animals, so on and so on. And then when you do programming, a lot of times it's important to know what the data types are. So we can simply do df2 dtypes. And if we run that, we can see that our animal is an object, because it's just a string, but it comes in as an object. Age is a float 64, integer 64, and then priority again is just an object. And exploring this one's very popular. Let's go df2 head, and if we print that out, the df2 head returns the first 5. And we can change this. You don't have to do 5. You might want to just look at the top 2. Maybe you want to look at, let's see, let's do 6. So maybe we want to look at just the top 6 in the database, in your data frame. And you can actually, this creates another data frame. So I could have a df3 equal to df2, and this now takes the df2 and just the first 6 values. So if we do df3, run, get the same answer. And if we do the head of the data, we can also do the tail. It's the same thing. df_tail, you can look at the last, we'll just do the tail, which by default does 5, the last 5. And of course you can just look at the last 3 of those real quick just to see what's at the end of the data. And this is, the tail, I love doing the tail of 1 because I'll have like the index or something like that, and it will just show me the last, whatever the last entry was. You know, looking at stock values, and I might want to look at just the last 5 days of the stock values. I can do that with the data frame tail. And some other key things to look up are the index. So we can do df2.index. And I want you to notice that this isn't a call function. So if I put the brackets on the end, it'll give me an error because index is not callable. It's just an object in there. So we do df2.index. There's also columns. So we can go ahead and let's print this. Remember, the first one's not going to show unless I print it, and then df2 columns. So now we can see that we have our indexes and we have our columns listed here, df2.columns, animal, age, visits, priority. It tells you what kind of object it is, or what kind of data type it is, and they're both object. And then finally df2.values. And again, there's no brackets on the end of df2.values because this is an actual object, it's not a callable function. So we'll go ahead and run that, and it just displays a nice array. A very easy way to convert this back to a NumPy array, basically. So before I go into the next section, let's just take a quick look at what we covered so far with the data frame. We came up here, we created our data frame. We did it from a NumPy array first, setting the columns and the index. The index setting it up is the same as when we set up the series, so that should look very familiar. So is the whole format, the NumPy array, the index dates, and the columns. And remember, in our NumPy array, we're looking at row, comma, column. So 6 rows, 4 columns is how that reads in the data frame. And we went ahead and also did that from a dictionary. In this case, animal was the column name with all the data underneath that column, and then age with that data, visits that data, priority that data. And then of course we added our labels in there for our index. So there's no difference in there, but it automatically pulled the column names. Important to know when you're dealing with a data frame and importing a data frame this way. And then we did looking up dtype. We looked at head and tail, looking at your data really quick. We also did index and columns and values. And note these don't have the brackets on the end. So the next thing we want to do is go ahead, since we're dealing with data science, is we want to go ahead and describe the data. So we have df2.describe to do that, and we're going to manipulate it in just a minute, but let's just see what this generates. And you can see right here we have age and visits. So looking at our data from up above, let me just go all the way up here. animal age visits priority. And it does a nice job generating your age versus visits, which has all the data. You have your count, your means, your standard deviation, your minimum value, 25% are in this group, 50%, 75, and your maximum value. So this should look familiar as a data science setup with your describe for a quick look at your data frame data. So let's start manipulating this data frame and moving stuff around, and we'll start with transposing. And it is simply capital T for transpose. And when we run that, it flips the columns and the indexes. So now the indexes are all column names and the columns are all indexes, animal age visits priority. So if we had come in here with our data shaped wrong, up above where we had a 4x6, we can quickly just swap it if we had it backwards. Not a big deal. And we can also sort our data, something that you can't do, which is more difficult to do with a lot of other packages. In the data frame, it's really easy to do. Take our data frame df2 and we're going to sort underscore values by equals age. And so when we run this, you'll see the default is ascending. So we have 0.52, 2.53, and everything else is organized. So if you look at your indexes, they've been moved around because each index, it moves the whole row, not just the one piece of data is not being sorted. So a very quick way to sort by age our different data in the data frame. And in addition to sorting it, we can also slice the data frame. So I could do df2, and this should look familiar from earlier. We'll just do 1 to 3. So we're going to pull out, oops, it does help if I use a df instead of just d. And we're going to pull up just between 1 and 3. So we have not 0, which is A, but we have B, which is 2, or B, which is 1, and C, which is 2. So 1, 2, and then it does not include 3, which is the standard in Python. And we can even do something like this. We can combine them, which is always fun, because remember this returns a data frame. So if I take df2 dot sort values, and we'll do by equals age. This is just kind of fun. And then I'm going to slice it. There we go. Double check my typing and run it. And now you should see FA, because FA are now 1 and 2 on there. So you can very quickly create a whole string on here which narrows it, that you can sort it, then slice it, and do all kinds of fun things with your data frame. We'll just go back to the original one. Run. There we go. And if we can slice it by row, we can also query the data frame. So we can do df2. And this is a little different because I'm going to create an array within an array. And in this case, we're going to look at, let's do age, comma, visits. So look at the different format in here. We have 1 to 3. So we've done this by slicing by an integer value. And then on here, I've done df2 age, comma, visits in an array. And when I run this, you can see that we get just these 2 columns on here. We get age and visits. So it's a quick way to select just 2 columns or select number of columns you're working with. And if you saw up there, we did the slicing. Almost identical to slice is iLocation, which uses the integer location 1, 3. There's a push in Pandas to move to this particular setup instead of doing just a regular slice. And that's because this can be confusing when we slice 1 to 3 and then we select age and visits. So there is a push to go ahead and move to an iLocation, which does the same thing. You can see here BC, it's the same as up above. There's also a copy command, so we can do df3 equals df2 copy. We're just going to create a straight copy of it. And of course, if we do df3, it'll be the same as a df2 on there. So df3 equals df2.copy. And then let's do df3.isNull. So we're looking for null values. And this will return a nice map, and you'll see that everything is false, except when you go up here under the cat or H, they had a null there. And so if we go, they have a couple up here also underneath of, let's see, the dog. Okay, there's a bunch of nulls in here. There's D up here. So let's look at D down here, and you'll see false, true. There it is. There's our null value. So we can create a quick chart of null values. You can use this to do other things. We can leverage that null value to maybe take an average or something and fill those null spaces with data. And we can also modify the location. So here's our df3 location. And notice this is location, not iLocation. iLocation has I for integer. Location uses the In this case, the variable is on the left. And what we can do on here, and we'll go ahead and just set this equal to 1.5, and then let's pick a spot. Let's go back up here where we had, let's do f age is, let's see, what was we looking at? Oh, here we go. Let's do f and age. And up here, f is set to age of 2.0. And we find out that that's incorrect data, so we go ahead and switch to df3 equal, and then we go ahead and print out our df3. And if we go to f and age, it is now 1.5. So we're just changing the value in the df3. And this is changing the actual data frame. Remember, a lot of our stuff, we do a slice, and like it returns another data frame. This changes the actual data frame and that value in the data frame. So we've covered location, and iLocation is null. Making a copy, here's our iLocation, which is equivalent of a slice, and also selecting columns. So now we want to just take a little detour here, and let's look at df3 means. And this is kind of nice because you can do this. You can either do this you can select a single column here, by the way. You can just add the column selection right here like we did before. So we could have age, look up the mean, that just creates a series. If I run that, there's our age. But if I take that out, instead of selecting it, we can do the whole setup, and it has age and visits. So why doesn't it have priority or animal? Well, those are not integers, so it's really hard. They're non-numerical values. So what is the average? I guess you could do a histogram, which probably we'll look at that later on. But the only two things we can really look at is age and visits, and we have the average or the mean on the age is 3.375, and the mean on visits is 1.9. And let's do df3 visits. We'll go ahead and steal the visits again. And you remember all those different functions we looked at for a series? Well, we can do those here. We can do the sum. So if we run that, we'll see that these sum up to 19. We could also look up minimum. If you remember that from before, the minimum is 1, max. So all that functionality is here. I'll just go back to summing it up and adding it all together. So real quick, we've shown you how to take the series operations and put them into the data frame. And then we can actually, this is an interesting one, we can just do df3 sum, run, and you'll see the different summations on there. It just combines them. I like the way it just combines the strings on there for priority and animal. We've looked at is null. We've also looked at copying, along with the different slices which we talked about earlier. So let's talk about strings. Let's dive into the string setup on there. And let's go ahead and create a string series. String equals PD series. And we just put it right in there. We have A, C, D, AA, BA, CA, popped in a null value, cow and owl. I don't know why they picked cow and owl in the background. Someone must like those animals. And of course we can just do string. If we run that, you'll see, leave the R out, we'll get an error. But if we put it in there, you'll see that we have a simple series. 0A, 1C, 2D, and it automatically indexes it 0 to 8. And then we can go string dot lower. So when we're talking about our data frame, in this case, or our data series string, in this case, we use the string function, str, and we're going to make it lower. And if we go ahead and put the brackets on there, and you'll see that we've gone from capital A, capital C, so on to ABC. And baka, CBA, cow, owl, they were all lowercase already. And of course, if you want to go lower, you can also do upper. We'll go ahead and run that. And you can see we now have ACD, AAA, baka. Everything's capitalized except for the null value, which is still null. Alright, so we looked at a few basic string. You can see that string functions upper and lower. We're going to jump into a very important topic. I'm even going to give it its own header on here because it's such an important topic. What do you do with missing values? Panda has some great tools for that, so we'll dive into those. We'll work with df4, and if you remember the df copy from above, we're just going to make a copy of df3. And let's just take a quick look at the data we're working with. Oops, df3, forgot the 3 on there. There we go. So here we have our cats, snakes, and dogs. Hopefully not all in the same container, because that would be just probably mean to all of them. So we made a copy, we're going to be working with df4. And the reason we made a copy is we want to go ahead and fill the data. And we just simply do fill NA, and then we're going to give it the value we want to put in there. We'll give it the value 4. So I can run in here, and you'll see now that df4 now has where the NA was, is filled with the value of 4. Same thing down here. A lot of times we'll compute the mean first. So I might do a mean age equals df4, and then we want to go ahead and do age and dot mean, and then I'll do something like this, df4. I only want to select the age, and I want to fill that with the mean age. And I run in there, and you'll see that our df4 age now has the means in there. Just a quick way of showing you how you can combine these. Let me go back to our original one. There we go. And run that. And keeping with good practices, df5 equals df3.copy. And then we'll print our df5, which should be the original one. And then on the df5, we can now drop our missing data. I'm going to simply drop NA, and we're going to use how equals any. So I'm going to drop any row that has missing data in it. And you'll see we had D here with missing data and H. And then let's go ahead and see what df5 looks like when we do that. There we go. And there it is. D is gone and so is H. So we create a new data frame off of this, missing those values. Now, if you have a lot of data, dropping values is a good way to take care of it because you don't miss some data. If you have not a whole lot of data, you're working with like the IRIS data set or something like that, or something small, you want to start trying to find a way to fill that data in so you don't lose your computational power of the data you got. So just a quick look at processing null values or missing values. You can fill them, usually with the means. Some people use medium or the mode. There's different ways you can fill it. One way is means. And we can also just drop those rows. Those are the two main things we do with missing data. Here we go. We're going to cover next. I so love data frames for this. File operations. It saved me so much time because they have so many different tools for bringing data in and saving data. So when we're looking at the data frame file operations, it's really streamlined. I don't know how many times I'll go on to different data downloads and they'll have Panda download standard on there just because it's so widely used. So let's start with the most common file is a CSV. So we have df3 to CSV or animal. And let me just show you what the folder is going into. Right now I have some untitled, a few things in here, but nothing labeled animal. So we go ahead and run this, and this has now saved the animal to my hard drive. And you can now see the animal folder up here, and if I, let's do edit with a notepad. Oh, let's open it up with just a regular notepad. There we go. Or WordPad. If I open that up, you can see it's comma separated. Our titles, they don't have an index on the categories on the top. And the index, comma, then all the different data is separated by commas. Standard CSV file on there. And if we're going to send it to CSV, and notice the format is .to_CSV. And it's just the name of the file we're sending it to. You can also put the complete path. By default, it's going to go whatever the active directory this program's running on. That's why those other folders are in there. So we have our df3 to CSV, and then if we're going to put it in there, we want to also get it back out. And we'll call this one df_animal equals pd read_CSV. I always have to remember it's to_CSV and read_CSV. I always want to do like a capital in there and not the underscore. We're going in here again, it's the active directory. So if I now do print out my df animal, and let's just do the head. We only want to look at the first 3 lines. So if I go ahead and run this, we'll see the first 3 lines, and they should match up here what we saved to our CSV. So very easy to save and import from our CSV files on here. And it turns out df3 also has a to Excel. They actually have a lot of different formats, but old school Excel was real popular for so long, still is. We can go ahead and save it as animal.xlsx. We're going to call the sheet named sheet 1, and then I can also do df, we'll call it animal2, and this one's going to come from, and the same format on here. There we go. So we still have our animal xlsx, the sheet 1, that's where it's coming from. Index columns equals none. So we're going to suppress the indexing on the columns. NA values, and it'll just assign it's 0 on up on your indexes. So if it says index columns equals none, that's what it does. And then we've added null values because there's null values in here, and we want to just make sure that they're marked as NA. And we'll go ahead and just print out the animal2, there we go. And let's run that. Let's make this, no, let's just do the whole thing. So we'll go ahead and run that. And it probably doesn't help that I completely forgot the read. So animal2 equals pd.read Excel. There we go, Excel. So now we go ahead and run it. And what we expect is happening here. We have the same data frame on here. And if I flick back to my folder, you can now see that we have the animal. One of these is in Excel and one of these is a CSV on here. And so there's our two file types on there. And they have other formats. These are just the two most common ones used. And I don't know how many times I've had stuff from Excel I need to pull out. If you've ever played with Excel, it's a nightmare in the back end because of the way they do the indexing. So this just makes it quick and easy to pull in an Excel spreadsheet. So we looked at two different ways to bring data in and save it to files. We've looked at all kinds of different ways of manipulating our data set and slicing it and creating it for our data frame. Let's get in there for your visualization. Always the big thing at the end, because one, it lets you check to see what you did, make sure it looks right. And then also, if you're going to show somebody else, it makes it very clear what's going on if they see something visual. So this is where a really important part of data science is. So let's go ahead and bring in our tools. We're going to do import numpy as np. We want to make sure we have our ampersand matplot library in line. This just lets Jupyter know that we're going to print it on this page. If you're using a different IDE, you don't really necessarily need that, but this does help it displays correctly in Jupyter Notebook. And if you remember for earlier, we could create a, we're going to call it TS. We're going to create a pandas, which are cute, cuddly creatures, versus a pandem, short for pandemonium? No. So we have TS equals PD series, and we're just going to create a random setup of 50. We'll do an index. We'll set it equal to the pandas date range today. Periods equals 50, so the 50 should match. And I want you to notice something here. I did not import the matplot library. Why? Because it's already in there. Pandas already has its built-in connection and interface with matplot library, so you don't have to import it. And we'll go ahead and do TS equals TS dot cumulative sum. We're going to do the cumulative sum. So a little reformatting there, and we'll go ahead and plot it. And let's take a look at what that looks like. So we have a nice graph here. We have the dates on the bottom. We've set this up so we have a nice range between, in this case, -4 to, looks like about 2 maybe, or 1, -4 and 1. So what we've done here, we plotted a basic series, just a single row of data, and we've set indexes on there. But we can also do the whole data frame on there, and let's see what that looks like. So first, let's go ahead and create the data frame. We have here random numbers, so we're going to do 50 by 4, and then we'll go ahead and create columns A, B, X, and Y. Just because we can. Index is a ts.index on there, so we're going to use the same index as before, just to keep it nice and uniform. We've already generated the dates to go with it. And then we can do, just like we did with the series, we can also do with the data frame, df equals df cumulative sum. So we're going to sum the whole data frame. And then we'll do simply df plot. And let's push that in, and let's go ahead and run this. And look how easy and quick that was to generate a nice graph with all the different data on there. So we have our shared index, we have the shared columns, and then we have the different data from each one that we can easily look at and compare. So very quick way of displaying data. You can imagine if you were working in, I think I mentioned stock earlier because I've been doing some analysis of stock lately. So you'd have your date down here, and then you would have stock A, stock B, stock XY, whatever it is. And you can put them all on one chart and see how what they look like next to each other. And this isn't too far off from what some of those graphs look like, and this is just randomly generated. So stock has a lot of randomness in it, which is one of the reasons I actually play with it for doing some of my models for testing them out. Now, there are a lot of features in pandas. So we're going to show you one more thing on here. There's some of the things, like I didn't go too deep. We looked at the top two for importing data from a CSV and from an Excel spreadsheet. Showed you how to quickly plot the data. There's more settings in there you can do. We're going to do one more thing down here, and this is kind of a fun one. Change this to a markdown and run that. So how would you remove repeated data using pandas? And this is where you have a data set that comes in, and maybe it's feeding from one location, and instead of noting that it's repeated the date. Like, oh, let's go back to stocks. That's a good visual. We have the stocks from the 23rd, and it adds another row, and it's the same row. It's importing the 23rd again and again. So now you have that data repeated 3 times, and you need to go back and figure out how to get rid of it. How do you track that down? So let's start by creating a quick database, or data frame. Not a database. I keep saying database. It's a data frame. And we'll just make this data frame using our dictionary going in. This data frame only has one data series in it, which is fine. So if we do df to print it out, you'll see A1, 2, 2, 2, 2, 4, 4, 4, 5, 6, 7, and so on. And so how would you remove that? Well, there is a neat feature in data frames called shift, along with another feature that lets us select just certain information. And we'll go with the location function. Put that in brackets. Remember that from above, location. And then in the location, let me just spread this out a little bit so it's real easy to read. In fact, I'm going to go upscale on that since we're doing a little bit more complicated here. What you can see on this, on the location, is I have dfa.shift. So this is going to shift up 1 by default. You can actually change this to 2 or 3. You can even do a -1 and it shifts the other way. But it's going to shift up by 1 by default. And it's going to say if that does not equal df of a, then we want that. And if you look down here, we had 1, 2, 2, 2, 2, 2. When we run this logic on here and we do the shift, it now gets rid of all the duplicates. So we went from 1, 2, 2, 2, 2, 4, 4, 5, whatever it was. Here it is, 1, 2, 2, 2, 4, 4, 4, 5, 5, 5, 6, 6, 6, to 1, 2, 4, 5, 6, 7, 8. And you'll see on the index, it just deletes them out of there so the index stays the same. Obviously, you don't want the dates to change if you're working with an index dated setup. So it just deletes those duplicates out of there. This is just a quick way to introduce you to, 1, the fact that you can add logic gates into here. And 2, the iLocation allows you to use shift. So there's the shift function, and then the iLocation selects that based on true or false. Wow, so we've actually covered a lot today in Pandas. We've really covered into the basics of selecting your different series out of your column, out of your data frame, how to index rows, how to slice, how to plot. Hopefully you'll take this beyond that and start combining these different things, and you can create long strings and really explore your data, generate some nice graphs. If you're in Jupyter Notebook, it's a great demo to show others. And I didn't know this about Jupyter Notebook. You can do this in Jupyter Notebook, and then you can download. And I never really look too closely at all the downloads. But you can download it as an HTML and post it to your blog. So it's got a neat feature in there. But any of this is a really powerful tool. All of this is really powerful tools for doing your data science. Today we're going to study the matplotlib library and the Python code. So what's in it for you? What is matplotlib library? Types of plots, plotting graphs and subgraphs, adding a graph inside a graph, graph parameters, title, label, legend, line graphs, line types, color and transparency, canvas, grid and axis range, 2D plots, scatter, step, bar, fill between, radar chart, histogram, contour image, 3D surface image, and then we'll hit a practice example pie chart. So let's start with what is matplotlib library. Matplotlib library is an open source drawing library which supports rich drawing types. It is used to draw 2D and 3D graphics. And there are so many packages in the matplotlib library, we're going to cover the basics. And there are so many packages that sit on top of the matplotlib library that we can't even cover them all today. But we'll hit the main ones so that you have a good understanding of what the matplotlib library is and what the basics can do. You can understand your data easily by visualizing it with the help of matplotlib library. You can generate plots, histograms, bar charts, and many other charts with just a few lines of code. And here we have some basic types of plots that you can see here that we'll go into. We have the bar chart, the histogram. Boy, I use a lot of histograms in my stuff. A scatter plot, line chart, pie chart, and area graph. Let's start plotting them. And to do this, I'm going to be using Jupyter Notebook. You can use any of your Python interfaces for programming or scripting and running it. Of course, we here really like the Jupyter Notebook for doing a lot of basic stuff because it's so visual. And in our Jupyter Notebook, which opens up in this case, I'm using Google Chrome, you can go up here to New, and we'll create a new Python 3 and set that up. If you're not familiar with Jupyter Notebook, we do have a tutorial that covers some of the basics of that. And you'll look at any of our tutorials. I usually cover a number of them showing how to set up Jupyter and Anaconda. I myself use Jupyter through Anaconda. In fact, let's go ahead and open that up and just take a look at this, see what that looks like. You can see your Anaconda Navigator. If you install it, it will automatically install the Jupyter Notebook. And that also installs a lot of other things. I know some people like the Qt console for doing Python or Spider. I've never used them. I actually use Notepad++ as one of my editors. And then I use the Jupyter Notebook a lot because it's so easy to have a visual while I'm programming. And even simple script in Python, I'll take it from the Jupyter Notebook and then do a save as. You can always go under File, and you can download as a Python program. So that will download it as an actual Python versus the IPython that this saves it as. So let's go ahead and dive in and see what we got going here. And let's go ahead and put Matplotlib tutorial. And I'm going to turn this cell into a markdown so it doesn't actually run it. But you can see it has a nice little title there. That's all Jupyter Notebook. And then from Matplotlib, let's import PyLab. Get that back one. And then let's go ahead and just print. We'll go PyLab and the version. Let's go ahead and run this. So we're going to import our PyLab module from the Matplotlib. And we find out that we're in version 1.15.1. Always important to note the version you're in. Probably I was reading an article that said the number one thing that Python programmers struggle with is remembering what version they're working in and making sure that they're going from one platform to the other with the same version. And if we're going to graph things, I think we need some data to graph. So we're going to import NumPy as NP. Now, if you're not familiar with NumPy, definitely go back and check out our NumPy tutorial. There's so many different things you can do with it, dealing with reshaping the data and creating the data. We're just going to use it to create some data for us. And there is a lot of ways to create data, but we're going to use the np.linespace. So we're going to create a NumPy array. And the way you read this is we're going to create numbers between 0 and 10. And we're going to create 25 of these numbers. So we're just going to divide that equally up between 0 and 10. And if we have x coordinates, we should probably have some y coordinates. And we'll do something simple like x times x plus 2. And let's just take a look. We're going to print x and print y. Let me go ahead and run this. And let's see what we got going on here. So we have our x coordinates, which is 0, 0.4, 0.83, etc. And you can look at this as an xy plot. So where we have 0, we have 2. Where we have 0.416, we have 2.17. And just as a quick reminder, we're going to do print np array x comma y dot reshape 25 comma 2. And the reason I want to do this is I want to show you something here. A lot of times a program returns x comma y, and it's an array of x comma y, x comma y, x comma y. And so when you're working with the pyplot, you have to separate it out and reshape it. So if I start off with pairs like this, I can reshape them. If I know there's 25 pairs in there, I can switch the 2 and the 25. And this is kind of goofy, but we'll do it anyways. Reshape. So I'm going to reshape my 25 by 2 back to 2 by 25. And if I run that, you'll see I end up with the same output as the XY, the two different arrays in here. And this is important that we want X and Y separate. Again, that's all NumPy stuff, but it's important to understand that this is a format that Matplotlib works with. It works with an array of X's, and they should match your array of Y's. So each one has 25 different entities in it. And then for our basic plotting of this data, it only takes one command to draw a graph of this data. And so we use our, from up here where we imported PyLab, we take our PyLab, and the key under there is plot for plotting a line. And then we want our x coordinates and our y coordinates. And we'll throw in R. And the R simply means red. So we're going to draw the line in red. Let me go ahead and run that. You can actually switch this around if you wanted to do different. There's B for blue. We have a lot of fun. Yellow. Hard to see yellow. There we go. But we'll go ahead and stick with red. Run. And when you're doing presentations with these, try to be consistent. You know, if the business and the shareholders send you a spreadsheet and they have losses in red, use red for losses in your graph. Try to be consistent. Use green for profit, for money. You don't have to necessarily use green, but it's whatever they're using, whatever the company's using. Try to mirror that. That way people aren't going to be confused if you switch your data around and every time one graph has red for loss and one graph has blue for loss. It gets really confusing, so make sure you're consistent in your graphs and your coloring. And something to know, because we're going to cover this in a minute, this is your canvas size. So we have a canvas here, and what we're going to do next is we're going to look at subgraphs. Okay? So let's take our PyLab and create a subplot. And one of the things also to know when we're working with the Matplot library, I'm not setting, when I do this, this is my drawing canvas, the PyLab. So once I've imported the PyLab, I'm drawing my images on there. Very important to know. And with the subplot, we're going to give it some different values. And we're going to represent by rows, columns, and indexes. And let's do 1, 2, 1. So it's going to be the first row, second column, and the index is like you can stack your graphs and things like that. We don't worry too much about indexes, but rows and columns. We want to go ahead and use row 1 and column 2. And if we're going to have one object, we should probably have two, but before we do that, we have to plot data onto the subplot. So the order is very important, and we'll go ahead and stick with our x comma y, and let's do this. We're going to add in a third parameter here. Remember we did red? We're going to add shorthand dash dash for dashed lines. So this plots the data into row 1, column 2. And if we're going to do that, let's do another one, pylab.subplot. And if we're going to do row 1, let's do column 2 and index 2. And this time we're going to add G for green, and this denotes a style. And if we're going to set up our PyLab subplot, there we go, PyLab, we got to go ahead and plot that, PyLab plot. And instead of XY, we want Y comma X. Whoops, I messed up. This is in the wrong spot. There we go. We'll move that down here real quick because that goes in the plot part. So the subplot tells it the row, column, and index, and the pyplot tells it what data. In this case, we switched them, and the color, and then the style shorthand. Now let's go ahead and run that. And you'll see it takes this canvas, splits it in two, and now we have two different graphs. And we have the red one with dashed lines, and we have the green one, which has little stars going up. And if we take this, and let's just for fun, let's change this and run that with an index of 1. It puts them both on the same index. It also gives me a warning because it's a strange way of doing two subplots. It's depreciated. There's another way to do it. But most people just ignore that warning because it's not going to go away anytime soon. Now that's using the same setup. What happens if we do, instead of this, let's change the column on here and find out what happens. And if we do the column, it didn't really like that on the setup, it just disappears. So let's keep our column as 2, and let's change the row on the second one to 2, and run that. And you'll see again it kind of squishes everything together and causes some issues. So let's take the index, so they each need a unique index. And you can see here where I've made some changes. I said row 2, and look what happens when I change to column 2. So I now have row 2, column 2, index 2. It squished it up here, so you could put another graph underneath is what that does. And there's all kinds of different things. You really have to just play with these numbers till you get a handle on them, because you have to repeat it 164 times according to Cambridge University if it's completely new to you. And you can see right here where, here we go, 3, run. There we go. But you can see it takes a little bit sometimes to play with these and get the numbers right. Oops, I hit the wrong one, that's why. Let's go 3 there, run. There we go. Now it's overlapping, so I have this doubled over here on the right. For now, we'll just go ahead and leave this with the where we have column and row 2 and the two different indexes so they appear nice and neatly side by side. And then, as we just saw, as we were flashing through them, we can put them on top of each other. And let me just highlight that and copy it down here. Paste it down there. And here we have 1, 2, 1. And then we'll do 1, 2, 1 also for this one, and that puts the two subplots directly on top of each other. It gives us that warning, and you can see we now have two different sets of data graphed on top of each other. And you can also see how it did the indexes. Since one of them is from 0 to 10, that's the green one on the x-axis, and the other one is from 0 to 10 on the y-axis. So it took the greatest value of either one and then used those as a shared value. So let's next look at operator description. And we'll go ahead and turn this cell into a markdown and run that so it looks nice. So Fig, and you remember I talked about the canvas earlier. I briefly mentioned it. We're going to look a little bit more at the canvas later on. But that's what the figure is. Fig, we're going to add axes. So we're going to initialize a subplot, add the subplot, in rows, in columns, and all kinds of different things with this that you can do. Let's look at that code and see exactly what's going on. And I want you to notice that there's Fig, which is the actual canvas in the Matplot library. And AX is commonly used to refer to the subplots. So when we're creating subplots, you'll see AX equals PLT subplot. Earlier, we did the PyLab. So let's go ahead and import PyPlot from Matplot library. And we're going to do it as PLT. You'll see that a lot. That's really the standard in the industry, is to call it PLT, just like Pandas is PD and NumPyArray is NP. Certainly you could import it as whatever you want, but I would stick to the standards. And we're going to do the same graph as we did above with the PyLab, but with the PLT. So if it looks familiar, there's a reason we're doing this, because we want to show you how the figure part works and working with the canvas goes. But we're going to do the same plot as we did before. And we'll call it Fig, and we're going to set that equal to plot figure. So there's our figure or our canvas on there. And let's create a variable called axes, and we're going to set that equal to fig.add axes. And in this, we're going to control the left, right, the width, the height of the canvas from 0 to 1. And so we can go ahead and I'm just going to put some stuff in there. I got 0.5, 0.1, 0.8, 0.8. So when you're looking at this, this is a 0 to 1, or you could say 50%, 10%, 80, 80%. But it's a control. It's going to control your left and your right, along with the width and the height. So the width and the height, we're going to use 80%, and we're going to have like a little indent on the left and the right. And this should look familiar from above. Axes.plot, x comma y, and then let's give it a color. How about red? Since we're recreating the same graph, let's keep it uniform. Oops, and it helps if I use AXIS instead of AXES. I don't know where that came from. But this looks identical to the one we had up above. So here's our axes plot, x comma y of red. Same graph, same setup, but this time we've added a variable equal to the figure.addAxes. So our plot figure is our canvas, our axes is what we're working in, and then our axes.plot x comma y. And again, we can draw subgraphs. Put that down here. Just like we did before. And a little different notation here. We're going to have fig comma axes equal plt.subplots. And in here it's going to be the number of rows. We're going to do one row, and columns equals 2. So if you remember before, that's what we did. We had one row with 2 different graphs on it. We're going to do the same thing. But note how we did this. Here's our figure, or our canvas, and our axes. We're going to create actually 2 different axes. We're going to create row 1, column 2. And so axes is an array of information. So we can simply do let's do ax in axes. And this will now look familiar. Ax.plot. We're going to do x comma y. We'll go ahead and make it red. Keep everything looking the same. Remember, nice uniform graphs, everything looks the same. And if we go ahead and run this, you'll see we get 2 nice side-by-side graphs. So just as we had before, the same look, the same setup. And just for fun, let's change in columns to 3. We'll run that. And now you'll see we'll have 3 on there. And let's see if we make it a little bit more interesting. We'll do in rows equals to 2. And you can see down here we're going to get an attribute error because it's trying to scrunch everything together. So it does have a limit how much stuff you can put in one small space. That's important to know. You can fix that by changing the canvas size, which we'll look at in just a minute. And there's other ways to change it on here. But here we go. We can do in rows 2 and columns equals 1. You can see 2 nice images right above each other. We'll go back to the original. 1 row, 2 columns, side by side, left to right. And we can also draw a picture or graph inside another graph. And that's kind of a fun thing to do. It's important to note that we can layer our stuff on top of each other, which makes for a really nice presentation. So let's start by fig. We'll create another figure. So we're going to start over again with our canvas. We set that equal to plt.figure. So there's our new canvas. And let's do axes. We'll call it axes 1 and 2. Axes 1 equals fig.add axes. Remember this from earlier? And This here, similar numbers we used before, saying how big this axis is, this figure in the axis is. So this is going to be the big axis. And let's do axis 2 equals another figure at axes, and then 0.2, 0.5, 0.4, 0.3. And if we're going to do this, they need data on them. So let's go ahead and plot some data on our axes. So axis 1 dot plot. And we'll make this simply x comma y comma, make it red. And then let's go axis 2 dot plot. And let's reverse them. Y comma x comma green. There we go. Doing what I told you not to do. You shouldn't be swapping axes around and plotting your data in 5 different directions because it's confusing. But let's go ahead and run this and see what this looks like. And then let's talk a little bit about this. We talked about the 0.2, 0.5, 0.4, 0.3. And let me just grab the annotation for that. That's left, right, width, and height. So we have in here that this is going to be left, right. So here's our left is 0.1n, 0.5. And you know what? Let's just play with this a little bit. What happens when I change this to 0.1? Moves it way over to the left. So there's our 0.1. So we can make this 0.4. Run that. There we go. So you can see how you can move it around the branches on here. 0.2, 0.5 is the left, so that's our right. So let's see what happens when we do let's make this 0.1. And that actually is, they had it down as left, right. I thought this was wrong. It's actually how far from the bottom. Let me switch that on here. Bottom. There we go. So we had here on this. We can go ahead and put that back to 0.5 and run that. And this is 0.3. Let's make this 0.3 also. And that is the width. And then, of course, there's the height. We can make that really tiny. Actually, let's do 0.2, and let's run that. And you can see it changes the height on there. We can make it even smaller, 0.2 by 0.2. And as you can see, you can get stuck playing with this to make it look just right. It can sometimes take a little bit. Certainly, once you have the settings, if you're doing a presentation, you try to keep it uniform, unless it doesn't make sense for the graph you're working on. Try to keep the same colors, the same position, and the same look and feel. And I mentioned earlier we can adjust the canvas size. So this is from earlier. I just copied it down below. We're going to replot the same data we've been looking at. And what we can do is we can change the figure size to 16 by 9. And let me run that and show you what that looks like. So it fills the whole screen. And then if you are, normally when you're working on the screen, you don't worry too much about this. But we can set the DPI to 300. Run that. There it goes. This is your dots per inch. And if you are doing an output of this and you're printing a hard copy, you want the higher quality. I would suggest nothing under 300 if it's a professional print. You might get a little less than that, but whenever I'm doing professional graphics and printing them out on something, 300 dots per inch is kind of the minimal on there. You can go a lot higher too, but keep in mind the higher you get, the more memory it takes and the more lag time and the more resources you use. So usually 300 is a good solid number to use in your dots per inch. And you can see it draws a nice large canvas here, which is 16 by 9, and then the DPI is 300 on here, so it's a little higher quality. And just out of curiosity, I wonder how long it takes to draw something double that size, 600. And you can see here where at 600 DPI, it's going to take a while. There it goes, just because it's utilizing a lot more graphics on there. And let me just go back to the 300. Now let's do a 100. You're not going to see a difference on this because it is web-based graphics are pretty low. And up here you saw I did this with the plot figure. This works the same if I do figure axes subplot, figure size, and then we'll go ahead and do axes plot x comma y comma, we'll stick to red. Let's go ahead and run this. And you should get almost the same thing here. Here's our axes on the subplot on here with the fixed size and the DPI. Let me take this all out. Let me just remove all that real quick. Run it again. There we go. Now we're back to our original figure. And let's look at some of the other things you can do with this. One of the things we can do is we can set a title for the axes. So axes set title. You'll see right here, since I put this on the axes, it's the main title for the whole graph. And if you're going to have a title, you should also label. So we can label our X label, and we can set our Y label. In this case, we're just going to call it X and Y. Keep it nice and uniform, and if we run this, you'll see that we've added a nice X label and Y label. Whoops, where'd they go? And it turns out in this environment that you have to put it before the title. So let me go ahead and put it before the title. And there's our X, Y, and let me run that. And of course, we can also do up our size a little bit so you can see what's going on a little better. So here we have X label X. If you come down here, you'll see our X label and our Y label. We can, of course, change this to X label. You can change this to Y. It can be whatever you want on here, of course. And our title graph. There we go. Run. So here we have our title graph, our Y label, and our X label all set up on our nice little plot. And then before we move on to the next section, let's do one more thing on here. We have a thing called the legend. And we're going to set our AX legend, label 1, label 2 up here. That's the format for it, but let's go down here and actually use it. I'm going to do two different plots. We're going to have axes plot x by x times x squared and x cubed. And if I run this, you'll see it puts two nice graphs on the setup on there. But it's nice to have a legend telling you what's going on. So for the legend, we can actually do axes, since we have the two plots, legend. And on here, we've created an array. And we have y equals x squared, y equals x cubed. You can actually put this as whatever you want. Those are just strings. And then location 2. And let's go ahead and run this and see what that looks like. And you can see it puts a nice legend on the upper left-hand corner. Location 2. We can do location 3 and run it. And it drops it down to the bottom. Location 1. I can't remember where that's at. There we go, upper right. So each one of these is a number that refers to the different locations on the screen. 0, kind of have to play with them or look them up to remember where they're at, but they do work. It just kind of moves around depending on where you want your legend at on there. So on this section we cover the title of the graph, the Y labels, and legends. We're getting into starting to look really fancy here. So we now have something we can actually put out. You'll see the title of the graph looks a little fuzzy. So I might, in a web setup, put the DPI up a couple notches. Maybe put it at 200. 100 might work fine. Just so, that's something to notice on here when you're playing with these different things. We had our subplots DPI equals, let's do 200 and just see what that looks like. So you can see it now is a lot clearer. It's also larger. So it's a nice little feature you can throw in there with your DPI dots per inch. So the next section is let's look at some graph features. We're going to look at line color, transparency, size, and a few more things on here. And, oops, I forgot the main title. So we have our figure and our axes equals our plot and subplots. And I'm going to go ahead and do a DPI equals 150 so the graph comes out nice and large and easy for you to see. And let's go ahead and do 3 plots on here. We'll do x by x plus 1, so it's just going to be a straight line. Plot x plus 2 and axes dot plot x plus 3. This looks like we're doing nearest neighbor setup or showing how it located data and putting your lines on there between the nearest neighbors. There we go. So it draws a nice little graph with 3 lines on it. One of the things we can do is we can control the alpha on this. Oops, and you can actually see when they did these lines, it automatically pulls in different colors for your setup. So there's some automatic things going on in there. And a lot of times we do that comma R, but we're going to do color equals red, another notation on here. Let's go ahead and run this. Now we have a bright red line down there. And with the Matplot library, you're not limited to red. You can also use one of the many different color references as you see here with the pound sign 1155DD. Which is just blue. And we can do the same thing with another color on here, which turns out to be green. And I can just as easily do this. Green, blue, oops, there we go, blue, and run that. And you'll see here we have red, blue, and green. And what I want to do is I want to make this, we're going to set what's called the alpha on this. And we're going to set this equal to 0.5. So this is halfway see-through when I run this. And it's almost going to look pink because you can see through it. And let's change this just a little bit, just to make this kind of fun. Let's square it. There we go, run it. So now we have this nice square that comes up, and you can see when it crosses it, because I plotted these 2 lines after it and they have no alpha, the red is behind those lines, or in this case pink, because we did the alpha halfway through. So let's go ahead and do this. Alpha equals 0.5, and you know what? Instead of squaring it, let's take it to the 0.5 power. That'll be kind of interesting to see what that does. We'll just go to keep it squared. There we go. And run that. And let's go back and look at this where it crosses over. And the first thing you'll see right here is on the blue, it's kind of light blue now. You can see how the 2 colors add together. You get almost a purple on there. So I can clearly see where the red crosses the blue line. And then the green just blanks it over because I didn't do any opaqueness, no alpha on there. So this is great if you have lots of data that crosses over and you need to be able to track those lines better. And we'll go ahead and do this 0.5, and we'll run that. Oops, I did equals 0.5. Let me go ahead and run that. And so you can see right here, now you can easily see the red line, how it crosses the green and the blue down here. And if we want to, we can do this as the default is 1, is solid, so we can change this all to 0.8. Let me just do that. Oops, 58.8. There we go. Run. Oops, I must have hit a wrong button there. Let me try that again. I accidentally got rid of a bracket. And let's go ahead and run that. And we come down here and look at this. You can still see where it passes behind them, but the green dominates and the blue dominates because we're now at 80% instead of 50%. And you can do less. That's kind of fun, although at some point the lanes kind of fade. So 0.5 is usually the best setting on there. We have a nice pastel here at 0.3, and you can easily see where they cross over. And just like you can play with the colors, we can play with line width. And let's try DPI 100 and see what that looks like on my screen. Equals 100. And we'll go ahead and just take our AX plot. Let's do 4 of these lines just so you can see how they look next to each other. Real quick here. There we go. And if I run this, they should all appear the same. It automatically does different colors on there. So let's do color equals blue. Forgot my quotation marks. There we go. And we'll go ahead and just make these all blue, just for purposes of being nice and uniform. And then what I want to do is I want to do the line width. Line width equals 0.25. And let's just copy and paste that down here. Let's do equals 1. About 1.5. And let's do just make this equal to 2. Let's see what that looks like. And when we do that, you can see it goes from a very thin line, a 0.5, a 1, our 1.5, and 2, which is twice the width of the 1. And if we're going to do different sizes, we had different colors, we had our alpha scheme. Let's take this whole thing here. Let's paste it down here and do another one. But instead of line width, let's look at styles. And something to note here, you can actually abbreviate this with LW. So line width can also be let's just do everything 0.2. And let's set up a line style. We'll do the first one dashes, and let me just paste that down here so I'm not doing a lot of extra typing. There we go. Take this out. So we have our dashed. We can do a dash dot. Oops, let's do the dash dot here. And a colon here. There we go. And there's a lot of different options. We'll look at a few more as we go down for different ways of highlighting data. But when you look at this, we have everything as a line width of 2, and now we have a straight line, we have a dash line, or a dot dash, and a dot 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 line. And then another thing we can add on here is we're going to do, here's our X plot, and we did X, let's do X plus 4, so it goes right on the top. We're going to do color black, line width 1.5, so it's a smaller line. And we're going to take the line and we're going to set dashes. So look how I've changed some of the notation here for my line and my ax plot. So I can set my line comma equal to ax plot, and then I can change the line settings this way. And when I run this, we run that on here, you'll see the 5, 10, 15, 10 creates a series of dashes that are varied in length. In this case, they alternate between a short dash and a long dash. And we can play with these numbers. Curiosity always has me what happens when you play with the numbers. Just to see what they look like, let's do this. Let's paste this down here. I'll do 2 of these just because they're kind of fun to play with. And let's change this from 10 to 3. And we're going to change this one from 15 to 4. And let's run that. And you can see the differences in the lines. Whoops, a little bit confusing on there, because I forgot to change the lines are all on top of each other. So let me change that really quick here. And let's run that. And now you can see here's our original dash line alternating. When I change these numbers on the second one, the very end value to 3, you can see now we have dashes of 5. Let's see, I'm going to guess this is a dashes of 5, skip 10, dashes of 15, skip 3, and then it goes back to the beginning. Dashes, 5 dashes, skip 10, 15 dashes, skip 3. And of course the last one we just switched up a little bit. It looks a lot more uniform because I'm using 2 sets of 10. Or if I did something like this and changed it to 30, it really becomes pronounced as far as the distances between them. And instead of 4, let's put 30 here also. 30 by 30, there we go. Really pronounced on that one. And let's look at one more important group for plotting our data. And in this, here's our plot we started with the x plus 1, x plus 2, x plus 3, and did it in blue on this one, 3 or 4 different blue lines. And this property, we want to add the actual plots, so you can see where the plots are on the graph. And for that, we might have marker equals O. And if we run this, you'll see it puts a dot for each of these, and there's 25 dots because we have 25 x values. So we actually have 0, and each of the different values of x, y are then plotted here with the dots. And we don't want to just limit ourselves to dots. We can also do plus sign, that's another option. Dots is most common. I actually like the dots the best. If we do the plus sign, you can see it puts a nice crosshairs or plus sign on there. And we can do a marker. There's a number of different markers you can use. And I think this one was it. S is another one, which is a nice square. And that's actually a good one, S for square. O for period. Okay, that's just kind of weird. So you can see that probably on these markers, another one is number 1. So if we run that, you'll see we now have these little hatch marks. And let's just go with the O on this one. By the way, this works with square really nicely. Some of the stuff we're going to do here in just a second. Let's do marker size equals 2. And change that to 5 and run that. And you can see here it puts a nice little tiny dot versus this size dot here. And this is interesting because it said 2. I thought it would be bigger. But if you do 0.5, it gets even smaller. And let's just do 10 to see what that looks like. Run. That looks huge. So marker size, a lot of these are dependent on the DPI and the setups. There's things that switch around as far as the way the size shows up. You got to be a little careful when you change one setting, it can change all the other markers. And then let's take our square on here. And we had marker size, so we also have marker face. We'll set that equal to red. Of course, I may change so it's up 1 notch. We'll run that. Whoops, must have mistyped something on here. And I did, it's marker face color equals red. And so when I run that, you can now see I have the squares on there with the marker face color. Of course, we can mix and match these. Come down here and we'll make this, let's make this plus 7. And we'll make this size 15. Marker face color equals, and we'll do green, just because. There we go, run. Very hard to actually see what's going on there. Still 25 dots, they kind of overlap. As you can see, they print them over each other. And of course, if we really wanted to make it look horrible, we could just make that really huge. Generally though, you'd want something a little bit smaller and cuter. We'll just try doing it this way. There we go. That's too small to even see the face. So 4, you can start to see the face on there around 4, and maybe on 8. 8 might be a good number for this. There we go, 8. Again, that all just depends on what you're trying to show and display. So we've covered a lot of stuff here as far as our lines. We've covered opaque with our alpha setting on there. Give us some nice pastels. You can see how they overlap and how they cross over. We covered the line width. Different size on there, different formats for the line itself, and these are all, you can combine all these. So you can have our line width equals 2, line style equals dash. You can bring this down here also to the markers. And then we added markers in, just standard circle, a plus sign, the square, a little tick, which uses a 1. Then we add a marker size and a marker color face, and we combine those. You see we get a nice different series of representations. We also briefly mentioned color, where you didn't have to use, like in here we used color black. Someplace up here, I'd have to find it, we use the actual number for the color, as opposed to, I changed them to red and blue. So you can get very precise on the color, if you have a very specific color set that you need to match your website or whatever you're working on. All of those are tools in the Matplot library. So we have one more piece to formatting the graphs that we want to show you, and then we have 2 big sections. We're going to go over the different graphs that they have along with a challenge problem. So let's go in the last section we're going to look at is limits. We're going to limit our data. So this first part I'm just going to paste in there. We're going to create our subplots 1, 2. So 1 row, 2 columns. We're going to do a figure size of 10, 5. This should all look familiar now since we've done a number of them. And we're going to go ahead and plot, and this is an interesting notation you should notice here. Our axes 0, so 1 we've used, instead of, you can just iterate through them, but they're just an array, so it's an array of 0 is still the axes of the first axes out of 2. And we're going to plot x, x squared, x cubed, line width 2. So we're going to go ahead and just plot two graphs right on top of each other without doing multiple plots on here. And we'll set the grid equal to true on here. Let's go ahead and run that. And you can see here are two plots with the x value going across. And I'm going to do something similar. And by the way, so you can just, if you look at it, you can see the grid on there. That's all that is. Easier to spot the data going across. We're going to take the same data for axis 1. So we have our plot of x, x squared, x, and x cubed, line width 2. And this time we're going to take our axis 1 and do y limit. It's actually set underscore y limit. This is the y-axis. So it's going to be an array of two values. And we'll do 0, 60. I'm just making these numbers up. The guys in the back actually made them up. I'm just using their numbers. And we're going to set the x limit. And we'll set the x limit as, don't forget our brackets there, 2, 5. So it's the same data going in, but we're setting a limit on it. And let's go ahead and run that. And let's see what it comes out of. And here we have the y limit 0 to 60. So we're looking at just the lower part of this curve here up to here. And we have the x limit 2 to 5. So that starts right here at 2, and you can see very different graphs. This is kind of nice because you could actually put one of these on top of the other if you wanted to draw focus to one part of a graph. Remember how we did that earlier, one inside the other? But just a quick note, you can easily limit your graph and kind of reshape the way it looks quite easily. And we can also add that grid down there if you want a grid. We'll run that and add the grid in there. Whoops, I guess you have to do the grid beforehand. Switch that. There we go. Sometimes the order on this is really important, so you may double check your order when you're printing these things out. It also helps if I change it to 1. So in this case it might not be the order. I wonder if it'll go back here as 1. There we go. So it doesn't matter the order on grid. But you can set the grid for easy viewing here. Nice setup on there. But you can see how we can limit the data. So let's start looking at some other 2D graphs and make this cell a markdown. So when we run it, it has a nice pretty title to it. And let's go ahead and create some data with an NP array. We'll do 0 to 5 on here. There we go. And let's look at 4 common graphs. We'll put them side by side. So we'll do a figure. Our axes equals plot, subplots, 1, 4 columns, and then figure size. Hopefully it'll fit nicely on here. It seems to do pretty good on here. And I'll go ahead and just run that since we're in there. Run. You'll see I have 4 blank plots on here. And we'll start with axes of 0. Let's set title. And we want this to be a scatter plot. A scatter plot just means it has a bunch of dots on it. So here's our axes of 0 dot scatter. Easy to remember. Scatter a bunch of plots on there. We'll do our n, or we can do x or n. There we go. And let's go ahead and do axes set title scatter. Oh, already did that. We're just going to do scatter. That's how you do it on there. That is how you create a scatter plot, simply with the scatter control. And we'll do, let's do the variable x plus, let's throw some randomness in here. Usually scatter plots have a lot of random numbers connected to them. That's why they do them on there. And so the bigger the x gets, the bigger the randomness, so 0.25 times the randomness. And what we should end up down here is with the scatter plot. And you can see as you go up, it just kind of has some random numbers and moves up and down the line. But plots just the points. So if you remember from back up here where we did marker, this is plotting basically just the marker. So it's a scatter plot. Probably less used is a step plot. So for axis 1, we'll go ahead and do a step plot so you can see what that looks like. And this time I'll use our n value instead of x. We generated that n value up here. And so for this we have n times 2, our n squared, n times 2, n squared. Line width equals 2, and if we run that, it creates a nice step up. Let's see, so we've got a scatter plot, we've got a step plot. Let's do a bar plot. And we'll use the same formula, n squared, alignment centered, because you can have them to the left or right, width 0.5, and alpha, if you remember correctly, that's how opaque it is. Let's see what that looks like on there. So we have some nice, you can see here a nice bar plot. It should look very similar to the step plot, but colored in. And we can change the width. Let's see what happens when we do 0.9. Run. And if we take width out completely, run that, you can see it starts coming together on there. And we can change the alpha. We can take the alpha out too and run that. So now you have the solid colors. And if we take out the center, and run that, everything, you really can't see the shift on here because that's actually the default on this. But these are common settings for the bar graph. Let me just put them back in there. There we go. Alignment, center, and alpha. Now, I can't say I've used a step graph very much. There's certain, I guess, domains of expertise that require a step graph. But the scatter plot and the bar graph, very common, especially the bar graph. And we'll look at histograms here in just a minute. So I use histograms a lot, especially in data science. But this is nice if you have very concrete objects. How many people are wearing yellow hats? That kind of thing. But if we're going to do that, let's go ahead and do the last one, which I see a lot more in the sciences. I'm certainly using the data science, but more like for mapping. I saw a publication on solar flares, and they were discussing the energy, and so filling in the graph gives it a very different look. So we're going to do the fill between. And it's just like you think it'd be. It's fill between, but with a underscore between them. And we'll do x and x squared and x cubed. And we'll do color green and alpha again, in case you had other data you wanted to plot on there. You can see it forms a nice squared coming up here. And also, if you look at the bottom one is your squared value, the upper line is your cubed value, and then it fills in everything in between. If you remember from calculus, this would be if you had like a motor and efficiency, they would talk about the efficiency going up and the loss, and you're looking for the space or the area between the two lines. So it gives you a nice visual of that. And let's look at a few more basic two-dimensionals. So we're going to have our figure size on here. We're going to do a radar chart. To be honest, I've never used a radar chart in business or in data science. I have to find a reason to use one now. So the first line for doing a radar chart, we have to add axes into the figure. And with this actually creates our, let's run it so you can see what it creates. It creates a nice, looks like you're on a submarine and you're tracking the hunt for red October or something like that. And it needs all of these. The polar is the fact that we're doing polar coordinates. 0.6.6 has to do with the size. If you take out any of these things and run them, you get just a box. If you take out the other half, you pretty much get nothing in there. And if you change these numbers, change them a little bit, you can see it gets bigger. They had 0.6 on here. I'll go ahead and leave it as 1 because that's just kind of fun. But that's all about the size on here, the height and the width. And then let's create some data. T equals NP line space. And this is 0 to 2 times NP times pi. So if you remember, that is the distance across, and we're going to generate 100 points. So this is just a thing of data we're putting together. Then we can simply do an AX.plot. And in this case, let's do T comma T, which would be a diagonal line on a regular chart. And we'll give it a nice color equals blue. And line width equals 3. Let's see what that looks like. And we can see here a spiral coming out. And remember, this would be just a diagonal line on a regular chart. What happens if we take this and instead of T times 0.5, there we go. And you can see it slightly alters the way it spirals out. We could do T times 2. Spirals out a little quicker. So it's kind of just a fun. Like I said, I've never used a radar chart. It's a column. But you can always think of radar in a submarine. Kind of looks like one of those, or in an airplane. And none of this would be complete if we didn't discuss histograms. Oh my gosh, do I use a histogram so much. And we'll use our numpy that we have set as NP to generate. Oh, it looks like we have 100,000 variables we're going to set equal to n. And of course, we create our figure and our axes. Subplots 1, 2, figure size 12, 14. So we're going to look at 2 different variations of the histogram. And we'll set a title, default histogram, set our title there. And then this is simply hist for histogram. And we'll just go ahead and put in our n in there. And let me run this and see what that looks like. And let's talk about what is going on here. So we generated an array here of data. 1,000 random arrays. It looks like they're mostly between -4 and 4. And then it adds up each one. It says 0, you have 35,000 that are 0. So that's what's most common on here. And we have 20,000 that are somewhere in this range right here between the -2 and, well, it looks like 1 and -2. And somewhere between 0 and 1, there's 30,000 numbers. So all this is saying is this is how common these variables are. And this will point you in so many directions when you're looking at data science to go ahead and run your histogram. So you should always have your histogram, and you can always put limits and all the other different things on your array, just like you did on the other graphs on there. And then we're going to do a cumulative detailed histogram. And all it is a histogram. Let me just do that. And we set cumulative equal to true and bins equal 50. And I really want to highlight the cumulative equals true is important. But we can now choose how many bins we have. In the first one, it kind of selected them for us. In this case, let me go ahead and run this. And you'll see it prints the data out for us. And here's our, whoops, must have missed, oh, there we go. It doesn't help that I put it over the old one. There we go, okay. So now you have your default histogram, and then we have a cumulative histogram. And we should have 50 steps in there. And let's just find out if that's true, not so much by counting them. I'm not going to count them. If you want to, you can count them. Let's just change it to 10 and see what happens. And we see here we have now 10 counts of that. And we could set that for 5 and run that. And then we have our 5 on there. And we go ahead and take the cumulative equals true out, just so you can see what that looks like. And let me run that on here too. That looks just like it did before. I think there's what, 1, 2, 3, 4, 5, 6, 7, 8. They have 8 different bins on here. Is what the default came out of. Put that back in there. Run. And so now it should look almost identical, and it does. And then we can put the cumulative back in, see what that looks like with the cumulative. And run that. And we can see how that shifts everything over and has a slightly different look. Wait, it shifts it all to the right? No, it doesn't actually shift it to the right. It's cumulative, so it's the total of the different occurrences. And so what that means is, like, if you consider this like for the year of rainfall, we have like day 1, you had a little bit of rain. Day 2, we have more rain. And so if you look at the number, this is 100,000, 35,000. So it's a cumulative detailed histogram of the occurrence as it grows. And rainfall is a good one, because that would be a cumulative histogram of how much rain occurred throughout the year. And we're going to look at 2 more graphs. We've already looked at a bunch of them. We looked at our radar graph. We've looked at scatter, step, bar, fill in, basic plots. We've looked at different ways of showing the data. We can increase the size of the line, the look, the color, the alpha setting. So let's look at contour maps. Just put that in there. There we go. Draw a contour map. And before we draw a contour map, we need to go ahead and create data for it. And if you have contours, your data is all going to have 3 different values. So let's go ahead and create the data here. We have our, you'd import your matplot library, your numpy, so we have our numbers array. And we'll import matplot.cm, and that's your color maps. So you have all these different color maps you can look at. There's like hundreds of color maps. So if you don't want to do your own color, you can even do your own color map. They're pretty diverse. And of course our PLT, our pie plot. And to generate our different data, we're going to create a delta 0.025, and we'll start with x, and we're going to create an array between -3 and 3 in delta increments of 0.025. And we'll have our y, we'll do something similar, and then we'll create our xy into a mesh grid. Again, these are all numpy commands, so if you're not familiar with these, you'll want to go back and review our numpy tutorial. And we'll do an exponential on here, -x squared minus y squared for our z1. We'll do a z2, so we have 2 different areas, and z equals z of 1 minus z2 times 2. So we've created a number of values here. And let me go ahead and run this. And let's plug that in so you can see where those values are going. So once we've set these, we're going to create our figure and our x from our PLT subplots. We're going to create the variable cs. And this is going to be our contour. So right here, CS is our contour surface. And we're feeding it X, Y, and Z. And if you remember, X, Y we created as our X and Y components using our mesh grid. And you know what? Let's do this. Just because it's kind of good to see this. Let's go ahead and print X. And let's print Y. And I always like to do this when I'm working with something that's either is really complicated, in this case is what we're looking at, or you don't understand yet. So we've created a mesh grid. We have x, y, and when we're done with this, we end up with, here's our x, and this set of values, and our y. So these are x and y coordinates. And then we've also created z based on our x and y. So we have x, capital Y, and capital Z as our 3 components. X and y being the coordinates, while z is going to be our actual height, since we're doing a contour map. So we created our contour map from our x, y, and z coordinates. We want to go ahead and put in a C label. Maybe we want to go ahead and do a title on here. We'll put that in our set title, and this is a contour. There we go, contour map. And let's go ahead and run this and see what that looks like. And you'll see we generated a nice little contour map. There's different settings you can play with on this, but you can picture this being you're on a mountain climb, and here we have a line that's represent 0, maybe that's sea level, and then moving on up you have your contours of 0.5 and then -1 and different setups, little hills. I guess if it's minus, that's like a pit. So I guess you're going down into a pit at -5 and -1. And on the other side, you can see you're going up in levels. So here's a mountaintop, and here's like a basin of some kind. And in data science, this could represent a lot of things. This could also be representing 2 different values and maybe profits and loss. I don't know if I'd ever really do that as a contour map, but I'm sure you can be creative and find something fun to do with a contour map. And then we're going to look at one last map, which is the 3D map. And those can be really important as a final product because they can show so much additional information that you can't fit on 2-dimensional graphs. There we go. Draw a 3D image. And so we're going to import from our MPL toolkits the mplot 3D and the axes 3D. We're going to import axes 3D. This is what's going to let us work with the 3D image. And this should look familiar. We're going to create another figure just like we did before. Figure size 14 by 6. That's a good fit on the screen. We'll go ahead and run that. So we have our figure, and let's go ahead and take our x, and we're going to set that equal to fig.add subplot. That should also be familiar from earlier. And we're going to work with, this sets the settings for the projection. And we're going to use 1, 2, 1 projection 3D. And we'll see what that looks like in just a minute. And we just created some 3-dimensional data here before, where we had X, Y, and Z, capital X, Y, and Z. So we're going to reuse that data. We're just going to use that since this is also a 3-dimensional image. So let's use that for a 3-dimensional graph. And we simply do AX plot underscore surface and our capital X, capital Y, capital Z. So there's our data coming in. And we're going to add some settings in here. We're going to do R stride 4, C stride 4, and line width 0. And I'll show you what that is here in just a minute. Let's go ahead and run that so we can see our graph. And of course it helps if I don't add an extra comma in there. And you can see it generates this really beautiful 3-dimensional graph. So let's take a little bit time to explore some of these numbers we have going in here. We have the R stride 4, the C stride 4, and the projection 3D. Projection 3D is the important one because that's telling us that this is a 3D graph here. So what are these first numbers? 1, 2, 1. Let's just change one of these. I'm going to change this to 5, and it's going to give me an error. Let's change it to 1. And that didn't work. Let's change this middle one to 3 instead. And you're going to see how it starts reshaping the size and how it fits on the screen. And we'll change the first one to 2. We'll run that one. And again, it's changed the dimensions and the size and how it fits on here. Play with these numbers till you get a nice look and feel for it. Part of it is the tilt and the angle. I'll do 7 on this one. There we go. You can see it really shifted it there. But again, that changes the size and how it fits on the canvas. But we'll leave it at the 1, 2. And just so you get a good look at what we're talking about here, this is column width and index from before. If we do 1, 1, 1, you can see that it now spreads it out all the way across. It uses the whole setup on there. So this has to do with the size and how big you want it to be. Now, there's one term that we didn't cover in this yet, but we've used it throughout the whole setup. And I'm just going to type that down here, even though we're not going to go into detail. And that's the term heat map. You might see that is kind of starting to lose ground as far as a common reference, but there sure are a lot of people who still talk about heat maps. What is a heat map? Well, it is simply a color map. That's all it is. So if you ever see the term heat map, that refers to the fact this is in different colors representing different heights. That one isn't a heat map, but you can see up here we switched into, let me go back up here, here we go. This one has different colors for the different values. A lot of times you'll use, like instead of X and Y, you might do a heat map where you have a 4th value, and the 4th value represents the color. And so you'll see this 3D image in a nice colors represented by a heat map. That's all it is. So if you see the term heat map, that only means we're plotting some of the data in color to make it stand out or to give it a 4th dimension in this case. So we've covered a lot of things on Matplot, and that brings us, covered all the basics, so that brings us to practice example. And this is going to be the challenge for you. And let me go ahead and change our cell type markdown and run that so it looks pretty. Practice example, write a Python program to create a pie chart of the popularity of programming languages. Okay, excellent. And if you're going to have a challenge, we need some data. And I'll just throw in import our matplot library at the beginning. You should do that automatically. And so for our data to plot, we're going to have our languages. We're going to have Python, we're going to have Java, PHP, JavaScript, C#, C++. So those are 6 categories. And then we have our popularity. Oops, misspelling there. Popularity. We'll give the first one 22.2%, Java 17.6%. And I don't know if these are real numbers they pulled. My guess is that they might have just been made up because I don't know if Python's really that much more popular than the other ones. Maybe specific to data science, because Python's very popular in data science right now because it has so many options. The only other program that's highly used and exclusively for data science is R. So Python's big, and Python also does a lot more. It's a full programming language, where R is primarily for data science. They didn't even put R in here. So we have Python, we have Java, we have our PHP, and you can see the different values they've given it, or different percentages. And I did add these up. It does not add up to 100%. It adds up to 71% or something like that. And then we're going to give colors. And we've chosen, these guys in the back brought in these colors. I'm not sure what these colors are. We'll find out in a minute, so it'll be exciting. But you can see they're using the actual color values you can pull off of a color wheel or something like that. You could have just as easily done blue, red, green if you're too lazy to pick the exact colors. And then let's go ahead and solve this and see what we got here. We're going to do something a little fancy just because we can. The first thing we're going to do is we're going to use a variable called explode. And you'll notice that there's 6 variables in here, so that matches our 6 different categories. And the first one we've done is 0.1 and then 0, 0, 0, 0, 0. 0.1, when we put this in here under the explode in the plot, it will actually push that square out. So it's a really cool feature to highlight certain information on a pie chart. And this is simply plt.py. And we're plotting popularity. There we go. And before we add in all the really cool settings for this, let's go ahead and run it. And you'll see we generate a nice flat pie. Not too exciting there. And then we'll go ahead and put in all the extras. I talked about explode, where we can explode one of the values out. So here's our explode equals explode. Labels is languages, because we want to know what the different colors mean. Here's our colors equals colors, our auto picture. And this is standard print format. So that's a Python setup on there. And that's just going to put the value on the pie slice. And then we're going to add shadow, because it just looks cooler with a shadow. Gives it a little 3D look. And we'll do a start angle of 140. Let's go ahead and run this and take a look and see what comes out of that. And look how that changes the whole setup. So here's our labels. There's our value we put on there. There's our slice that's pushed out. There's our shadow, a 3D effect. And then we started at 140. We could also rotate this. Let's just do this angle 90. And if we run it, you'll see the blue pie slices moved up a little bit. We could actually let's just take the whole starting triangle out and run. It'll default to 0. And this is what it looks like if it defaulted to 0. So depending on where you want the highlighted slice to appear, usually you want that to appear on the left because people read left to right. And so it draws a focus onto, in this case, Python and how great Python is. I'm a little biased. We're teaching a Python tutorial, so it should be understandable that we're looking at Python. And one last reference before we close. You can go over to the matplotlibary.pyplot setup, and if you go underneath the different functions on there, you can look this up on their website. You'll see a full list, and this is why it's so important to go through a tutorial like this, because this list is just so massive. I'm trying to figure out, like, here's our bar plot. There's a bar H. You can add barbs. There's a box plot we didn't cover. C labels, a totally different kind of, for your contour plot you can set up in there. If you go down here, we have our figures we used on there. We showed you the basics of how to do the figure. You'll see some closer references on those. There's a histogram down here, HIST. There's also the hist2d, makes a 2D histogram plot. H-lines, all of this, these are all the different commands that are underneath of here. And you can see it's pretty extensive. We've covered all the basic ones so that you now have a solid ground to look at these different options. So when you come to these functions, some of them are going to look a little off, or not off, will look unfamiliar. but you'll still have the availability to probably understand most of this and have a basic understanding of your matplot library.
What does a data scientist do? These are some of the activities: data acquisition, data preparation, data mining, data modeling, and then model maintenance. We will talk about each of these in a great detail, but at a very high level, the first step obviously is to get the raw data, which is known as data acquisition. It can be in all kinds of format and it could be multiple sources, but obviously that raw data cannot be used as it is for performing data mining activities or data modeling activities. So the data has to be cleansed and prepared for using in the data models or in the data mining activity. So that is the data preparation. Then we actually do the data mining, which can also include some exploratory activities. And then if we have to do stuff like machine learning, then you need to build a machine learning model and test the model, get insights out of it. And then if the model is fine, you deploy it, and then you need to maintain the model, because over a period of time it is possible that you need to tweak the model because of change in the process or change in the data and so on. So that all comes under the model maintenance. So let's take a deeper look at each of these activities. Let's start with data acquisition. So in the stage of data acquisition, basically the data scientist will collect raw data from all possible sources. So this could be typically an RDBMS, which is a relational database, or it can also be a non-RDBMS, or could be flat files or unstructured data and so on. So we need to bring all that data from different sources. If required, we need to do some kind of homogeneous formatting so that it all fits into in a looks, at least format, from a format perspective, it looks homogeneous. So that may be requiring some kind of transformation. Very often this is loaded into what is known as data warehouse. So this can also be sometimes referred to as ETL, or extract, transform, and load. So our data warehouse is like a common place where data from different sources is brought together so that people can perform data science activities like reporting or data mining or the statistical analysis and so on. So data from various sources is put in a centralized place, which is known as a data warehouse. So that is also known as ETL. And in order to do this, there can be data scientists can take help of some ETL tools. There are some existing tools that a data scientist can take help of, like for example DataStage or Talent or Informatica. These are pretty good tools for performing these ETL activities and getting the data. The next stage, now that you have the raw data into a data warehouse, you still probably are not in a position to straight away use this data for performing the data mining activities. So that is where data preparation comes into play, and there are multiple reasons for that. One of them could be the data is dirty, there are some missing values, and so on and so forth. So a lot of time is actually spent in this particular stage. So a data scientist spends a lot of time, almost 60 to 70% of the time, in this part of the project or the process, which is data preparation. So there are, again, within this there can be multiple sub activities, starting from, let's say, data cleaning. You will probably have missing values. The data, there is some columns, the values are missing, or the values are incorrect, there are null values, and so on and so forth. So that is basically the data cleaning part of it. Then you need to perform certain transformations, like for example normalizing the data and so on, right? So, or you could probably have to modify categorical values into numerical values and so on and so forth. So these are transformational activities. Then we may have to handle outliers. So the data could be such that there are a few values which are way beyond the normal behavior of the data. For whatever reason, either people have keyed in wrong values, or for some reason some of the values are completely out of range. So those are known as outliers. So there are certain ways of handling these outliers and detecting and handling these outliers. So this is a part of what is known as exploratory analysis. So you quickly explore the data to find out and you can use visual tools like plots and identify what are the outliers and see how we can get rid of the outliers and so on. Then the next part could be data integrity. Data integrity is to validate, for example, if there are some primary keys, that all the primary keys are populated. There are some foreign keys, then at least most of the foreign keys should be populated, and otherwise when we are trying to query the data, you may get wrong values and so on. So that is the data integrity part of it. And then we have what is known as data reduction. Sometimes we may have duplicate values, we may have columns that may be duplicated because they are coming from different sources, the same values are there, and so on. So a lot of this can be done using what is known as data reduction, and thereby you can reduce the size of the data drastically, because very often this could be redundant data which can be removed and so on. So let's take a look at what are the various techniques that are used for data cleaning. So we need to ensure that the data is valid and it is consistent and uniform and accurate. So these are the various parameters that we need to ensure as a part of the data cleaning process. Now, what are the techniques that are used for data cleaning? So we will see what each of these are in this particular case. And so what is the data set that we have? We have data about a bank and its customer details. So let's take an example and see how we go about cleaning the data. And in this particular example, we are assuming we are using Python. So let's assume we loaded this data, which is the raw file.csv. This is how the customer data looks like. And we will see, for example, if we take a closer look at the geography column, we will see that there are quite a few blank spaces. So how do we go about when we have some blank spaces? Or if it is a string value, then we put an empty string here, or we just use a space or empty string. If they are numerical values, then we need to come up with a strategy. For example, we put the mean value. So wherever it is missing, we find the mean for that particular column. So in this case, let's assume we have credit score and we see that quite a few of these values are missing. So what do we do here? We find the mean for this column for all the existing values, and we found that the mean is equal to 638.6. So we kind of write a piece of code to replace wherever there are blank values. NaN is basically like null, and we just go ahead and say fill it with the mean value. So this is the piece of code we are writing to fill it. So all the blanks or all the null values get replaced with the mean value. Now, one of the reasons for doing this is that very often if you have some such situation, many of your statistical functions may not even work. So that's the reason you need to fill up these values, or either get rid of these records or fill up these values with something meaningful. So this is one mechanism, which is basically using a mean. There are a few others. As we move forward, we can see what are the other ways. For example, we can also say that any missing value in a particular row, if even one column the value is missing, you just drop that particular row, or delete all rows where even a single column has missing values. So that is one way of dealing. Now the problem here can be that if a lot of data has, let's say, one or two columns missing, and we drop many such rows, then overall you may lose out on, let's say, 60% of the data has some value or the other missing, 60% of the rows. Then it may not be a good idea to delete all the rows like in that manner, because then you're losing pretty much 60% of your data. Therefore your analysis won't be accurate. But if it is only 5 or 10%, then this will work. Another way is only to drop values where, or rather drop rows where all the columns are empty, which makes sense, because that means that record is of really no use because it has no information in it. So there can be some situations like that. So we can provide a condition saying that drop the records where all the columns are blank or not applicable. We can also specify some kind of a threshold. Let's say you have 10 or 20 columns in a row. You can specify that maybe 5 columns are blank or null, then you drop that record. So again, we need to take care that such a condition, such a situation, the amount of data that has been removed or excluded is not large. If it is like maybe 5%, maximum 10%, then it's okay. But by doing this, if you're losing out on a large chunk of data, then it may not be a good idea. You need to come up with something better. What else we need to do next is, so the data preparation part is done. So now we get into the data mining part. So what exactly we do in data mining? primarily we come up with ways to take meaningful decisions. So data mining will give us insights into the data, what is existing there, and then we can do additional stuff like maybe machine learning and so on to perform advanced analytics and so on. So one of the first steps we do is what is known as data discovery, and which is basically like exploratory analysis. So we can use tools like Tableau for doing some of this. So let's just take a quick look at how we go about that. So Tableau is excellent data mining, or actually more of a reporting or a BI tool, and you can download a trial version of Tableau at tableau.com, or there is also Tableau Public, which is free and you can actually use and play around. However, if you want to use it for enterprise purpose, then it is commercial software, so you need to purchase license, and you can then run some of the data mining activities. Say your data source, your data is in some Excel sheet, so you can select the source as Microsoft Excel or any other format, and the data will be brought into the Tableau environment, and then it will show you what is known as dimensions and measures. So dimensions are all the descriptive columns, and Tableau is intelligent enough to actually identify these dimensions and measures. So measures are the numerical values. So as you can see here, customer ID, gender, geography, these are all dimensions, non-numerical values, whereas age, balance, credit score and so on are numeric values, so they come under measures. So you got your data into Tableau, and then you want to, let's say, build a small model, and you want to, let's say, solve a particular problem. So what is the problem statement? All right, let's say we want to analyze why customers are leaving the bank, which is known as exit, and we want to analyze and see what are some of the factors for exiting the bank, and we want to, let's assume, consider these three of them, like let's say gender, credit card and geography, these as a criteria, and analyze if these are in any way impacting or have some bearing on the customer exiting or the customer exit behavior. Okay, so let's use Tableau, and very quickly we will be able to find out how these parameters are affecting. All right, so let's see. So this is our customer data. So from our Excel sheet, we have data set about, let's say 10,000 rows, and we want to find out what is the criteria. Let's start with gender. Let's say we want to first use gender as a criteria. So Tableau really offers an easy drag and drop kind of a mechanism, so that makes it really easy to perform this kind of analysis. So what we need to do is exited says whether the customer has exited or not, so it has a value of 0 and 1, and then of course you have gender and so on. So we will take these two and simply drag and drop. Okay, so exited, and then we will put gender. And if we drag and drop into the analysis side of Tableau, all right, so here what we are doing is we are showing male female as two different columns here, and 0 for people who did not exit and 1 for people who exited, and that is color coded. So the blue color means people who did not exit, and this yellow color means people who did exit. All right, so now if we pull the data here, create like bar graphs, this is how it would look. So what is yellow? Let's go back. So yellow is who exited, and for the male, only 16.45% have exited. And we can also draw a reference line that will help us, or even provide aliases. So these are a lot of fancy stuff that is provided by Tableau. You can create aliases, and so that it looks good rather than basic labels. And you can also add a reference line. So if you add a reference line, something like this, from here we can make out that on an average, female customers exit more than the male customers, right? So that is what we are seeing here on an average. So we have analyzed based on gender. We do see that there is some difference in the male and female behavior. Now let's take the next criteria, which is the credit card. So let's see if having a credit card has any impact on the customer exit behavior. So just like before, we drag and drop the credit card has credit card column. If we drag and drop here, and then we will see that there is pretty much no difference between people having credit card and not having credit card. 20.81% of people who have no credit card have exited, and similarly 20.18% of people who have credit card have also exited. So the credit card is not having much of an impact. That's what this piece of analysis shows. Last, we will basically go and check how the geography is impacting. So once again, we can drag and drop geography column onto this side. And if we see here, there are geographies like, I think there are about 3 geographies like France, Germany, and Spain, and we see that there is some kind of impact with the geography as well. Okay, so what we derive from this is that the credit card is really, we can ignore the credit card variable or feature from our analysis because that doesn't have any impact, but gender and geography we can keep and do further analysis. Okay, all right. So what are some of the advantages of data mining? Bit more detailed analysis can help us in predicting the future trends, and it also helps in identifying customer behavior patterns. Okay, so you can take informed decisions because the data is telling you or providing you with some insights, and then you take a decision based on that. If there is any fraudulent activity, data mining will help in quickly identifying such a fraud as well. And of course, it will also help us in identifying the right algorithm for performing more advanced data mining activities like machine learning and so on. All right, so the next activity, now that we have the data, we have prepared the data and performed some data mining activity, the next step is model building. Let's take a look at model building. So what is model building? If we want to perform a more detailed data mining activity, like maybe perform some machine learning, then you need to build a model. And how do you build a model? First thing is you need to select which algorithm you want to use to solve the problem on hand, and also what kind of data that is available, and so on and so forth. So you need to make a choice of the algorithm, and based on that you go ahead and create a model, train the model, and so on.
We look at data science components. There's the mathematics, statistics, domain expertise, data engineering, data visualization, and machine learning. When we sum this up in data science, really this point in all of this you want to focus on first is domain expertise. Now, when you're taking your classes, obviously you want to go through the mathematics, the statistics, the data engineering, the data visualization, the machine learning, and learning all those tools. But it really, in the job field, the domain expertise comes in. Because if you're really good with business and you go into business with these tools, then you're able to ask the right questions and deal with it. When we talk about the tools in data science and where they sit, there is a data analysis. Data analysis focuses more on statistics and mathematics, where the data science side focuses more on the machine learning, data visualization. And then there's database management, which really focuses on the data engineering part of it and how to manage that data and the data flow. And you can see all these components come together, and then they form the data science. And we talk about tools in data science. We have SAS, we have MATLAB, we have SQL, you have your Apache Spark, your R, Tableau, Python. Right now in the programming languages, Python is probably the most widely used, with R coming in a close second. The reason for that is these are both open source and anybody can use them. When we look at SAS and Tableau, those are 2 packages that are paid for, which have a lot of automation behind them. So a lot of the larger companies will pay for those packages because they help work out a lot of the back-end stuff before you even need to use them. And of course we have Apache Spark. You almost have to know Apache Spark and the growing data lakes today. That's your big data. How do you distribute this if you're going to process it over a large amount of data? When we look at data science applications, there's internet search, very common. You enter your Google thing and it uses the data science algorithms to figure out what to return. Voice assistants, analyzing the voice coming in and connecting it with whatever patterns they need to activate so you can ask it to turn your lights on in the living room. Healthcare, biggest field growing right now. How do we analyze health data from a smartwatch and figure out how to know when a disease is being spread across the world? Healthcare, how do we identify cancer versus non-cancer so we know who to prioritize and get them in for surgery where other people might not need that immediate care? And even identifying problems somebody might have with their health long before they even happen. What a neat thing to do instead of waiting till you have a heart attack to know months ahead of time that you're having heart conditions. Logistics. How do we get from point A to point B? If you ever look at some of the major distributors, they pre-ship things based on what they guess people are going to need. This way you get your stuff right in the mailbox the day after you order it. E-commerce. Huge in there because you have to know what kind of marketing we're going to put out. Who are we selling to? What's our target audience? Robotics. One of the funner ones when you're coming up into the future is how do we automate the different tasks we have, from self-driving cars to manufacturing lines to maybe even a self-robotic chef in the kitchen. So when we talk about solving problems with data science, we have to ask possible questions and the desired algorithms. And these really are kind of an overview of some of the terminology you'll want to know in data science. So when we talk about that, how much or how many? We're talking about regression. Regression basically means a number. If you've ever seen stock charts, you see the guess at what the next sales price is or buy price is. That's all on your regression side. Is it A or B? Classification. Is that a dog or a cat that my photo took a picture of? How is this organized? Clustering. This is where we take things that look alike and put them together so that we can then make predictions on it. How different is this? Just like you have clustering, you have the opposite, anomaly detection. How do we find things that don't fit in? What are the outliers? What are things we might need to look at that aren't in our model? And what to do next? Reinforced learning. This is probably the newest market, is how do we set something up where as the data comes in, it learns from the new data as to what the next action is going to take. Most of these are combined. So when we talk about regression, classification, clustering, anomaly detection, reinforced learning, a lot of times when you put your model together, you might have multiple parts of this. We might look at the clustering of data and then feed it into a classification. Is this a bad loan to make at the bank, or is this a good loan to give? And from there we might start looking at, when we start clustering these things as good and bad and what kind of setup is, we then might run it through a regression model to say, hey, what is the dollar amount this person should be allowed to take a loan out? And you can see that all of these start coming in, and then a lot of the models, reinforced learning, we talk about like bank loans and things like that, once a year they have to rerun those algorithms. And so that's like a human run reinforced learning. Now we're starting to automate that so that as the data comes in real time, the models start updating themselves. They start figuring out a way to solve new problems as they occur. And of course in robotics, reinforced learning is one of the biggest growing fields. Algorithms used in data science. Linear regression. Logistic regression. When you're looking at both of these, think numbers. We're talking regression models. And so linear regression figures out the best line through the data. Maybe it's looking for a curved line. Logistic regression starts looking at data on a continuum so that it goes to an exponential. You have a spot where it might be one or the other, and then you know what it is as it goes to one side or the other. Decision tree. Wonderful tool. If you they used to call it a hack, now it's becoming mainstream, to look at the back end, what made the decision. So it's really easy to trace back to how you arrived at the decision. Decision trees are kind of nice that way. Nearest neighbors. K nearest neighbors is your clustering. K means clustering. Hierarchical clustering. So hierarchical starts dividing them and builds a hierarchy where the K means and the K nearest neighbor look for things that kind of connect each other. How close are they in data format? DB scan, another form of clustering your data. Principal component analysis. So we start breaking up and looking at the different components in our data coming in. These are all algorithms used in data science, and there are more. These are kind of the mainline ones. And each one of these has many settings which you can play with to build a better model to predict your data and where you want it to go. Let's go ahead and take a hands-on demo and just see what does this look like. Now I'm going to go ahead and use the Anaconda Navigator and the which is your Jupyter Notebook, which will then open up in Google Chrome. This is one of the IDEs or ways of editing Python code. I like this one because it, one, protects my computer and creates its own kind of container, and two, it's got a really nice visual demo for doing Python. Certainly you can use a number of other different tools like PyCharm is another real popular one. You can actually access PyCharm code through the Anaconda Navigator now, and there's a lot of other tools on there that each have their benefit. And we come into our Jupyter Notebook. I go ahead and create a new Python. I've already done that. And we'll start with a logistics regression model, just so you can see what this looks like in code. We'll actually do two of these as we go through this, and take a look and see what that code looks like in Python. Now, the first thing we want to go ahead and do is load up all our parts modules that we need in our Python code. I'll go ahead and run that, and you'll see here I'm going to ignore warnings, because some of the stuff we're doing, we're just looking at it, and as you go from one version of Python to one version of whatever the scikit, or in this case the SC package, you'll see some warnings come up. They're not really important right now. And then we're going to go ahead and use the German credit data CSV. And so when I run this, this is all loaded up. Now let's go ahead and just open up this CSV file so you can see what that looks like. And here it is. Here's our German credit data file. We'll go ahead and just open that up with, let's do WordPad is fine because it's a Word document. And when we open that up, you can see right here it's just a bunch of comma separated values. We have across the top, it actually has columns on here, so our first row is a bunch of columns. And then of course we look down here. Oops, I just moved stuff around, but that's okay, I'm not going to save it. And you can see the values, AL1, AL4, whatever that means, or A14 I guess, and then some sorted numbers on here. And we'll take a closer look when we get into the program and looking at the data. For right now we've loaded that under credit DF. And at this point, I want to just kind of take a detour back to the life cycle of data science so we can see how that fits in there. And so we've already done our data discovery. We have a little data prep, but the data is pretty clean. It already comes in preset on there. We might do a little data preparation in here. We're going to start looking at exploring the data analysis and building a data model and then interpreting the results. So really we're focusing on the last three steps of this. The data discovery would be start asking questions of what do we want in there? Is this going to be a good loan, a bad loan? What do we want to get out of this data? Where are we going with it? That would be part of the data discovery. And a lot of times that might be a meeting you have with the management in the office or whatever. And then data preparation is, of course, cleaning the data up, making sure you know where the source came from, all those kind of fun things that go into making sure you have good data coming in.
We're going to cover mathematics for machine learning. So today's agenda is going to cover data and its types. Then we're going to dive into linear algebra and its concepts, calculus, statistics for machine learning, probability for machine learning, hands-on demos. And of course, thrown in there in the middle is going to be your matrices and a few other things to go along with all this. Data and its types. Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers, and then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So when we talk about types of data, in our types of data, we have a qualitative, categorical. You think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range. If you have 10,000 to 20,000, number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually, a lot of times discrete could be put into true-false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's where we're talking about a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle, AB, is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart, or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. Very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these, because these are such primary. This is what we're here to talk about, is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have two variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept, which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. I kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is A row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, smaller case a for the top row. Or, I mean, you can see where they can go all kinds of different directions as far as the value. You just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have two matrices of 2 by 2, and you just add each individual number in that matrix, and then when you get to the bottom, you have, in this case, the solution is 12, 10 plus 2 is 12, 5 plus 3 is 8, and so on. And the same thing with subtraction. Now again, you're counting matrices, you want to check your dimensions of the matrix. The shape, you'll see shape come up a lot in programming. So when we're talking about dimensions, we're talking about the shape. If the two shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at 2 variable. So this is a 2 variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5, and it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of 2 matrices, okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one. And it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to eigenvectors vectors and eigenvalues values. Eigenvectors vectors, the vectors that don't change their span while transformation, and eigenvalues, the scalar values that are associated to the vectors. Conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your eigenvector. 2 is the eigenvalue. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your eigenvalue. And you can see here, vector after line transition, we have 3a. A is the eigenvector, 3 is the eigenvalue. So A doesn't change. That's whatever we started with. That's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the eigenvalues. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook, and we'll create a new notebook called linear algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. Given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create 2 different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our 2 arrays, 10, 15, 29. And I went ahead and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as a plus b, I can also do a plus b dot t, and you're going to see that that will come out the same, the 30, 24, whether I transpose a and b or transpose them both at the end. And likewise, we can very easily subtract two vectors. I can go a minus b, and we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down scalar so you can remember that. What we're talking about here is I have this array here, u, and if I go a times u, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a two-dimensional vectors. It is the equivalent of to matrix multiplication. And remember, we were talking about matrix multiplication, where it is the, well, let's walk through it. We'll go ahead and start by defining two NumPy arrays. We'll have 10, 20, 25, 6, or our u and our v. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of u comma v. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here. There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma n means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is A plus B, and you should already guess, because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do A minus B and do our matrix subtraction. And we look at this, we have what? 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is, of course, 10. 10 minus 8 is 2. 4 minus 46 is minus 42, and so forth. So same as a subtraction as before, we just call it matrix subtraction. It's identical. Now, if you remember up here, we had scalar addition, where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply, if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a NumPy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication, and you can mix and match. When you get into really complicated back-end stuff, this becomes more common because you've got layers upon layers of data. And so you'll end up with a matrix and a set of vector matrices do you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the scikit looking at sklearn, where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times, you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the scikit. And if we can do, up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this where we have the 2 matrices, you can see we have a very complicated array that, of course, comes out on there for our dot. And just to reiterate it, we have our transpose matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers, and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you can be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1, depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here, is that you create this preset matrix and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind, 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then of course it equals the dot, A inverse of A, with an identity shape of, A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we go ahead and have here's our array. We'll go ahead and run this, and you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down, 2, 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up, or at least remember where to look it up. We took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic. Traffic opens up and I accelerate again up to the speed limit, and maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating, and if I hit the brakes, it'd go the other way. So the rate of change of speed with respect of time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to zero in order to approximate the acceleration. So the idea is that instead of, if you ever took a basic calculus class, they would draw bars down here and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. It looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, the differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from C to D and A to B of f of x of y dx dy equals the sum of A to B, sum of C to D of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals a change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? Speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I mean, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. On the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is, and this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Sidekick and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff, because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current X. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. We're just saying if it's if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's so we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot in with the sklearn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits in built-in code. And so from, we'll just do, it's actually docs.scipy.org, and we're looking at the scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught. There's your start value. So your function, your start value, there's all kinds of things that come in here that you can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. what this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly if you're working in a domain that deals with viruses and T cells and how does, where does that come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you gotta be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup or our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. Let's say we're studying economics of an area. We know pretty much that based on their culture and where they came from, they might need to be separated. And so, and when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call her expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups they're in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group, or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say this is what it is, then everybody assumes that's what it is for everybody. And so you got to be very careful of that, and it's a very unethical thing to kind of do. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are so many different terms in statistics to break it up. So we're talking about a particular setup. So we're talking about descriptive and inferential statistics. The base of the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we're going to take that from the small population to a large population. So if you're working with a drug company, you might look at the data and say, these people were helped by this drug. They did 80% better as far as their health, or 80% better survival rate than the people who did not have the drug. So we can infer that that drug will work in the greater populace and will help people. So that's where you get your inferential. So we are predicting how it's going to affect the greater population. So descriptive statistics. It is used to describe the basic features of data and form the basis of quantitative analysis of data. So we have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your interquartile range, your variance, and your standard deviation. And we're going to look at all these a little deeper here in a second. But one of them you can think of is how the data differences, what's the max, min range, all that stuff is your spread. And anything that's just a single number is usually your central tendencies, measure of central tendencies. So when we talk about the mean, it is the average of the set of values considered. What is the average outcome of whatever's going on? And then your median separates the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it so that the average is much higher than if you took those outliers out, where the median would, by separating the high from the low, might give you a much lower number. You might look at it and say, oh, that's odd. Why is the average so much higher than the median? Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. You might find that the most common income, like in the U.S., was $1,240,000 a year, where the average was closer to $80,000. And it's like, wow, what a difference. Well, there's some people who have a lot of money, and so that skews that way up. So the average person is not making that kind of money. And then you look at the median income, and you're like, well, the median income is a little bit closer to the average. So it does create a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. And we look at the measure of central tendencies. The mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, if we have 0 through 10, and we take half the numbers and put them on one side of the line, half the numbers on the other side of the line, we end up with 5 in the middle. And then the mode. What mark was scored by most of the students in a test? In a simple case where most people scored like an 82% and got certain problems wrong, easy to figure out. Not so easy when you have different areas where like you have like the, let's go back to economy. A little bit more difficult to calculate if you have a large group that makes 30,000 and a slightly bigger group that makes 26,000. So what do you put down for the mode? Certainly there's a number of ways to calculate that, and there's actually different variations depending on what you're doing. So now we're looking at a measure of spread, range. What's the difference between the highest and the lowest value? First thing you want to look at, it's we had everybody in the test scored between 60 and 100%. Somebody got 100%, or maybe 60 to 90%. It was so hard that a lot of people could not get 100%. Then you have your interquartile range. Quartiles divide a rank-ordered data set into 4 equal parts. Very common thing to do as part of all the basic packages, whether you're working in data frames with pandas, whether you're working in Scala, whether you're working in R. You'll see this come up where they have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the standard deviation. It is the measure of the variance or the dispersion of a set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed, and then based on the error, I might graph the standard deviation and the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread. Marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is. And then there's the first quarter, the second quarter, and the third quarter based on splitting it apart by those values. And to understand the variance and standard deviation, we first need to find out the mean. So here's our calculating the average there. We end up at approximately 66 for the average. And then we look at that and the variance. Once we know the means, we can do equals the marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have like if you're putting all this stuff together, you end up with an error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. And if you were looking at a predictable model, you would be looking at the deviation based on the error. How much error does it have? And that's, again, really important to know. If your prediction is predicting something, what's the chance of it being way off or just a little bit off? Now that we've looked at the tools, as far as some of the basics for doing your statistics and what we're talking about, let's go ahead and pull up a little demo and show you what that looks like in Python code, so you can get some little hands-on here. For that, let's go back into our Jupyter Notebook in Python. Now, almost all of this you can do in NumPy. Last time we worked in NumPy. This time we're going to go ahead and use pandas. And if you remember from pandas on here, this is basically a data frame, rows, columns. Let's just go ahead and do a print df.head and run that. And you can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all those hand calculations and add everything together and divide by the total, we can do something very simple on this, like use the command mean in pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. We want to find the means of that column. And we go ahead and print this out, and you can see that the average income on here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And the median is very similar, except it actually is just median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And then the median, oops, let's put a median here, df salary, that way it displays a little better. We can see the median is 54,000, so the halfway mark is significantly below the average. Why? Because we have somebody in here who makes $189,000. Darn you, Rosie, for throwing off our numbers. But that's something you'd want to notice. This is the difference between these is huge, and so is what is the meaning behind that when you're studying a populace and looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make in this little tiny sample. And so we'll go ahead and do the mode. And you can see here with the mode, it's at 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000. So half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min will pull up your minimum, and then dot max pulls up the maximum. Pretty straightforward on as far as translating it and knowing what what your lowest value and what your highest value is here, which you'll use to generate like a spread later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute the mode. Although the standard one's pretty good. We can of course do the range, which is your max minus your min. So now we have a range of 149,000 between the upper end and the lower end. And you might want to be looking up the individual values on all of these. But it turns out there is a describe feature in pandas. And so in pandas, we can actually do df salary describe. And if we do this, you can see we have that there's 7 setups. Here's our mean, our standard deviation, which we didn't compute yet, which would just be a .std. And you got to be a little careful because when it computes it, it looks for axes and things like that. We have our minimum value, and here's our quartiles, our maximum value, and then of course the name salary. So these are the basic statistics. You can pull them up and just describe. This is a dictionary, so I could actually do something like in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically. But just in case, I always put it in there. Import matplot library, pyplot as PLT. That's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. Maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary df salary, salary.plot history title, salary distribution, color gray, plot AXV line, salary the mean value. So we're going to take the mean value, color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here we are taking on our plot. So here's the data. Here's our data frame printed out so you can see it with the salaries. And we're looking at the salary distribution. And just look at this, the way the salary is distributed. You have our In this case, we did, let's see, we had red for the median. We have violet for our average or mean. And you can just see how it really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average, and here's the median. And so as you look at this, you can say, wow, based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, what the average salary is. So some of the things you want to take away in addition to this is that it's very easy to plot an AX, V line. These are these up and down lines for your markers. And as you display the data, I mean, you can add all kinds of things to this and get really complicated. Keeping it simple is pretty straightforward. I look at this and I can see we have a major outlier out here. We can definitely do a histogram and stuff like that. But, picture's worth 1,000 words. What you really want to make sure you take away is that we can do a basic describe, which pulls all this information out, and we can print any of the individual information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also do describe mean. So if you're doing a lot of statistics, being able to, it doesn't have the print on there, so it's only going to print the last one, which happens to be the mean. You can very easily reference any one of these. And then you can also, if you're doing something a little bit more complicated and you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture of movie ratings, and if we took this group of people and said, hey, how many people like the movie, dislike it, can't say, and then you ask just a random person who comes out of the movie who hasn't been in this study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or a 10 or 11% chance of can't say. So that's real basics of what we're talking about, is you're going to infer that the next person is going to follow these statistics. So let's look at point estimation. It is a process of finding an approximate value for a population's parameter, like mean or average, from random samples of the population. Let's take an example of testing vaccines for COVID-19. Vaccines and flu bugs, all of that, it's a pretty big thing of how do you test these out and make sure they're going to work on the populace. A group of people are chosen from the population. Medical trials are performed. Results are generalized for the whole population. So here's our small group up here where we've selected them. We run medical trials on them, and then the results work for the population. Nice diagram with the arrows going back and forth and the very scary COVID virus in the middle of one. And let's take a look at the applications of inferential statistics. Very central is what they call hypotheses testing, and the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis, assumption, by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis. We execute the test, and we make a decision. And so when you're talking about hypothesis, you're usually trying to disprove it. If you can't disprove it and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who were given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people: Nick, Rob, Imlia, and Summer. Now Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e. whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e. his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of Rob not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do work. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very high probability when on day 12 he still hasn't gotten the job cleaning the room. So we come up to our important terminologies. We have null hypothesis, a general statement that states that there is no relationship between 2 measured phenomena or no association among the groups. Alternative hypothesis. Contrary to the null hypothesis, it states whenever something is happening, a new theory is preferred instead of an old one. And so the 2 hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it, it's about proving that the things have no correlation. Null hypothesis says these 2 have 0 relation to each other. Where the alternative hypothesis says, hey, we found a relation, this is what it is. We have p-value. The p-value is a probability of finding the observed or more extreme results when the null hypothesis of a study question is true. And the t-value. It is simply the calculated difference represented in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you can look at the t-value as being specific to the test you're doing, where the p-value is derived from your t-value, and you're looking for what they call the 5% or the 0.05, showing that it has a high correlation. So digging in deeper, let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. And this is a good one because the null value here isn't that you don't have any drug. The null value here is that it's better than the existing drug. The new drug doesn't lower the blood pressure more than the existing drug. Now, if we get that, that says our null hypothesis is correct. There is no correlation, and the new drug is not doing its job. The alternative hypothesis, the new drug does significantly lower the blood pressure more than the existing drug. Yay, we got a new drug out there. And that's our alternative hypothesis, or the H1 or HA. And we look at the p-value, results from the evidence like medical trials showing positive results which will reject the null hypothesis. And again, they're looking for a 0.05 or 5%. And the t-value, comparing all the positive test results and finding means of different samples in order to test hypothesis. So this is specific to the test. What percentage of increase did they have? And this leads us to the confidence intervals. A confidence interval is a range of values we are sure our true values of observations lie in. Let's say you asked a dog owner around you and asked them, how many cans of food do you buy for your per year for your dog? Through calculations, you got to know that on an average, around 95% of the people bought around 200 to 300 cans of food. Hence, we can say that we have a confidence interval of 2-300, where 95% of our values lie in that data spread. And the graph really helps a lot, so you can start seeing what you're looking at here, where you have the 95%, you have your peak. In this case, it's a normal distribution, so you have the nice bell curve equal on both sides. It's not asymmetrical. And 95% of all the values lie within a very small range, and then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability is a measure of the likelihood of an event to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of its occurrence. So any event cannot be predicted with total certainty. It can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather prediction, stock prediction. If you've studied physics and chaos theory, even the location of the chair you're sitting on has a probability that it might move 3 feet over. Granted, that probability is 1 in I think we calculated it as under 1 in trillions upon trillions. So it's the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of a random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each. There's how often you're going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this as one of the cases is rolling 2 dice and gambling. There's also a binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case. And let's consider the game of football between 2 clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series. So we look at the total games, and we're looking at 5 different games or matches. Let's say that the winning chance for Barcelona is 75% or 0.75. That means at each game, they have a 75% chance that they're going to win that game. And losing chances are 25% or 0.25. Clearly 0.75 plus 0.25 equals 1. So that accounts for 100% of the game. Probability for getting K wins in N matches is calculated. And we're talking so if you have 5 games and you want to know if I play, how many wins in those 5 games should I get? What's the percentage on those? And the probability for getting K wins in N matches is calculated by Px equals K equals NCK P to the K, Q to the N minus K. Here, P is the probability of success and Q is the probability of failure. And so we can do total games of N equals 5, where K equals 0, 1, 2, 3, 4, 5. P, which is the chance of winning, is 0.75. Q, the chance of losing, equals 1 minus P, which equals 1 minus 0.075, which equals 0.25. The probability that Barcelona will lose all of the matches can then just plug in the numbers. and we end up with a 0.0009765,625. So very small chance they're going to lose all their matches. And we can plug in the value for 2 matches. Probability that Barcelona will win at least 2 matches is 0.0878. And of course we can go on to the probability that Barcelona will win 3 matches, the 0.26, and of course 4 matches, and so on. And it's always nice to take this information and let's find the cumulative discrete probabilities for each of the outcomes. Where Barcelona has won 3 or more matches, x equals 3, x equals 4, x equals 5. And we end up with the p equals 0.264 plus 0.395 plus 237, which equals 0.89. In reality, the probability of Barcelona winning the series is much higher than 0.75. And it's always nice to put out a nice graph so you can actually see the probability and how that pans out with our binomial case. Continuing in our important terminology, location. The location of the center of the graph depends on the mean value. And this is some very important things. So much of the data we look at, and when you start looking at probabilities, almost always has a normalized look, like the graph in the middle. But you do have left skewed, where the data is skewed off to the left, and you have more stuff happening off to the left, and you have right skewed data. And so when this comes up and these probabilities come up where they're skewed, it's really important to take a closer look at that. Mostly you end up with a normalized set of data, but you got to also be aware that sometimes it's a skewed data. And then the height. Height of the slope inversely depends upon the standard deviation. So you can see down here the standard deviation is really large. It kind of squishes it out. And if the standard deviation is small, then most of your data is going to hit right there in the middle. You're going to have a nice peak. And so being aware of this, that you might have a probability that fits certain data, but it has a lot of outliers. So if you have a really high standard deviation, if you're doing stock market analysis, this means your predictions are probably not going to make you much money. Where if you have a very small deviation, you might be right on target and set to become a millionaire. Which leads us to the z-score. Z-score tells you how far from the mean a data point is. It is measured in terms of standard deviations from the mean. Around 68% of the results are found between 1 standard deviation. Around 95% of the results are found between 2 standard deviations. And you read the symbols. Of course, they love to throw some Greek letters in there. We have mu minus 2 sigma. Mu is just a quick way. It's a kind of funky U. It just means the mean. And then the sigma is the standard deviation, and that's the O with the little arrow off to the right, or the little waggly tail going up, the O with the line on it. So mu minus 2 sigma is your 95% of the results are found between 2 standard deviations. Central limit theorem. This goes back to the skew. If you remember, we were looking at the skew values on this previous slide. Have left skewed, normalized, and right skewed. When we're talking about it being skewed or not skewed, the distribution of the sample means will be approximately normally distributed, evenly distributed, not skewed, if you take large random samples from the population with the mean, mu, and the standard deviation, sigma, with replacement. And you can see here, of course, we have our mu minus 2 sigma and the spread down here, the mean, the median, and the mode. And so when you're talking about very large populations, these numbers should come together and you shouldn't have a skewed value. If you do, that's a flag that something's wrong. That's why this is so important to be aware of what's going on with your data, where your samples are coming from, and the math behind it. And if you're going to do all this, we got to jump into conditional probability. The conditional probability of an event A is the probability that the event will occur given the knowledge that an event B has already occurred. And you'll see this as Bayes' theorem, B-A-Y-E-S, Bayes. And this is read, I mean, you have these funky looking little P brackets, A, B. This is the probability of A being true while B is already true. And you have the probability of B being true when A is already true, so P, B of A. The probability of A being true divided by the probability of B being true. And we talk about Bayes' theorem, which occurred back in the 1800s when he discovered this. This is such an important formula, and it's not, if you actually do the math, you could just kind of do xy equals jk, and then you divide them out, and you're going to see the same math, but it works with probabilities, which makes it really nice. And so if you have you might have 8 or 9 different studies going on in different areas. Different people have done the studies, they brought them together. If we look at today's COVID virus, the virus spread, certainly the studies done in China versus the studies the way they're done in the US, that data is different in each of those studies. But if you can find a place where it overlaps, where they're studying the same thing together, you can then compute the changes that you need to make in one study to make them equal. And this is also true if you have a study of one group and you want to find out more about it. So this formula is very powerful, and it really has to do with the data collection part of the math and data science, and understanding where your data is coming from and how you're going to combine different studies in different groups. And we'll go ahead and go into a use case. Let's find out the chance of a person getting lung disease due to smoking. And this is kind of interesting the way they word this. Let's say that according to medical report provided by the hospital, states that around 10% of all patients they treated suffered lung disease. So we have kind of a generic medical report. They further found out by a survey that 15% of the patients that visit them smoke. So we have 10% that are lung disease, and 15% of the patients smoke. And finally, 5% of the people continued smoke even when they had lung disease. Not the brightest choice, but it is an addiction, so it can be really difficult to kick. And so we can look at the probability of A. Prior probability of 10% people having lung disease. And then probability B. Probability that a patient smokes is 15%. And the probability of B, if B then A, the probability of a patient smokes even though they have lung disease is 5%. And probability of A is B, probability that the patient will have lung disease if they smoke. And then when you put the formulas together, you get a nice solution here. You get the probability of A of B, probability that the patient will have lung disease if they smoke. And you can just plug the numbers right in, and we get a 3.33% chance. Hence, there is a 3.33% chance that a person who smokes will get a lung disease. So we're going to pull up a little Python code. Always my favorite. Roll up the sleeves. Keep in mind, we're going to be doing this kind of like the back end way, so that you can see what's going on. And then later on, we're going to create, we'll get into another demo which shows you some of the tools that are already pre-built for this. Let's start by creating a set. So we're going to create a set with curly braces. This means that our set has only unique values. So you have a list, you have your tuples, which can never change, and then you have, in this case, the set. So 4, 7, you can't create a 4, 7, comma 4. It'll delete the 4 out. So it's only unique values. And if you use dictionaries, quick reminder, this should look familiar because it is a dictionary where you have a value, and that value is assigned to, or that key is assigned to a value. So you could have a key value set up as a dictionary. So it's like a dictionary without the value. It's just the keys, and they all have to be unique. And if we run this, we have a set of 4, 7. We can also take a list, a regular setup, and I'm going to go ahead and just throw in another number in here, 4, and run it. And you can see here, if I take my list 1, 2, 3, 4, 4, and I convert it to a set, and here it is, my set from list equals set, my list. The result is 1, 2, 3, 4. So it just deletes that last 4 right out of there. And with the sets, you can also go in there and print, here is my set, 3 is in the set, and then if you do 3 in my set, that's going to be a logic function. And 1 in my set, 6 is not in the set, and so forth. If we run this, we get 3 is in the set true, 1 is in the set false, because 3, 5, 7 is another 1. 6 is in the set, 6 is not in the set, so not in my set. You can also use this with a list. We could have just used 3, 5, 7, and it would have the same response on there, is 3 in. Usually you do if 3 is in, but 3 in my set still works on just a regular list. And we'll go ahead and do a little iteration. We're going to do kind of the dice one. Remember 1, 2, 3, 4, 5, 6. And so we're going to bring in an iteration tool and import product as product. And I'll show you what that means in just a second. So we have our 2 dice. We have dice A, and it's going to be a set of values. You can only have 1 value for each one. That's why they put it in a set. And if you remember from range, it is up to 7. So this is going to be 1, 2, 3, 4, 5, 6. It will not include the 7. And the same thing for our dice B. And then what we're going to do is we're going to create a list, which is the product of A and B. So what's A plus B? And if we go ahead and run this, it'll print that out, and you'll see, in this case, when they say product, because it's an iteration tool, we're talking about creating a tuple of the 2. So we've now created a tuple of all possible outcomes of the dice, where dice A is 1, 2, 3, 1 to 6, and dice B is 1 to 6. And you can see 1 to 1, 1 to 2, 1 to 3, and so forth. You remember we had a slide on this earlier where we talked about all the different outcomes of a dice. We can play around with this a little bit. We can do in dice equals 2, dice faces 1, 2, 3, 4, 5, 6. Another way of doing what we did before, and then we can create an event space where we have a set, which is the product of the dice faces, repeat equals in dice. And we'll go ahead and just run this. And you can see here, it just again puts it through all the different possible variables we can have. And then if we wanted to take the same set on here and print them all out like we had before, we can just go through for outcome and event space, outcome and equals. So the event space is creating a sequence. And as you can see here, when we print it out, it stacks them versus going through and putting them in a nice line. And we'll go ahead and do something, let's go print. Since we have the end printing with a comma, that just means it's not going to hit the return going down to the next line. And we'll go ahead and do the length of our event space. That'll be an important variable we're going to want to know in a minute. And of course, if I get carried away with my typing of length, we'll print it twice and it'll give me an error. So we have 36 different possible variations here. And we might want to calculate something like, what about the multiple of 3? What if we want to have the probability of the multiple of 3 in our setup? And so we can put together the code for the outcome and event space of x, y equals outcome. If x plus y remainder 3, so we're going to divide by 3 and look at the remainder, and it equals 0, then it's a favorable outcome. And we're going to pop that outcome on the end there. And we'll turn it into a set. So the favorable outcome equals a set. Not necessary because we know it's not going to be repeating itself, but just in case, we'll go ahead and do that. And if we want to print out the outcome, we can go ahead and see what that looks like. And you can see here, these are all multiples of 3. 1 plus 2 is 3, 5 plus 4 is 9, which divided by 3 is 3, and so forth. And just like we looked up the length of the one before, let's go ahead and print the length of our F outcome so we can see what that looks like. There we go. And of course I did forget to add the print in the middle because we're looping through and putting an end on the setup on there, so we're going to put the print in there. And if I run this, you can see we end up with 12. So we have 36 total options. We have 12 that are multiple that add up to a multiple of 3. And we can easily compute the probability of this by simply taking the length of our favorable outcome over the length of the event space. And if we print it out, let me put that in there, probability last line, so we can just type it in. We end up with a 0.3333 chance. That's roughly a third. And we might want to make this look nice. So let's go ahead and put in another line there. The probability of getting the sum, which is a multiple of 3, is 0.3333. We can compute the same thing for 5 dice. And if we do this for 5 dice and go ahead and run it, you can see we just have a huge amount of choices. So it just goes on and on down here. And we can look at the length of the event space. And we have over 7,776 choices. That's a lot of choices. And if we want to ask the question like we did above, what is the sum, where the sum is a multiple of 5 but not a multiple of 3, we can go through all of these different options, and then you can see here D1, D2, D3, D4, D5 equals the outcome. And if you add these all together and the division by 5 does not have a remainder of 0, but the remainder is also of a division by 3 is not equal to 0. So the multiple of 5 is equal to 0, but the multiple of 3 is not. We can just append that on here, and then we can look at that favorable outcome. We'll go ahead and set that, and we'll just take a look at this. What's our length of our favorable outcome? It's always good to see what we're working with. And so we have 904 out of 776. And then, of course, we can just do a simple division to get the probability on here. What's the probability that we're going to roll a multiple of 5 when you add them together, but not a multiple of 3? And so we're just going to divide those two numbers, and you can see here we get 0.116255, or 11.62%. And so you can really have a nice visual that this is not really complicated math right here on probabilities. It's just how many options do you have, and how many of those are you possibly going to be able to come up with the solution you're looking for. And this leads us to a confusion matrix. A confusion matrix is a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. And so you'll see on the left we have the predicted and the actual. And we have a negative, false negative, positive, true positive, and then we have false positive and true negative. And you can think of this as your predicted model. What does that mean? That means if you divided your data and you used 2/3 of it to create the model, you might then test it against an actual case for the last third to see how well it comes out. How many times was it true positive versus false positive? It gave a false positive response. And you can imagine in medical situations, this is a pretty big deal. You don't want to give a false positive. So you might adjust your model accordingly so you don't have a false positive. Say with a COVID virus test, it'd be better to have a false negative and they go back and get retested than to have 30% false positives where then the test is pretty much invalid. So in a use case like cancer prediction, let's consider an example where a cancer prediction model is put to the test for its accuracy and precision. Actual result of a person's medical report is compared with the prediction made by the machine learning model. And so you can see here, here's our actual predicted, whether they have cancer or not. You know, cancer, a big one. You don't want to have a false positive. I mean, a false negative. In other words, you don't want to have it tell you that you don't have cancer when you do. So that would be something you'd really be looking for in this particular domain. You don't want a false negative. And this is, again, you know, you've created a model. You have hundreds of people or thousands of pieces of data that come in. There's a real famous case study where they have the imagery and all the measurements they take. And there's about 36 different measurements they take. And then if you run a basic model, you want to know just how accurate it is. How many negative results do you have that are either telling people they have cancer that don't, or telling people that don't have cancer that they do. And then we can take these numbers and we can feed them into our accuracy, our precision, and our recall. So accuracy, precision, and recall. Accuracy metric to measure how accurately the results are predicted. And this is your total true, where you got the right results, you add them together, the true positive, the true negative, over all the results. So what percentage of them were accurate versus what were wrong. When we talk about precision, is a metric to measure how many of the correctly predicted cases are actually turned out to be positive. So we have a precision on true positive. Again, if you're talking about like COVID testing with the viruses, you really want this to be a high number. You want this true that to be the center point, where you might have the opposite if you're dealing with cancer, where you want no false negatives. So this is your metric on here. Precision is your test positive, true positive plus false positive. And then your recall, how many of the actual positive cases we were able to predict quickly with our model. So test positive is the test positive plus the false negative on there.
Let's look at an example of a common use for linear regression. Profit estimation of a company. If I was going to invest in a company, I would like to know how much money I could expect to make. So we'll take a look at a venture capitalist firm and try to understand which companies they should invest in. So we'll take the idea that we need to decide the companies to invest in. We need to predict the profit the company makes, and we're going to do it based on the company's expenses, and even just a specific expense. In this case, we have our company, we have the different expenses, so we have our R&D, which is your research and development, we have our marketing, we might have the location, we might have what kind of administration it's going through. Based on all this different information, we would like to calculate the profit. Now, in actuality, there's usually about 23 to 27 different markers that they look at if they're a heavy-duty investor. We're only going to take a look at one basic one. We're going to come in, and for simplicity, let's consider a single variable R&D and find out which companies to invest in based on that. So when we take our R&D and we're plotting the profit based on the R&D expenditure, how much money they put into the research and development, and then we look at the profit that goes with that. We can predict a line to estimate the profit. So we can draw a line right through the data. And when you look at that, you can see how much they invest in the R&D is a good marker as to how much profit they're going to have. We can also note that companies spending more on R&D make good profit. So let's invest in the ones that spend a higher rate in their R&D. What's in it for you? First, we'll have an introduction to machine learning, followed by machine learning algorithms. These will be specific to linear regression and where it fits into the larger model. Then we'll take a look at applications of linear regression, understanding linear regression, and multiple linear regression. Finally, we'll roll up our sleeves and do a little programming in use case profit estimation of companies. Let's go ahead and jump in. Let's start with our introduction to machine learning, along with some machine learning algorithms and where that fits in with linear regression. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from is called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1, plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values, based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e-square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumberPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000 companies.csv. You're going to have to change this to fit whatever setup you have. In the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a colon -1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one-hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across, and we have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the 3rd row. And in there we're going to take the label coder and we're going to fit and transform the X, also the 3rd row. So we're going to take that 3rd row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one-hot encoder, which equals one-hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one-hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that 1 extra column we put in there when we did our one-hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit. Because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take y. We've already created those. X has the columns with the data in it, and y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do xtrain and ytrain because we're using the training data, x being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a yPredict variable, and we're going to put in the xTest. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have yPredict equals regressor.predict xTest going in, and this gives us yPredict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print yPredict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print yPredict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m to the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103,009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. We're looking at the error. So, in the R2 score, we take our y-test versus our y-predict. Y-test is the actual values we're testing. That was the one that was given to us, so we know are true. The y-predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
What is logistic regression? Let's say we have to build a predictive model or a machine learning model to predict whether the passengers of the Titanic ship have survived or not, the shipwreck. So how do we do that? So we use logistic regression to build a model for this. How do we use logistic regression? So we have the information about the passengers, their ID, whether they have survived or not, their class and name and so on and so forth. And we use this information where we already know whether the person has survived or not. That is the labeled information. And we help the system to train based on this information, based on this labeled data. This is known as labeled data. And during the process of building the model, we probably will remove some of the non-essential parameters or attributes here. We only take those attributes which are really required to make these predictions. And once we train the model, we run new data through it, whereby the model will predict whether the passenger has survived or not. So let's see what we will learn in this video. We will talk about what is supervised learning, and we will go into details about classification, which is one of the techniques for supervised learning. And then we will further focus on logistic regression, which is one of the algorithms for performing classification, especially binary classification. Then we will compare linear and logistic regression and what are some of the logistic regression applications. And finally, we will end with a use case or a demo of actual Python code for doing logistic regression in Jupyter Notebook. Alright, so let's start with what is supervised learning. Supervised learning is one of the two main types of machine learning methods. Here we use what is known as labeled data to help the system learn. This is very similar to how we human beings learn. So let's say you want to teach a child to recognize an apple. How do we do that? We never tell the child, okay, this is an apple has a certain diameter on the top, a certain diameter at the bottom, and this has a certain RGB color. No, we just show an apple to the child and tell the child this is apple. And then next time when we show an apple, child immediately recognizes, yes, this is an apple. Supervised learning works very similar on the similar lines. So where does logistic regression fit into the overall machine learning process? Machine learning is divided into two types, mainly two types. There is a third one called reinforcement learning, but we will not talk about that right now. So one is supervised learning and the other is unsupervised learning. Unsupervised learning uses techniques like clustering and association, and supervised learning uses techniques like classification and regression. Now, supervised learning is used when you have labeled data. You have historical data, then you use supervised learning. When you don't have labeled data, then you used unsupervised learning. In supervised learning, there are two types of techniques that are used, classification and regression, based on what is the kind of problem we are solving. Let's say we want to take the data and classify it. It could be binary classification, like a 0 or a 1. An example of classification we have just seen, whether the passenger has survived or not survived. It's like a 0 or 1. That is known as binary classification. Regression, on the other hand, is you need to predict a value, what is known as a continuous value. Classification is for discrete values. Regression is for continuous values. Let's say you want to predict the share price, or you want to predict the temperature that will be there. What will be the temperature tomorrow? That is where you use regression. Whereas classification are discrete values. Will the customer buy the product or will not buy the product? Will you get a promotion or you will not get a promotion? I hope you're getting the idea. Or it could be multi-class classification as well. Let's say you want to build an image classification model. So the image classification model would take an image as an input and classify into multiple classes, whether this image is of a cat or a dog or an elephant or a tiger. So there are multiple classes, so not necessarily binary classification. So that is known as multi-class classification. So we are going to focus on classification because logistic regression is one of the algorithms used for classification. Now, the name may be a little confusing. In fact, whenever people come across logistic regression, it always causes confusion because the name has regression in it, but we are actually using this for performing classification. Okay, so yes, it is logistic regression, but it is used for classification. And in case you are wondering, is there something similar for regression? Yes, for regression, we have linear regression. Keep that in mind. So linear regression is used for regression. Logistic regression is used for classification. So in this video, we are going to focus on supervised learning, and within supervised learning, we are going to focus on classification, and then within classification, we are going to focus on logistic regression algorithm. So first of all, classification. So what are the various algorithms available for performing classification? The first one is decision tree. There are of course multiple algorithms, but here we will talk about a few. Decision trees are quite popular and very easy to understand, and therefore they are used for classification. Then we have k-nearest neighbors. This is another algorithm for performing classification. And then there is logistic regression, and this is what we are going to focus on in this video, and we are going to go into a little bit of details about logistic regression. Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis, x is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the class, the outcome rather. So for a logistic regression curve, a threshold has to be set saying that because this is a probability calculation. Remember, this is a probability calculation and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0 and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1. And let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now, let's do a quick comparison between logistic regression and linear regression because they both have the term regression in them. So that can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this where you're trying to find continuous values is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion. That is a no. And this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not. Yes, no, right? So there is nothing in between. And what is the employee's rating? Okay. And ratings can be continuous. That is not an issue. But the output is discrete in this case. Whether employee got promotion, yes, no. Okay. So if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right because it looks like there will be a lot of errors. Thus, root mean square error, if you remember for linear regression, would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images we can display using matplotlib, some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's the gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label. That's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, yeah, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay. All right. So with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images, that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of the entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable. and y underscore train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x underscore train. And since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2. So this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this. Right? So this is the label. So the same way, x underscore train, y underscore train is for the training data set, x underscore test, y underscore test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of this. So x underscore train, the shape is 1383 by 64, and y underscore train has 1383 because there is nothing like the second part is not required here. And then x underscore test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is, or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So if let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value and also the predicted value. Both are 4. This is an image of 0. So the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1. And again, this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of k, where I equals 1 to k. K would represent the number of the different animals in there, where value, or p, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8
So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here where I have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the numpy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this, it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path, I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balanced data from the Panda Read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance_data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, And let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet, or open Office Calc, or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it as source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data.values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or I'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it. Let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X-test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y-test, that's the one we ran the predict on. And then we put in our yPredict in, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. Today we're going to be looking at random forest, one of the many powerful tools in the machine learning library. Before we dive into the topic, let's start by looking at a few of the uses for random forest. Currently today it's used in remote sensing. For example, they're used in the ETM devices. If you're a space buff, that's the enhanced thematic mapper they use on satellites, which see far outside the human spectrum for looking at land masses. And they acquire images of the Earth's surface. The accuracy is higher and training time is less than many other machine learning tools out there. Also, object detection, multi-class object detection is done using random forest algorithms. A good example is traffic, where you're trying to sort out the different cars, buses, and things. And it provides a better detection in complicated environments. It's very complicated up there. And then we have another example, connect. And let's take a little closer look at Connect. Connect, they use a random forest as part of the game console. And what it does is it tracks the body movements and it recreates it in the game. And let's see what that looks like. We have a user who performs a step. In this case, it looks like Elvis Presley going there. That is then recorded so that Connect registers the movement. and then it marks the user based on accuracy. And it looks like we have Prince going on this one, from Elvis Presley to Prince. It's great. So it marks the user based on the accuracy. If we look at that a little closer, we have a training set to identify body parts. Where are the hands? Where are the feet? What's going on with the body? That then goes into a random forest classifier that learns from it. Once we've trained the classifier, it then identifies the body parts while the person's dancing. And it's able to represent that in a computer format, and then based on that, it scores the game and how accurate you are as being Elvis Presley or Prince in your dancing. Let's take an overview of what we're going to cover today. What's in it for you? What we're going to start with is what is machine learning. We're not going to go into detail on that. We're going to specifically look at how the random forest fits in the machine learning hierarchy. Then we're going to look at some applications of random forest. What is classification, which is its primary use? Why use random forest? What's the benefits of it? And how does it actually come together? What is random forest? And then we'll get into random forest and the decision tree. That's like the final step in how it works. And finally, we'll get some Python code in there, and we'll use the case, the iris flower analysis. Now, if you don't know what any of these terms mean or where we're going with this, don't worry. We're going to cover all the basics and have you up and running, and even doing some basic script in Python by the end. Let's take a closer look at types of machine learning. Specifically, we're going to look at where the decision tree fits in with the different machine learning packages out there. We'll start with the basic types of machine learning. There's supervised learning, where you have lots of data and you're able to train your models. There's unsupervised learning, where it has to look at the data and then divide it based on its own algorithms without having any training. And then there's reinforcement learning, where you get a plus or negative if you have the answer correct. This particular tool belongs to the supervised learning. Let's take a closer look at that, what that means in supervised learning. Supervised learning falls into two groups, classification and regression. We'll talk about regression a little later and how that differs. This particular format goes underneath classification. So we're looking at supervised learning and classification in the machine learning tools. Classification is a kind of problem wherein the outputs are categorical in nature, like yes or no, true or false, or 0 or 1. In that particular framework, there's the KNN, where the NN stands for nearest neighbor, naive Bayes, the decision tree, which is part of the random forest that we're studying today. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better, even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. In this random forest, then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? We'll go, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes those decisions is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in 2. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to 2 lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second 2, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has 2 or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out, how does a decision tree work? So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle. It's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by a diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3, We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and you go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in 2 more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Pandas is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. the first thing you want to notice is that our DF has created what looks like an Excel spreadsheet. And in this Excel spreadsheet, we have set the columns. So up on the top, you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column header set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the 3 that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into 2 different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it And then the other 25% we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create 2 variables. We're going to create 2 new data frames. One's called train, one's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next 2 steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans. And let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a panda thing, the df columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, pd. Factorize. What is factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this just like when we were up here and I typed in y and it printed out y instead of print y. This does the same thing. It treats this as a variable and prints it out. But if you're actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see in jobs equals 2. You can see the random state equals 0. Those are the 2 that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, Setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for virginica, and it predicts a 0 for versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, virginica gets 0.5 votes, versicolor gets 0.5 votes, but let's just go with the virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, virginica, versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, and it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually let's do the first 25, just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the versicolor and the virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes two sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here, and we have the predicted species. So across the top you'll see the Setosa versicolor virginica and the actual species, Setosa versicolor virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have versicolor where they meet, and you have virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says virginica, but it was supposed to be versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction, and we read it on test features. But we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this. Today we're going to cover the k nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor K? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws. How sharp are their claws? and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question. Usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or it's not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at K equals 3, we can classify, we have a question mark in the middle, as either a square or not. Is it a square or is it, in this case, a triangle? And so if we set K equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put K equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the K changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of K? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right K? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of K, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your K is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing K, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your K value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the K value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work?
consider a dataset having two variables, height in centimeters and weight in kilograms, and each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what, 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. At 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results. So we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are three tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our two general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those, you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column
equals dataset column.replace. This is still pandas. You can do a direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, NumPy NAN is what that stands for, is none, it doesn't exist. So the first thing we're doing here is we're replacing the 0 with a NumPy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything where, except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you want to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set, let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle. Because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go ahead and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the iLocation, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far, we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there with the actual running of our KNN. We need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replace that with the means of those columns, that way that they fit right in with our data models. We've come down here and we split the data, so now we have our test data and our training data, and then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using K-neighbors classifier and fit the train data in the model. So we do all that data prep, and you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. And that's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the K-neighbors classifier. N neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean's the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score, and finally accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the 2 values we're going to put in there, and let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED, predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like 3 different, if you're looking at this across 3 different variables instead of just 2, you'd end up with the 3rd row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn.
and running the KNN, the K nearest neighbor, on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
What is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with K-means clustering, we will have here, that means K is equal to 2, and we will have 2 clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in K-means clustering is the allocation of 2 centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means K is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. Initially, they are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them one point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color. and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined, and the original randomly allocated centroid is repositioned to the actual centroid of these new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D, E, and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with. And then as we progress, we keep changing until we get the best clusters. Or there is a technique called elbow technique whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly that to start with randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point. And if required, the data points are reallocated to the new centroids and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares. And the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated, and the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here. But after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned the value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we picked the centroids randomly, so they are not real centroids. So now what we have to do? We have to calculate the actual centroids for each of these groups, which is like the mean position. Which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to Ck, and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. x1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing. And that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to Ck. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups because we wanted to create k clusters, right? So we have k groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position, which is the actual centroid for each of these groups. Okay. And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have k groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of k-means clustering. We will actually see some live demos in Python Notebook, using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python Notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python Notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python Notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like matplotlib and numpy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead and, so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually also, we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and it will create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0, cluster 0, 1, 2, and 3 maybe, and then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k means. When we call predict, that is what it does. And we can take a quick look at these y underscore k means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance, and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step, what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering. And there is a function or a library calculates for a given two pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid. And then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare. And if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop. It only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. as usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this, and so this is how the original, the color, the pixel distribution is. These are 2 plots, one is red against green and another is red against blue, and this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in, the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are this is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also three-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors, and this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors, and then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using blob to just execute the k-means clustering.
Now you'll notice here we're using pandas. Whoops, I drew it through the pandas, and we're going to go ahead and read it as a pandas data frame. And of course pandas sits on NumPy, so a lot of stuff you do with pandas can go right into NumPy very easily. And the reason I bring this up is because pandas has a lot of tools in there for just looking at the data real quick and easy. And so the first one we want to go ahead and do is do credit.df or credit_df, our data we read in info, and just see what that looks like. And when we go ahead and print this out, you can see here we have 13 columns. Remember, we were looking at our data and it had that row you couldn't read across the top. Then it has non-null count. How many values don't have null? What kind of objects are they? They're an object, an integer, different things like that. And we look at object. Is it a checking account? This is probably text on here. Duration, how long, credit history, amount, savings account, present employed since. So a lot of different numbers coming in here, and these are just the columns we're looking at. And if you're going to look at the columns, it's kind of nice to actually look at the data. And so we'll use the pandas to go ahead and print it out just like you would on a spreadsheet. Hard to see them all on here, but you can see we have, here's our row across the top, because Panda does such a good job sorting out columns, and the actual data. Checking account A11, A12, A14, not sure what that means. Duration, how long they've had it. Credit history, not sure what the A33 or A34 means. I'm sure it has a special meaning on there. The amount, here's our savings account and all the information on that. And this is actually a much more easy to read view than what we had before, as far as like that text file. When you're just looking at data through the database, sometimes those can be really hard to read. This you can really see, and if I take it down a notch, I can get all the columns in here. We'll go ahead and keep it zoomed in just so we can see that what's going on a little easier. And then we can also do creditdf.ilocation. The ilocation feature in the pandas is going to go ahead and do rows 0 through 5, and we're going to look at columns 1 through 7. And let's go ahead and just run that. And you can see right here how we just split it up. So it's real easy to manipulate our data and get a smaller view of different parts of the data as we're going through it. And just like we can look at the first 7 columns, we can also look at the last 7 columns. Same kind of format. We're looking at rows 0 through 5, column 7 to the end, if you leave the number out there. And you can see we can easily now look at this on a smaller screen, much better for displaying. Those are just tricks to help you display your information so that when you present this in front of a group of people, it makes it very easy to read, or you can just copy this out and put it into a document, that kind of thing. And then we also like to go ahead and do like credit status value counts and things like that. Again, we're just looking at the different sets of information on here. And in our pandas data frame, value counts is we're looking at unique values. So there's a lot of unique values in here. That's 700 and 300. That's a significantly diverse set of data. And if we look at the data, one of the things we're looking at is the status 01, 001. And I'm going to guess that that means that it is either default or not default. So that's probably what we're going to want to look for. Hopefully you've had your specialty in domain. Remember we talked about the different parts of data science. Domain is what field it is in. This would be in banks and loans. And so if we want to figure out what the status of a new loan is, we're going to separate the status out. And so if we take our X features equals a list of the columns, that's all this is, credit_df.columns. We remove status, and then we go ahead and this will print our features out, and you can see it's everything but the status on the end. Because that's what we want to predict. We want to predict the new data, whether that status is 0 or 1 or not. And next we want to do a little bit more data preparation. We're going to go ahead and encode. And we're going to take an encode credit df. We're going to create that off of our setup on here. And you're going to ask, well, what are we encoding on here? Well, when we go up to here, let me just go back all the way. When we're looking at all this information up here, you can see there's object, object, object. Well, if I'm doing a prediction and something's just a random object, it doesn't really mean anything. There's no numbers to process. And so when we come down a little further, we can see down here that we are looking at A65. I'm not sure what A65 means. We're looking at A93 personal status. We're looking at A143. These aren't actual numbers. There's some kind of code that the bank put in, probably. And so for our model, they really don't mean anything unless we convert them to numbers. And you convert them to numbers by literally creating a bunch of yes/nos. So instead of thinking it as A173 and A172 as being 0, 1, and if you had A174, maybe 0, 1, 2, you would think of this as a label, A173 is true or false. And then you'd have another label, A172 is true or false. So for every unique job in here, that it becomes another feature added in, and it's on or off, it's true or false. That's what this encoding is doing. And we'll go ahead and list our encoding as it comes out. And if you come up here, you can see it did exactly what I was describing. We've now encoded it. So here's checking account A13, checking account A12, 14, A31. Here's all of our checking account numbers. So there was 3 of them. Here's our credit history, A31, A32, A33, A34. Again, the computer has no idea of knowing what those are. All it knows is those are each unique features. And the same thing with the savings account, A62, and so on, going down. And so once we have our nice list of there, we can go ahead and do, let me pull this in. Here we go. Let's look at our new data set. And if we go ahead and run the new data set, we have our income credit DF checking, and we're just going to look at these and look at the head. This is just the first few of these, so we can see what it actually looks like in the data. And just like I said, it's now 0, 0, 0, 0, 1, 1, 0, 0. This first column is just the count, 0, 1, 2, 3, 4. That's not part of the data. But you can see here that it just puts a check mark of 1 because it's an AC A12, and we have a checking account AC A14 where it's also a check mark of 1 going across. So we've done a little data preparation. We've come in here and done some exploratory data analysis. And now we want to start building our data model. And we'll kind of go back and forth between exploratory data analysis and data model, and then interpreting the results on this. And so when we go ahead and import our stats models as API as SM, now a lot of times we use the sklearn or the scikit models. In this one we're going to go ahead and use the SM model from stats models, which is pretty common for doing a very basic logistics regression model. And then from the scikit we're going to have our train test split. With any data, you want to go ahead and train your model, and then you need something to test it on, some unknown data, so you can see how well you did. Very common in your setting up your models is to split it up into your training set and your testing set. And what I want you to notice on here is we have xtrain. Well, what is xtrain? That's all the columns except for the last one, which was the status. Was it default or was it in good standing? And then, of course, our x-test is part of the data. We're going to split that up by 0.3, so 30% of the data is going to be, 30% of our rows are going to be put in the x-test, and the y-train and y-test is just the status. And then we create our, once we've created our data and split it up, we go ahead and create our model, and it's a logit. We're just going to call it logit, but a lot of times you end up seeing logit model. With logit, it equals the sm.logit xtrain, ytrain xtrain. In sklearn it's always xtrain ytrain, but in the stats model it's reversed on there. And then they go ahead and run the fit. So we load the data up and then we fit it, and then we can go ahead and summarize that model and see what it looks like. And let's go ahead and run that. It takes it just a moment, and we get a nice summary of our data. Again, we're still looking at the data, and we have takes just a moment to kind of feed through, and you can certainly see where we have our coefficient, which has to do with the weights in the model. Standard error, that's very important as we look at this coefficient and how it affects the model. P is greater than the absolute value of Z, 0.025. These are all your statistical notes on here. So as you look at these, you might look at like how big is a standard error. That's one of the big ones that I usually look at. As we go up and we start looking at the different things, the higher the error, the less, the more we want to be a little careful of it. The lower the error, the better. In more general terms, they also have dealing with the model and its iterations. You can see some general status on here. How many iterations did it have to go through before it was able to come up with the numbers? Because it kind of guesses. It's playing a high-low game, and it takes it 6 iterations till it finds what it considers the best fit. And you can see there's more information up here as far as when it converged, how it converged, and so on. Now, when we have our summary up there, one of the questions starts coming in. Remember I told you we're looking at like our standard error and how these numbers all are telling us how important each one of these features is in running our prediction. And if you have a ton of features and some of them are just kind of all over the place, all they do is create noise. So we really want to get rid of them. They also cause issues in that if you're running a huge amount of data and you have to rerun this model over and over again, this can really tax your time, and so you're losing both time, money, and your results might not be as good because they might be weighted based on some of these very fuzzy numbers. So we're going to look at significant variables and put together a little routine for that. Again, we've come in, if you remember from back here, we're still in kind of an exploratory data analysis and data modeling. They kind of go hand in hand sometimes. We haven't quite got to interpreting the results and running predictions. And so we'll go ahead and build this thing on here. It looks at the LM values, so that's coming up here where this was generated. I'd have to actually look that up for this particular model because I usually use the sklearn version of this. So as we look at this, we're going to look at the p-values of our variables, and basically we're looking to see how good the p-values are. If they're less than or equal to 0.05, we probably those are probably solid values, and if they're greater than that, then probably we're not interested in them. And so let's go ahead and run this, and we see that when we pull out all the values that are less than or equal to 0.05 for the p-values, and if we go up here, here we go, here's our p. I knew it was up here, I just wasn't seeing it correctly. So you can probably see duration, that's going to be good. Amount, 0.01, that looks good. Instant INST rate, which I'm guessing is the percentage rate or the interest. I was trying to say INST and interest at the same time. So we have our interest rate and all that. If we come down here, we see duration, amount, our instant rate, age, checking account A13, checking account A14, credit history A34, savings account A65. These are our primary features. These ones are related when we look at the data. These are the ones that are going to predict whether it's a good or bad loan. And so now that we know which ones work, we want to go ahead and recreate our SM model, or our final logit model. And you'll see here we now have the X train, the Y train, and then instead of the X train, it's X train significant variables right there. So all we're doing is running this just on the significant variables in the setup. And we'll go ahead and fit it. And you can see here you can actually double bracket and do it all in one line. Up above we had to do it in the 2 lines. There's just how the setup is for this particular module. And then we'll go ahead and do a final legit summary and just see what that looks like. And we can see here, here's our p-scores. Remember, they're all supposed to be under underneath the 0.05. These are all under 0.05. You can see up here are different statuses as far as how it ran. It still took 6 iterations to go through the data, the date, and so forth. And now that we have a solid model, and that's, if you remember correctly, let me flip back on over here. We've done our data modeling, we've created a solid model, and so now we need to actually run a prediction so that we can interpret the results and weigh in on that and see how good they are. And so for that, I'm going to go ahead and, let's see if we can find it over here. Y predict. So we have our model that we created. We want to go ahead and create our Y predict, and it's based on our final eject. And here's the magic word predict, or dot predict. And so this is where we're going to come in and actually get our predictions on here, that our model comes up. And remember, we're testing, X test is going in. There's our X test, and it's only the significant variables. So we've created our model. Now we want to push in our test version that's never seen this data before. So this is all new. And then we're just going to take a random sample to see what it looks like. What do those predictions look like? In this random sample, we're just looking at 10 of these. And you can see here is the actual number. It says 0.08, gives us a 1. 0.07, this is our probability number, which is, I would have to actually look to see whether higher or lower is better. I'm guessing the closer to 0, the better it is, but I'm not completely sure on that. I have to actually look up and see with this particular framework. But you can see the actual prediction, 1, 0, 0, 0. So I guess this is a good loan, a bunch of defaults, and some good loans. That's what it predicts it's going to come out as. Now, just looking at the data, it's confusing. You have different models, they have different setup, they have the predicted probability comes out on this, and other models it doesn't. So you really need a tool to dig deeper into the setup to understand what this means. And so what we're going to do is we're going to take our predicted values, which you can see right here has an actual predicted probability, and then we're going to go ahead and insert on there from a sample. Let me just run this because it'll make a lot more sense. We have our actual value and our predicted value. So this is what we predicted, and this is the actual setup. If we just look at this right off the bat, we can see that we predicted 0 and this was a 1. These all came out correct. Number 332 came out correct. 917 was an actual. They were good on their loan and they predicted it's going to be a default. You start to see that there's some variance. So how do we measure that? How do we know whether our model was any good or not? Well, for that we're going to go ahead and load up a nice graph, and we'll use, for our graph, we'll import Matplot library pyplot and Seaborn. Seaborn sits on Matplot library. And this Matplot library inline is just because I'm using Jupyter Notebook. With the new version I'm in, it doesn't even need it, but I tend to leave it in for older versions. And then we import from our sklearn metrics. This is your scikit. Scikit is the main package, and sklearn is how it looks on here. And we'll go ahead and run that so it's nicely loaded. And then we'll go ahead and create a little routine in just a moment here to print this out so we can see what that looks like. And this metrics is kind of a fun metrics because it tells you like how many you have correct on the correct one, how many you had wrong on the wrong one. And this top part is just all a draw routine. So it comes in here and has our actual and our predicted, and has our CM metrics. It breaks it up, puts it into the heat map. The SN heat map gives it some colors, add some labels, and then we go ahead and show it. And we're just going to dump that in there and run that. And you can spend forever building graphics. It's so much fun. We come in here, we have bad credit, good credit. We have bad credit, good credit. We have predicted label. And so when you look at this, you can see here it had, on the good credit, it tells you how well it predicted it and how many false positive it has. And on our bad credit, here we have bad credit, bad credit. It said 30 of those were bad credit. It predicted them bad credit. While 21 were good credit that it predicted would be bad credit. And then we have here, we have 188 that were good credit. But the actual value, and then it had 61 that were bad credit that it said were predicted good credit. So at this point, you'd look at this and you'd say, well, if I'm predicting this is our good credit here. Let me flip this on over here. And this is our bad credit. There we go. So we have bad credit, good credit. You start looking at that and you say, okay, can we afford that many defaults after 5 years or whatever it is? And so those are the questions you start asking is, does this model work good enough to predict whether we should give these people loans or not? You're always going to have somebody default on them. And again, that starts going into domain, banking domain, something I don't know very much about. Clearly I know whether I default on a loan or not, which I don't, and I try very hard not to. And then if we're going to draw the chart, which is really nice to have just a clear visual chart. Metrics also has our classification report, and you can see these are just the numbers we were looking at. They let us know the precision, our F-score and recall and all that stuff on here. You can just print a straight out metrics classification report. Now, we looked at a regression model. Let's go ahead and look at a clustering model to see what that looks like. And we'll go ahead and create a new Python on there. And this is going to be our clustering setup. Let me flip this off and switch on over to my clustering menu. In this case, we're going to be looking at k-means clustering. So let's just put that up here. K-means clustering. Now, the last one was a regression model, so it figured out coefficients for lines. You can go back to your old Euclidean geometry or the algebra expression for slope on a line, y equals mx plus b or whatever. And it goes on from there as far as finding distances and figuring out the lines on there. This is a little bit different. When we talk about clustering, it uses similar ideas, but it has to do with edges, 2 points, and how do you figure out a distance between 2 points and what does that mean? Now, you'll see here we have our pandas PD, our numpy is NP, our matplot library. Seaborn sits on matplot library as we talked about. They've added some parameters here as far as colors, and then we did an inline for the matplot library. Again, that's not really necessary. Even in the new version of the Jupyter Notebook, in the old version of Jupyter Notebook, if you didn't do that, it would just kind of hang or disappear. And then we're going to import some data. It's important to have our data set up in here. And instead of looking at this and guessing what the data is, usually you open up the CSV file at this time. Let's just go ahead and print it under the DF head. Because really those text files are so messy, and you look at the DF head and it's easy to look at. Whoops, had a path issue there. So college data, it's a CSV, so it automatically knows there's a .csv on there. And we can see here that they downloaded from a number of colleges, Abilene Christian University, Adelphi University, Adrian College, and then it has whether it's private, I'm guessing yes or no, apps, I'm not sure what that is, acceptance rate, applications I'm betting, and then the acceptance rate, enrollment, top 10%, top 2, 5%, undergrad, so on. So these are just statistics based on the college, their college getting into a college. And just like we did before, let's explore the data. If you can remember from the chart we were looking at, we're going through our data discovery, data preparation, and exploratory data analysis. So we're really kind of looking at the data and what do we have here, what came in. At this point, the data has already been prepared. We're not doing a whole lot as far as getting rid of null values and finding out whether it's bad data or good data and that kind of thing. And data discovery would be figuring out which data to send. So that we've already done. So we're going to go with the exploratory data, jump into data modeling, and interpret the results just like we did with the other one. And we'll go ahead and use the Panda tool to get the info. DF, you'll see DF very commonly. It just stands for data frame. A lot of people use it as a generic setup when they import from Pandas. And so we have our info, and you can see right here, non-null numbers. Here's our count. So each one of these has 777 non-null values. And again, here's our type of data we're dealing with. And if you remember from last time, here's an object. This was our yes or no. Everything else looks like it's integer. We do have a float value here, integer. Floats and integers, usually when you're running them on a prediction, they're pretty interchangeable in a lot of cases. But whether it's private, true or false, that's pretty important on here. The fact that they could probably be switched to a 0 or 1 is pretty helpful also. And if we're going to look at all that data, we can go ahead and describe it. So there's our data frame, describe. And you have the same thing. Here's our count. All these should be 777. We have the mean value, so you can actually look at what our average is, standard deviation, minimum, different quartiles, 25, 50, the third quartile, that's so on. And of course our max value on there, min and max. And as we explore the data, we can do a lot of fun things on here. We're going to use our Seaborn, and we're going to look at room and board versus graduation date. We're going to add, this is going to be a heat map, so we're going to add whether it's a private college or not, how it fits, the size, the aspect ratio, and all that. That's what this line is here. Seaborn, you can almost do your own class on Matplotlib in Seaborn because there's so many features in there. But when you look at the very basics, you can throw up some data and have a nice colorful map set up. And here we have our graduation rate compared to room and board costs, and in private or public. So you can see that the graduation rate compared to room and board. Interesting thought. How much did I spend on room and board? Am I going to graduate the more I spend on room and board? And you can see numbers go up there on graduation rate, and you can see that the graduation rate tends to go way up for your private schools, and the room and board also continues to grow on private schools, kind of thing. It's kind of just a fun heat map. And we can explore other things in our doing our heat maps. We can look at out-of-state, whether it's out-of-state, undergrad, private again is one of our setups on here. And you can see here that for undergrad, there certainly is a lot more public schools, and whether it's out-of-state, interestingly enough, the out-of-state number goes way up, how many people coming from out-of-state into the school for the private schools. Just kind of fun things. If you're trying to figure out where you're going to go, maybe you'd want to do this for picking a bachelor's degree or a master's degree or something, or certainly you could also plot this with fun locations and download information on tourism sites if you're traveling, that kind of thing. You do the same kind of thing with. And we'll go ahead and throw out another map on here. Let me go and run this. This is a slightly different setup on here with the out-of-state. And so we're running, let's see, pull this up. Bins 20. The bins is each, how many bins are you going to split it into? And this is kind of a fun one where you can see private versus public. We have how many out-of-state, and I'd have to look this up to see what they picked on here. Oh, there we go. Okay, so you can see we have another chart that has to do with the out-of-state and the number of students coming in, and private and public. So a lot of different setups on here as we dig into the different graphing. So at this point, we've just been kind of looking at the graphs on here. Let's go ahead and import our cluster, our k-means cluster. And you can see here we have, we're going to call it KM, I guess for k-means, or maybe it's k-means model. I always label mine with model. Equals k-means in clusters equals 2, random state equals 90. And so when we cluster it, we're only going to cluster into 2 groups. That's what this is meaning here, across the different settings on there. And then we're going to go ahead and fit, and we're going to drop private. So we're not going to be looking at whether it's a private or public school. And we're just going to go ahead and run the cluster on there. And then once we run the cluster on there, we can actually look at cluster centers. Let's go ahead and do that on this. When we talk about k-means, let me run this. Boom, there we go. So we have all these different columns, and each of those columns has a center, and we start looking how the data comes together on those centers. That's what all these numbers, this is the hidden stuff behind the clusters on here. And so we can now do, maybe we'll create a little converter here. If private equals yes, return 1, else return 0. We're going to run our cluster private and apply the converter. And then we'll go ahead and print that out. Let me just show you what that looks like so you can see what we're doing here. And then we go ahead and do df cluster. We'll create a new column on here, private, apply converter. And we can see here it creates private apps except. We've just added on to our data frame on here. And we did that so that we can run the confusion matrix. Make sure we import our confusion matrix. We're going to do a classification report confusion matrix, and we'll go ahead and run this on our clustering. And as you can see here, as our predictions, here's our confusion matrix up here, just like we had on the other setup where it has how many false, true, false, false, true, false, and false, false. As your accuracy and our setup on there. This is really, if you're looking at where you want to go, maybe you're looking at where you want to go in I think more of a tourism thing, but for colleges, this is a great way for looking for a bachelor's or a master's. Coming in here, and you can start finding out which one you want to go to based on this accuracy, whether it's private or public, or how many graduations are on there. So we looked at a couple examples, went through some of the parts of the cycle, whether using a k-means or linear regression model. And certainly this cycle and these models, you start to see that there are some similarities. We're doing the same thing, and each model has a better setup depending on what you're trying to accomplish on there. The need for feature selection. To train a model, we collect huge quantities of data to help the machine learn better. Consider a table which contains information on old cars. The model decides which cars must be crushed for spare parts. And when we talk about huge quantities of data, they save everything from people's favorite cat pictures to, and you can imagine there's so much data out there. Even in a company, they'll save all these little pieces of information about people and companies and corporations. You need some way to sort through, because if you try to run your models on all of it, you'll end up with these very clunky models, and they might have issues, which we'll talk about later. But in this case, we're talking about cars and crushing. But not all this data will be useful to us. Some classes or part of the data may not contribute much to our model and can be dropped. And you can see right here we have who was the owner of the car. In our data, a car will not be crushed based on its previous owner. So that's kind of a clear cut. You can see that. Why would I care who owned the car before? Once it's in the junkyard and we're crushing the cars, we're not going to really care about that. So here we have dropped the owner column, as it does not contribute to the model. Having too much unnecessary data can cause the model to be slow. The model may also learn from this irrelevant data and be inaccurate. So feature selection is a process of reducing the input variable to your model by using only relevant data and getting rid of the noise in the data. Consider the database given below. A library wants to donate some old books to make place in their shelves for new books. We want to train a model to automate this task. In this case, the color of the book does not matter, and keeping it can cause the model to learn to donate books based on color. We can remove this as a feature. Using feature selection, we can optimize our model in several ways. And so the number one is to prevent learning from noise and overfitting. That's actually the huge one, because we don't want it to give us a wrong prediction. And that means also improved accuracy. So instead of giving us a wrong prediction, we also want it to be as close to the right answer as we can get. And we want to reduce the training time. It's an exponential growth in some of these models, so that each feature you add in increases that much more training time. We talk about feature selection methods. We put together a nice little flow chart that shows the various methods used for feature selection. And you have your basic feature selection, and then there is supervised and unsupervised. Under supervised, there's intrinsic, wrapper method, filter method. So when we talk about unsupervised feature selection, refers to the method which does not need the output label class for feature selection. And that was, you can see here under unsupervised, we don't have, that's really a growing market right now, unsupervised learning. And so feature selection is the same thing. Supervised feature selection refers to the method which uses the output label class for the feature selection. And if you remember, we looked at we have intrinsic, wrapper, and filter method. So we're going to start with the filter method on this. Now remember, we know what the output is. So we're going to be looking at that output to see how well it's doing versus the features. In this method, features are dropped based on their relation to the output, or how they are correlating to the output. And you can see here we have a set of features, selecting best feature, learning algorithm, and then performance. And so we want to find out which feature correlates to the performance on the output. Consider the example of book classifier. Here we drop the color column based on simple deduction. And that kind of sums it up in a nutshell, is we want to filter out things that clearly do not go with what we're looking for. We look at the wrapper method. In the wrapper method, we split our data into subsets and train a model using this. Based on the output of the model, we add and subtract features and train the model again. And you can see here in the wrapper method where we have a set of features, we generate a subset, we run it through the algorithm, and we see how each one of those subset of features performs. Consider the book data set. By using the wrapper method, we would use a subset of different features to train the machine and adjust the subset according to the output. And so you can see here, let's say we take name and number of times read, and we run just those, and we look at the output. And if we looked at them with all 4 inputs and look at the output, we'd see quite a different variation in there, and we might say, you know what, condition of the book and color really doesn't affect what we're looking for. And you can see here we've run it on condition of the book and color. Depending on the output of the model, we will choose our final set of features. These features will give us the best result for our model. And it might come up that the name, number of times read is probably pretty important. The intrinsic method, this method combines the qualities of both filter and wrapper method to create the best subset. The model will train and check the accuracy of different subsets and select the best among them. We kind of looked at a little overview of some of the stuff. Some of the common feature selection algorithms based on which method they belong to are given below. And you'll see it's primarily under supervised. There's not, like I said, a lot of unsupervised methods, and the ones that are usually use these methods and finds a way to create a supervised connection between the data. When we talk about supervised methods, we have our filter method, which we talked about, and it uses like the Pearson's coefficient, chi-squared, ANOVA coefficient. Those are all under the filter method. And in the wrapper method, recursive feature elimination. So remember, we're choosing a subset, and we want to go through there and look at each one. So you're just doing a lot of loops or recursive calculations to see which one works best and which ones don't have an impact on the output. And there's a lot of genetic algorithms to go with this too on the wrapper method and how they evaluate it. And with the intrinsic method, there's the 2 main ones we're looking at is the lasso regularization. The lasso algorithms are basically your standard regression model. So it's finding out how these different methods fit together and which ones have the best add together to have the least amount of error. The other one used in the intrinsic method is the decision tree. It says, hey, if this one is this one produces this result, this one produces this result, yes, no, which way do we go? Based on the input and the output variables, we can choose our feature selection model. So you have your numeric input coming in, you have your numeric output. If you use the Pearson's correlation coefficient or Spearman's rank coefficient, you can then select what features you're going to feed into that specific model. And you maybe have a numerical input and a categorical input, so we're going to be looking more at ANOVA correlation coefficient or Kindle's rank coefficient. And if you have a categorical input and a numerical output, we might be looking at ANOVA correlation coefficient and Kindle's rank coefficient. So based on the input and the output variables, we can choose our feature selection model. And you can see we have categorical to categorical. We might be looking at the chi-squared test, contingency tables, and mutual information. Let's go ahead and take a look and see in the Python code what we're talking about here. And I'm going to go ahead and use for my IDE the Jupyter notebook, and I always launch it out of Anaconda on here. And we'll go ahead and go up here and create a new Python 3 module. And we'll call it feature select. And since we're in Python, we're going to be working mainly with your NumPy, your pandas, your matplotlib library. So we have our number array, our data frame setup, which goes with the number array, the NumPy, the pandas data frame, and then we want to go ahead and graph everything. So we're going to import these 3 modules. And then we put together some data. We're going to read this in. It's Kobe Bryant. I guess he's a basketball player. Our guys in the back, we have a number of them. Guys, it's both. We have a lot of men and women, so it's probably a misnomer. Our team in the back, they have some of them have a liking for basketball, and they know who Kobe Bryant is, and they want to learn a little bit more about Kobe Bryant and what's going in for whatever's going on with his game in basketball. So we're going to take a look at him. And once we import the data, we can see what columns are available, original features count, so we can see how many features there are, the length of it, and we'll actually have a list of them, and then print just the data head, the top 5 rows. And so when we do this, we can see from the CSV file, we have 25 original features. Our original features are your action type, combined shot type, game event ID, and so forth. There's a lot of features in here that they've recorded on all of his shots. This is what we talk about, like a massive amount of data. I mean, people are sitting there and they record all this stuff and they import this stuff for different reasons. But depending on what we want to look at, do we really want all those features? Maybe the question we're going to ask is, what's the chance of him making any one specific shot? Right from the beginning, we can look at some of these things and say team name. Team name probably, I don't know, maybe it does matter because the other team might be really good at defense. Game date, maybe we don't really want to look at the game date. Team ID, definitely not of importance in any of this. So when we look at this, we have 25 features, and some of these features just really don't matter to us. We also have location X, location Y, latitude and longitude. I'm guessing that's the same data. We've actually imported the very similar data. Maybe they're slightly zoned differently. But as far as our program, we don't want to repeat data. Some of the models, when you repeat data into them, and this is true for most models, create a huge bias. They weigh that data over other data. So just at a glance, these are the things we're looking at. We want to find out, well, how do we get these features down and get rid of this bias and all these extraneous features that we don't really want to spend time running our models on and programming on. And as I pointed out, there's a location X, a location Y, latitude and longitude. Let's just take a look at that and see what we're looking at here. We'll go ahead and create a plot of these. And we'll just plot, we'll do a scatter plot of location X and location Y. And then we'll do a scatter plot of data lon, data lat, which is probably longitude and latitude. And the scatter plot, let's go ahead and actually put a little title here, location and scatter on there. And we'll just go ahead and plot these. And when you look at this coming in, these two graphs are pretty identical except they're flipped. And so when we look at the location from which they're shooting from, they're probably the same. And at this point we can say, okay, we can get rid of one of these sets of data. So we don't need both X and Y and latitude and longitude because it's the same data coming in. And as we look at this particular data, the latitude, longitude, we might also ask, does it really make a difference which side of the court you're on, whether you're on the left side or the right side? And so we might go ahead and explore, instead of looking at this as XY, we might look at it as a distance and an angle. And we can easily compute that. And you can see we can create our data distance equals the location X plus the location Y squared, standard Euclidean geometry or triangular geometry. Hypotenuse squared equals each side squared. And then once we've done that, we can also compute the angle. So the data angle is based on the arc tangent and so forth on here. So this is all this is we're just going to compute the angle here and then set that up, pi over 2 to get our angle. And we'll go ahead and run that. And you'll see some errors come up, and that's because when we took slices over here, we took a slice of a slice. There's ways to fix that, but it's really not important for this example. So if you do see that, you want to start looking up here for, instead of data location X of not location X0, this would be like, I believe the term is .ilocation. If this was, yeah, this is in pandas. So there's different things in there, but for this, it doesn't really matter. These are just warnings. That's all they are. And then let's combine our remaining minutes and seconds column into one. There's another one. So if you remember up here, we're trying to get rid of these columns. Do we really need, let me see if I can find it on here. There we go. There's our minutes remaining. And then they had, what was it? It was minutes remaining and seconds column. So there's also a seconds column on here. Let me see if I can find that one. This is where it really gets kind of crazy, because here's our seconds remaining. So you can see that, and here's our minutes remaining. This gets crazy when you're looking at hundreds of these features. And you can see that if I'm going to, say, write a model that's going to predict a lot of this, and I want it to run, in this case it's a basketball and how good his shots are as the data comes in. Let's say I want to have it run on your phone. If I'm running it across hundreds of features, it's going to just hang up on your phone, where if I can get it down to just a handful, we'll actually be able to come in here and run it on a smaller device and not use up as much memory or processing power. So we'll go ahead and take data remaining time here, and data minutes remaining times 60 plus data seconds remaining. So we're just going to combine those, and we'll go ahead and reprint our data so we can see what we got coming across. We have our action type combined, and this is, we do this a lot. We want to take a look at, oops, I got it so zoomed in. Let me see if I can zoom out just a little bit. There we go. Boom. Alright, so when we come up here, you can see that we now have our distance, our angle, remaining time, which is now just a number that computes both the minutes and seconds together. And we still have, we've been adding columns. I thought you said we're supposed to subtract columns, right? We're going to delete the obsolete columns when we get to them. So we're just filtering out, and this is the filter method. We're just filtering through the things that we really don't need. And next, let's go ahead and explore team ID and team name. Let me just go ahead and run that. And if you look at this, we have Los Angeles Lakers, and then they have the team ID here, and they're unique. That's not really anything that's going to come up, because that's this particular athlete's works for that team. So it's the same on every line. So there's another thing we can filter out on there. Team ID and team name is just useless. The whole column contains only one value each, and it's pretty much useless. Let's go ahead and take a look at matchup and opponent. That's an interesting one. And we see here that we have the LAL versus POR, and the opponent is POR and IND. Again, here's a lot of duplicate information. So this basically contains the same information on here. Again, we're filtering all this stuff out, and this is because we're only looking at one athlete. And this might change if you're looking at multiple athletes, that kind of thing. Now, these are easy to see, but we might have something that looks more like this. We might have something where we're looking at the distance, which we computed, and the shot distance. Are they the same thing? And what we can do is we can plot that and plot them against each other on here, and we see it just draws a nice straight line. And so, again, we're looking at the same information. So again, we're repeating stuff, and we really don't want to be running our model on repeat information on here. So again, it contains the same information. So now let's look at the shot zone area, shot zone basic, shot zone range. So now we're looking at the zones, and what does that mean? And we'll go ahead and do this also in a scatter plot. In this case, we're going to just create 3 of these side by side. So we're going to create our plot figure side 20 by 10. And then we're going to define our scatter plot by category feature. And we're going to do each one, set up on here, give it a slightly different color. And so our shot zone area is going to be plot, subplot 131, scatter 131 is how that's read, by the way. Meaning that it's number 1, we have 3 across, and this is the first one down, so 1, 1, 1. Our scatter plot by category is going to be the shot zone area. We're going to plot that, and then we're going to do the shot zone basic, and then the shot zone range, and each just push them through our definition. So each of those areas go through, and you'll see 131, 132, 133. Again, it's a 1 by 3 setup, and then it's just a place on each one. And so when we look at this, we can see that these shots, they map out the same. So it's very, again, redundant information. That should be intuitive. When we're looking at this in these color graphs, it kind of helps, and you start looking at something that's very intuitive like this is, and you start to realize that some of this stuff you'll be looking for in data you might not understand. And you'll see these circular patterns where they match, or they mostly match, and you start to realize when you're looking at these that they're repetitive data, and then you want to explore them more closely depending on what domain you're working in. So we look at these, and we look at them, and they look just like the regions of the court, but we already have stored this information in angle and distance columns. So we've seen this image before. We go back up here, and here's the similar image. And repeating that image is down here, and so let's go ahead and drop some of this stuff. So now let's drop all the useless columns. And we can drop the shot ID, team name, shot zone area, shot zone range, shot zone basic, the matchup, the longitude and latitude, because we're putting that into distance, seconds remaining, minutes remaining, because we combine that into one column, shot distance, because we have just distance on there, location X, location Y, the game event ID, game ID, all of this stuff is just being dropped on here. And we'll just go ahead and loop through our drops. And this is a nice way of doing this, because as you're playing with this, this kind of data, putting your list into one setup helps, because then you're just running it through an iteration, and you can come back and change it. You might be playing with different models and do this with models. You might be looking at all kinds of different things that you can drop and add in as you test these out. And again, we're working in the filter method. So this is a lot of human interaction with the data. And it takes a lot of critical thinking to look at this stuff and say what matches and what doesn't. And so when we look at the remaining features, let me go ahead and just run this. The original to the new count, we had 25 features. Now we have 11 features. You can see that right there. We just circle that. There's our 25, and there's old, new. Now we're down to 11. So we've cut it down to less than half. And you can just see the actual different information on here and the remaining time. At this point, we filtered it through, and then we'd move into the next process, which would be to run our model on this, and maybe we would drop some of the features and see if it runs better or worse and what happens. That's kind of would be the next step on there, versus this is the filter setup, and that would be one of the other setups depending on which algorithm you use. So that wraps up our demo on filter, the feature selection, and going through and seeing how these different features are being repeated in this particular in a basketball setup. The need for cost function comes in a number of points. One of them is that after training our model, we need to see how badly our model is performing. While accuracy function tells us how well our model is performing, they do not provide us with the insight on how to improve them better. And when we're talking about the training process, I'm not talking about you train a model and then you run this on there. We're talking about each time you train the model. The model itself is continually going through iterations and finding a better solution. And hence we need a correctional function, which can help us compute when our model is the most accurate. A cost function is used to measure just how wrong the model is in finding a relation between the input and the output. It tells us how badly our model is behaving, predicting. Consider a robot which is used to stack boxes in a factory. The robot might have to consider certain changeable parameters called variables which influence how it performs. Let's say our robot comes across an obstacle like a rock. The robot might bump into the rock and realize that's not the correct action. It will learn from this, and next time it will learn to avoid rocks. Hence, our machine uses variable to better fit to the data. The outcome of all these obstacles will further optimize our robot and help it perform better. The outcome acts as a cost function which helps us optimize our variable to get the best variables and fit our model. The outcome of all these obstacles will further optimize our robot and help it perform better. The outcome acts as a cost function which helps us optimize our variable to get the best variables and fit our models. So to kind of understand this, we're going to look at a linear regression model and the cost function for linear regression. It uses a straight line to fit the model. This is done using the equation for a straight line as shown. This should look familiar as your Euclidean geometry. you have y equals ax plus b, where a and b, a is the slope and b is the intercept. In this case, we'll call it output equals a times input plus b for the intercept. In the equation, we can see there are two entities which can have changeable variables or variables. We have a, which is the slope of the line, and b, which is the intercept on the y-axis. If at first the variables are not properly optimized, we get a line which might not properly fit our model. And you can see this line, as you draw it through the data, might give us a very skewed setup. It might predict one point of data, have a small error on a couple of them, and then a huge error on the other 4 pieces of data going in. And this is when we start talking about error. We're looking more at numbers than a single on-off obstacle. So it's more regression. You'll think regression numbers if you've seen some of our other videos. So we're looking at the numbers. How can we minimize the error? And as we optimize the values of our model, for some variables, we will get the perfect fit. For our linear regression model, the cost function will be the minimum of the root mean squared error of our model, obtained by subtracting the predicted values from our actual values. Our cost function will be the minimum of these error values. And you can see we have our output y equals a input, you could say a input x, plus b. And so in this case, they just went ahead and left it as output. Well, let's look at the cost function. The cost function j equals 1 over n, so we're summing up all of our outputs to inputs. And it's based on what we predicted it's going to be. So that was the output of our formula minus the actual value that we're looking for, and we square that. For our linear regression model, the cost function will be the minimum of the root mean squared error for our model, obtained by subtracting the predicted values from the actual values. Our cost function will be the minimum of these error values. When you think of this and you're computing this on a computer, like, my mind's trying to look at this long formula. It's not really that long. Really, you're adding them up one at a time, so that makes it a lot easier. Your data comes in and you say, hey, this is what the answer is. And then it goes back and says, oh, these are what the answer was supposed to be. And then you can compute each line one at a time and easily add them up to get your cost function on there. And we talk about cost functions. We certainly look at that in the linear regression model, and there's a couple other ways to do a linear regression model. But certainly we want to minimize the error. And we look at a cost function for our neural networks. Neural networks are interesting because they have multiple layers on there. And a neural network is a machine learning algorithm which takes in multiple inputs, runs them through an algorithm, and essentially sums the output of the different algorithms to get a final output. The cost function of a neural network will be the sum of the errors in each layer. This is done by finding the error at each layer first and then summing the individual errors up to get a total error. The cost function of a neural network will be the sum of errors in each layer. This is done by finding the error at each layer first. The error function will depend on the model used at each layer. And that's important to note. If you're working with neural network, it's based on the model used on each layer. So there's a whole nother level in here that we're not going to address on neural networks. Maybe I'll mention a little bit when we look at the code down here in just a minute. The below function is for linear regression model. So we have a cost function which equals the sum of the actual minus the predicted. There's our error squared, 1 over the number of observations. So if you have 100 points of data going in and you calculate your actual values minus the predicted values, you have to divide it by 100. That way, when you look at the cost function over the next setup, they're very uniform and you don't end up getting a bias on there. And so we can see here the cost function equals 1 over n times I equals 0 to n of y of I minus mx of I plus b squared. Now, when we're solving this, we have a gradient descent. Gradient descent is an algorithm which is used to optimize the cost function or the error of the model. It is used to find the minimum value of error possible in our model. When you're writing code, this comes up. There isn't a maximize function. If you go into most of like scikit-learn and a lot of the other packages in Python, they have a minimize function, not a maximize function. Because we are expecting that the error will never be unlimited. Your error can go to 0. It can't go to negative infinity. And so you always are looking for the minimum because you know it's not going to be an open-ended formula when you look for that minimum. And so the gradient descent can be visualized as a ball rolling down a hill. In this case, the ball will roll to the lowest point in the hill. This point can be taken as a point where the error is least. For any model, the error will be minimum at one point and will increase again after that. The graph shows the error in a model. And again, this comes off of the fact that we're squaring the error. The best error you can have is 0. But even if you have like a negative error, it gets squared, and so you have it's plus or minus 1. It's not looked at as a negative error and a plus error. It's just how far off are we from the least amount of error. In gradient descent, we find the error in our model for different values of an input variables. You can see here we have our error 1 listed there. This is repeated, and soon we see that the error values keep getting smaller and smaller. This is repeated, and soon we see that the error values keep getting smaller and smaller, and it just keeps going down until you find the bottom of our little downward loop on our errors. And so we can take that, and the error graph for linear regressions is given. This graph is obtained using the cost function j. And you see the cost function j. This should look familiar now. We have our predict minus our actual squared, and we're summing it up over the total number that we're computing that under. We must reach the lowest point in the graph. This can be done by traversing the graph from any point and moving to the point where the error is lower. Now, I know this is a little repetitive, but this is going to make a sense why we're repeating here in just a minute. So as we keep going down the hill, the small difference between each errors can be attained by differentiating the cost function and subtracting it from the previous gradient descent to move down the slope. So here's our cost function of j, and then we go ahead and try new numbers, and the gradient descent is going to be our difference in those. And that's how we're going to look at finding that new value in there. And if this is, they put it in the differential of j and the differential of theta. So you have theta j minus alpha times the differential. We're just looking at the differences. Just a fancy way of saying, hey, what's the difference of our last cost function minus the difference of our new cost function? And so you get a gradient descent. The gradient descent full formula looks like this, with the original difference minus the new difference summation. And as we continue to go down, we can continue to compute the differences on there to find our new values. In the above equation, alpha is known as learning rate. It decides how fast we move down the slope. If alpha is large, we take big steps. Now, remember I said we're doing a lot of repeating, that we're going down the slope, and you're going to see why we keep repeating that and where the complications come in. And it's important to note that we have this value in there of alpha. Hey, how far are we going to try on the next number? Are we going to jump way ahead? Are we going to take little steps? And you can see that this happens. We might completely miss the least error point, and our results will not be accurate. So that's one of the dangers of having a very high alpha. And as you go down, if alpha is small, we take small steps, and we may take a very long time to reach the error point and waste computational power to do it. When we're playing with this alpha, we might be talking the difference between 100 iterations and 2,000 iterations when you're talking a large neural network. And suddenly, instead of solving this in the course of an hour, you're looking at days processing time on your computer. So this is a big deal to start understanding how that alpha comes in and understanding your data and how it all fits together. Hence, we need to optimize value for alpha to attain the correct minimum error value. So we want it to go down as quickly as we can without missing where we want to go. For neural networks, each layer will have a cost function, and each cost function will have its own least minimal error value. The error graph for neural networks is shown. And this gets interesting because you're going to see that we have multiple minimal error areas that come out from the neural network. And this is also true even on some of our regular models are more complex. When you look at a polynomial regression model as opposed to linear, where we're fitting a curve versus a straight line through the data, you start having multiple minimals. And depending on where we start, we can arrive at different value for the minimum error. We need to find the minimum value out of all local minima. And you can see here we have a global minima and then the two local minima. And depending on where we start, we can arrive at different values for the minimum error. We need to find the global minimum value out of all local minima. And this can be a real challenge because if you're looking at just one of those loops, you run into the issue that you don't know whether there's other minima out there, minimal values, and if one of those is the global minimal value. And so this can be quite a challenge when we're programming and writing these, putting together these different models, is finding these different points, especially in a neural network. Again, it's not just a neural network that has that come up. That comes up in a lot of regular solutions in our different regression models. The gradient descent for a neural network is just a differentiation of its cost function. It can be written as gradient descent equals the theta j and then the differential of j over the differential of theta. Cost function j equals 1 over the total number we're going to do, and then you sum up the total number of the differences of the y of I minus mx of I plus b, where m and b is your slope and your intercept of your linear regression model. The difference is we're doing that linear regression model across all the different neural nodes and the different layers, and that's why you're summing them all up on there. And it still looks very similar, but it is done in a larger scale. The gradient descent for a neural network is just the differentiation of its cost function. In the equation, m is the weight of the layer and b is a constant called bias. And you'll see that a lot because like in a neural network you might have each node will have all the nodes from above going into it. So if you have 10 nodes going into it, you have to add all those nodes and they have a weight, the m value, and then the summation of all those nodes going in, all the values going in from the above layer, then has a bias in there, the bias weight that's added in. And then you get the full, you can see down here we have the gradient descent of the differential of j and the differential of theta equals a total number. And I'm not going to go too detailed on the actual formulas. We'll show that in the code. A lot of times these formulas are always being updated. So when you're writing code for this, it's important to know these formulas a little bit. If it comes up, you can understand why it's doing what it is, but there's more than one formula to compute this. And so as you start understanding these different formulas, you can start seeing how they fit and how one works better than another. These are the most basic formulas that are currently used today. And you can see here we form a nice little matrix with the 1 over n of I of 0 minus 2 x of I, y of I minus mx of I plus b. There's our linear regression kind of set up right in the middle of the formula. And then you have that with the 1 over n of I equals 0 minus 2 yi mxi plus b. So you're forming a matrix out of it. So as we continue looking at gradient descent for neural networks, in the following picture we are computing the errors for each layer separately, and to this gradient descent will be applied. We also know that each layer has a weight which is assigned to it. And so we have our total error at the end. And here's those nodes I was talking about. You have your input layer, it goes into a layer of algorithms. You use the error from those algorithms to program each one of those nodes. And one of the things they're not showing here is each input goes to each one of the nodes to sum it. So I guess in this particular image, the sum would be a single node. And then you have your layers. Each layer goes into the lower layer and so forth until you sum them up and you get a total error on the end. The weight will be different for each node in each layer. Consider a node in layer 3. The node will have an output which may differ from the desired output. So layer 3 has our predicted versus our actual wanted output on there. And then we create a weight equals a new weight. As a value of the predicted output depends on the weight applied to the layer, we can tweak it to get the desired output. We can similarly tweak the weight of each node in the layer. We use gradient descent on the cost function to get the best value of the weights, which is a variable in the cost function. Using the corrected values of the outermost layer, we can tweak the weight of the layer before that. This will help us minimize the error in the second last layer too. We keep using the corrected weight of layer to further tweak the weight of the layer before that and get the desired output from the network. This is called back propagation as we move backwards. So to kind of put that more in perspective, you have your output, you have all of your inputs. You know, maybe it's a picture with 1,000,000 pixels on it and you have 1,000,000 inputs. And it comes out and says it's a cat picture or a dog picture, so you might have just one output. Or maybe you have all your inputs and you're trying to figure out what the next predicted value for the stock market is. So you have a number coming out. We look at that error at the very end and we push it back to the layer right before it. And we kind of split it up between all the nodes in that layer. And each one of those nodes computes an error. Then all of those nodes push back their error to the layer before, and so forth. That's what backpropagation is it starts at the end and goes in reverse. So we've actually looked at a lot of stuff here as far as cost functions, and neural networks are probably the most labor intensive as cost functions because you're solving that cost function for each layer and for each node in the layer. They're all working together, so it gets very complicated. But the cost function is the same. We're still looking at the same thing even in a simple linear regression model. So let's go ahead and take a look at a demo on a cost function. And I'm going to do this in Python I'm using the Add Account and Navigator to open up a Jupyter Notebook in Chrome. We'll go up here in our Chrome setup and do a new Python 3. Give it a moment there. And so we're going to be looking at cost function. I'll go ahead and rename that. And let's go ahead and start by just importing our NumPy in our matplot library so we have a little view of what's going on here. And then I have a data set that has just a bunch of random points on it, kind of. And we'll go ahead and just bring that in. This is a simple NumPy load text because we put it as a text file. Probably could have put it as a comma separated file or whatever. And you can see it's just a bunch of pairs of numbers. We have 6, 11, 17, 5, 9, 2, whatever on there. And we can take that list of numbers on there that was pretty much randomly set up on this. And we'll go ahead and plot it so you can see what we're looking at. Run. And I would probably spend a little bit more time on here playing with this to see what the numbers are. These are just random numbers, so don't write too much into them. There's nothing fancy going on here. They do kind of group along a nice line. That's what we're going to look up at this graph. And let me switch this. This is sometimes we'll do graphs where we put the X's in to make it very clear that these are points on the thing. But let's just do a scatter plot on here. That's all this is. If you looked at the last one we had, we did a plot XY RX marker size 10. This plot would normally do lines, but we change it to RX and we put a marker size, and that's what gives it the nice little X's. But I like the scatter plot better, so we'll just do a scatter plot. And you can see the values kind of go from 5 to 22.5, 0 to 25 on the y-axis. And if we drew a line through here, which is what we're going to be working with, this line would have a y-intercept, our b number, and our slope m. And we'd want to just fit this with the least amount of error between all this data. And so we're going to go ahead and create, and bear with me on this just for a minute. This part gets just a little confusing here. Oops, I left a t off theta. We're going to take our theta equals our NumPy zeros. We're just going to create a zero array, and it's 2 by 1, so it's just one row that's 2 wide. And our new x, NumPy delete points, NumPy s 1 to 1, insert new x 0, 1, axis equals 1, learning rate equals 0, initial b equals 0, and iterates 1500 times. What this means is that we're going to start with a flat line that equals the x-axis. This is y equals 0 times x plus 0. There's our m, there's our b, there's our slope, there's our intercept. And the learning rate is going to be looking at going 0.01 in its steps to find the minimal error. Now we're not talking, this is the distance between this line, what it predicts, which is going to be very small here on this point. Let me just, there we go. You'll see this point here, here's the distance, because right now we have a flat line. Our flat line, let me just draw that in there for you, goes here, and we look at this, the squared value of this difference here versus the squared value of this distance here, the squared value of this distance, and we're going to look at all these errors. And so when we look at all this, some of these errors, that is the error we're looking at, is the predicted, which is all going to be 0. So we can just put 0 squared, and the actual. And actually did this backwards. So the actual would be here, would be y square, y minus 0 squared. So y is our actual output, and then 0 is our predicted output the first time through, because we set everything equal to 0. Usually you guess a little bit more in the first one. I would take, when I write a script on here, it pulls the first 2 data points in. So maybe pull these 2 data in, and it says, okay, here's our line with our first 2 data points. And then it starts looking for, then it goes through and looks for the error on there. But this is fine. We start with 0 on here. And so let's go ahead and load this up. So we have our theta, which is going to track the differences. It starts off with pretty much just a simple 2 points, our first beta and our first slope and our first intercept. And so we need to start putting together a cost function. And again, a lot of this stuff is in your scikit learning packages to find minimums and stuff like that. And so our cost function goes in here and it says m equals the length of the points. We're going to look at all our points. Y equals delete points numpy s. So we're going to kind of skip through on looking at the y and how they compare. And we end up with a, let's see, here we go. If we look at next, 1 over 2 times n times numpy dot sum. This is just summing all of these values up for us. And we have our numpy dot power, numpy subtract, numpy dot x, theta. Numpy is such a powerful array. It's just so fun to play with. It's a little hard to go backwards and dissect this, but this is just our cost function on here. It's what we expected and what we're actually going to get. And so when we come out and we print this, we come out and we look at this, we go, okay, so this has an error of 32. That's what that number is. That's just the first time through. The error is the summation of all those lines to the x-axis on there. And we're going to go ahead and do theta second equals numpy array. And it's going to be the same thing, but we're going to, let me just run this, guessing at a second number based on the first number, and it gets an error of 54. Really, this is telling us, because we're not actually going through the implementation of 0.01. Remember up here, we're going to iterate learning rate of 0.01. We just went in and said, hey, what happens if I take this error up here and I adjust for it based on this error? What do I get? Well, my new error is 54. It actually got worse. That's why you need a gradient descent. When we play high-low, you might look at it and just pick some random huge number. You end up with that kind of return on there. And there's a lot of ways. There's actually a lot of math that can go into this. You might do something where, okay, if this is this error, maybe we would try a value on each side of that error that is a quarter of it. So there's some math in here that they do when they do the optimization in scikit, which really does a good job zeroing in on this. But to understand it, it's better to go ahead and do an actual gradient descent. And so we're going to go ahead here and do cost history. This is just kind of fun. Equals the numpy zeros iteration. And then we have our theta history, theta second. And so it's going to have our first theta. Oops. Yeah, that's right. Theta history, which we start off by just putting in the number of iterations. It's going to go down. And we're going to have our theta second, which is we're going to start stacking on them and tracking them. And that's really not what we're interested in. We're interested in the cost history. But it's kind of fun to generate these values down here. The cost history is what we're looking at. And we start with iterating through the total number of iterations. That's what we set up above, which was what, 1,500? Yeah, there it is. 1,500. So we're going to go through 1,500 iterations. We're going to do our prediction, which equals numpy dot product x theta second. So right here, we're just creating what we guess the new number is based on, in this case, our theta second is our slope on there. That's why we're doing the dot product, slope and intercept. Theta second, so we create our new theta second minus 1/2 times the learning rate. There's our 0.005 times our x dot t dot product, which is a prediction minus y. Now, this code looks a little confusing. When you're digging through it and you go back, you'll see how the numbers match up. Playing with NumPy arrays in itself is a lot of fun, and once you start playing with them, looking at somebody else's code is really hard to do. The guys in the back put this together for me. Building your own code just becomes like a very creative, fun challenge to see how it all fits and how you flip the numbers around. The .t means I'm transposing it in a NumPy array, so I'm turning it from columns to rows. And we're just going to take our theta history and our iteration and create a theta history, and then here's our temp cost. This is the one that's really important. It's going to be 1 over 2 times n NumPy sum, and then we have our NumPy power, NumPy subtract, NumPy dot, x theta second of y2. So we're looking at the cost of each iteration on there. And this formula comes from here, where we're summing all the different values and finding our error. And then we're adding it onto theta history. And so here is our slope, here is our intercept, and it just keeps guessing for each one of these. And we could look at pieces of the history, and you can see it slowly changes on here. A lot of times I'll do something like this and just look at the end of the data, let's look at the last 20. Run that. And in the last 20, you can see that 6210, 3261, 602, this becomes a 5. A 0 is kind of bouncing back and forth on the slope, and it kind of zeroes in to the 630 down here. 629, 630. It gets closer and closer to this one answer on there. But that's not the part we want to look at. The part we want to look at is there we go, is the cost history. We want to take a look. Remember, we're dumping on here our temp cost, and we're just going to keep adding it on to the cost history. So let's go ahead and run that. There we go. And you can see we have a nice curve here. And what you want to notice on this curve, what's really important, one of the things a lot of programs look for would be the elbow. Not as important on this particular graph. And somewhere right around here, we jump from 800 to 1400 with almost no improvement. Look how small this improvement is. A lot of times, this improvement, as you get down to here, is less than the actual error that we have coming off of it. And so when you're looking at statistics, if my error is something like this, here's my error, that means that these values right here supposedly are getting better, but they might not be. So when you have, when you start looking at the craziness of data coming in and how it varies, at some point you cut it off and you say, okay, right here we got to cut it off, and you might actually find an intercept here. Usually though, on the curve like this, I would look around 800 to 1000. Around 1000 you really are just bouncing back and forth between the bottom, and in this size of data, that is way beyond what this size of data would actually be able to predict. And that's why you look at these things. You want to know where your points are, and there's a lot of algorithms to guess where this best spot is. But as far as understanding how we minimize the error, you can see we use a basic setup to do our gradient descent to find the minimal error. Finding that bottom of our, whoops, that's a horrible loop. Finding that bottom of this graph right here. How close can we get to 0? There might be our 0 line. So we've gone through a lot. We went through a quick demo to show you what that looks like and what's going on in that minimize routine, using the most commonly used gradient descent with a linear model. And we talked a little bit about how that fits in with neural networks, pointed out that there's a global and local minimals, all important things to understand when you start looking at minimizing the error. One of the most common used tools to train our models in our machine learning kits.
When we talk about the principal component analysis, we're going to cover dimensionality reduction, principal component analysis, what is it, important PCA terminologies, and you'll see it abbreviated normally as PCA, principal component analysis, PCA properties, PCA example, and then we'll pull up some Python code in our Jupyter Notebook and have some hands-on demo on the PCA and how it's used. Dimensionality reduction. Dimensionality reduction refers to the technique that reduces the number of input variables in a data set. And so you can see on the table on the right shows the orders made at an automobile parts retailer. The retailer sells different automobile parts from different companies. And you can see we have company BPAX, Isomax, and they have the item, the tire, the axle, an order ID, a price number, and a quantity. In order to predict the future sales, we find out that using correlation analysis that we just need 3 attributes. Therefore, we have reduced the number of attributes from 5 to 3. And clearly we don't really care about the part number. I don't think the part number would have an effect on how many tires are bought. And even the store, who's buying them, probably does not have an effect on that. In this case, that's what they've actually done, is remove those. And we just have the item, the tire, the price, and the quantity. One of the things you should be taking away from this is, in the scheme of things, we are in the descriptive phase. We're describing the data, and we're pre-processing the data. What can we do to clean it up? Why dimensionality reduction? Well, number one, less dimensions for a given data set means less computation or training time. That can be really important if you're trying a number of different models and you're rerunning them over and over again. And even if you have 7 gigabytes of data, that can start taking days to go through all those different models. So this is huge. This is probably the hugest part as far as reducing our data set. Redundancy is removed after removing similar entries from the data set. Again, pre-processing, some of our models, like a neural network, if you put in 2 of the same data, it might give them a higher weight than they would if it was just one. So we want to get rid of that redundancy. It also increases the processing time if you have multiple data coming in. Space required to store the data is reduced. So if we're committing this into a big data pool, we might not send the company that bought it. Why would we want to store 2 whole extra columns when we add it into that pool of data? Makes the data easy for plotting in 2D and 3D plots. This is my favorite part. Very important. You're in your shareholder meeting. You want to be able to give them a really good, clear, and simplified version. You want to reduce it down to something people can take in. It helps to find out the most significant features and skip the rest, which also comes in post-scribing. Leads to better human interpretation. That kind of goes with number 4, where it makes data easy for plotting. You have a better interpretation when we're looking at it. Principal component analysis. So what is it? Principal component analysis is a technique for reducing the dimensionality of data sets, increasing interpretability, but at the same time minimizing information loss. So we take some very complex data set with lots of variables, we run it through the PCA, we reduce the variables. We end up with a reduced variable setup. This is very confusing to look at because if you look at the end result, we have the different colors all lined up. So what we're going to take a look at is, let's say we have a picture here. Let's say you are asked to take a picture of some toddlers and you are deciding which angle would be the best to take the picture from. So if we come up here and we look at this, we say, okay, this is one angle. We get the back of a lot of heads, not many faces. So we'll do it from here. We might get the one person up front smiling. A lot of the people in the class are missing, so we have a huge amount off to the right of blank space. Maybe from up here, again, we have the back of someone's head. And it turns out that the best angle to click the picture from might be this bottom left angle. You look at it and you say, hey, that makes sense. It's a good configuration of all the people in the picture. Now, when we're talking about data, it's not, you really can't do it by what you think is going to be the best. We need to have some kind of mathematical formula so it's consistent and so it makes sense in the back end. One of the projects I worked on many years ago had something similar to the iris. And if you've ever done the iris data set, it's probably one of the most common ones out there, where they have the flower and they're measuring the stamen in the petals, and they have width and they have length of the petal. Instead of putting through the width and the length of the petal, we could just as easily do the width to length ratio. We can divide the width by the length and you get a single number where you had 2. That's the kind of idea that's going on into this. in pre-processing and looking at what we can do to bring the data down. A very simplified example on my iris petal example. When we look at the similarity in PCA, we find the best picture or projection of the data points. And so when we look down at from one angle, we've drawn a line down there, we can see these data points based on, in this case, just two variables. Now keep in mind, we're usually talking about 36, 40 variables. Almost all of your business models usually have about 26 to 27 different variables they're looking at. Same thing with like a bank loan model. We're talking 26 to 36 different variables they're looking at that are going in. So what we want to do is we want to find the best view. In this case, we're just looking at the XY. We look down at it, and we have our second idea, PC2. And again, we're looking at the XY, this time from a different direction. Here, for our ease, we can consider that we get two principal components, namely PC1 and PC2. Comparing both the principal components, we find the data points are sufficiently spaced in PC1. So if you look at what we got here, we have PC1. You can see along the line how the data points are spaced versus the spacing in PC2. And that's what they're coming up with. What is going to give us the best look for these data points when we combine them? And we're looking at them from just a single angle. Whereas in PC2, they are less spaced, which makes the observation and further calculations much more difficult. Therefore, we accept the PC1 and not the PC2 as the data points are more spaced. Now, obviously, the back-end calculations are a little bit more complicated when we get into the math of how they decide what is more valuable. This gives you an idea, though, that when we're talking about this, we're talking about the perspective, which would help in understanding how PCA analysis works. What we want to go ahead and do is dive into the important terminologies under PCA. And important terminologies are views, the perspective through which data points are observed. And so you'll hear that if someone's talking about a PCA presentation and they're not taking the time to reduce it to something that the average person, shareholders, can understand, you might hear them refer to it as the different views. What view are we taking? Dimension, number of columns in a data set are called the dimensions of that data set. And we talked about, you'll hear features, dimensions. Now I was talking about features. There's usually, when you're running a business, you're talking 25, 26, 27 different features, minimal. And then you have the principal component, new variables that are constructed as linear combinations or mixtures of the initial variables. Principal component is very important. It's a combination. If you remember my flower example, it would be the width over the length of the petal as opposed to putting both width and length in. You just put in the ratio instead, which is a single number versus two separate numbers. Projections. The perpendicular distance between the principal component and the data points. And that goes to that line we had earlier. It's that right angle line of where how all those points fall onto the line. Important properties. Important properties. Number of principal components is always less than or equal to the number of attributes. That just makes common sense. You're not going to do 10 principal properties with only 3 features. You're trying to reduce them, so it's just kind of goofy, but it is important to remember that. People will throw weird code out there and just randomly do stuff instead of really thinking it through. Principal components are orthogonal. And this is what we're talking about, that right angle from the line. When we do PC1, we're looking at how those points fall on to that line. Same thing with PC2. And we want to make sure that PC1 does not equal PC2. We don't want to have the same 2 principal points when we do 2 points. The priority of principal components decreases as their numbers increase. This is important to understand. If you're going to create one principal component, everything is summarized into that one component. As we go to 2 components, the priority, how much it holds value, decreases as we go down. So if you have 5 different points, each one of those points is going to have less value than just the one point, which has everything summarized in it. How PCA works. I said there was more in the back end. When we talk about the math, this is what we're talking about, is how does it actually work. So now we have understanding that you're looking at a perspective. Now we want to see how that math side works. PCA performs the following operations in order to evaluate the principal components for a given data set. First, we start with the standardization. Then we have a covariance matrix computation. And we use that to generate our igene vectors and igene values, which is the feature vector. And if you remember, the igene vector is like a translation for moving the data from x equals 1 to x equals 2 or whatever, altering it. And the igene value is the final value that we generate. When we talk about standardization, the main aim of this step is to standardize the range of the attributes so that each one of them lie within similar boundaries. This process involves removal of the mean from the variable values and scaling the data with respect to the standard deviation. And you can see here we have z equals the variable values minus the mean over the standard deviation. The covariance matrix computation. Covariance matrix is used to express the correlation between any two or more attributes in multi-dimensional data set. The covariance matrix has the entries as the variance and the covariance of the attribute values. The variance is denoted by var and the covariance is denoted by cov. On the right, we can see the covariance matrix for two attributes and their values. When we do a hands-on look at the code, we'll do a display of this so you can see what we're talking about and what that looks like. For now, you can just notice that this is a matrix that we're generating with the variance and then the covariance of x to y. On the right side, we can see the covariance table for more than two attributes in a multi-dimensional data set. And this is what I was talking about. We usually are looking at not just one feature or two features. We're usually looking at 25, 30 features going on. And so if we do a setup like this, we should see all those different features as the different variables. Covariance matrix tells us how the two or more variables are related. Positive covariance indicate that the value of one variable is directly proportional to the other variable. Negative covariance indicate that the value of one variable is inversely proportional to the other variable. That is always important to note whenever we're doing any of these matrices, that we're going to be looking at that positive and negative, whether it's inverted or not. And then we have the igene values and the igene vectors. Igene values and igene vectors are the mathematical value that are extracted from the covariance table. They are responsible for the generation of a new set of variables from the old set of variables, which further lead to the construction of the principal components. Igene vectors do not change directions after linear transformation. Igene values are the scalars or the magnitude of the igene vectors. And again, this is just transforming that data. So we're going to change the vector b to the b prime as denoted on the chart. And so when we have like multiple variables, how do we calculate that new variable? And then we have feature vectors. Feature vectors is simply a matrix that has igene vectors of the components that we decide to keep as the columns. Here we decide whether we must keep or discard the less significant principal components that we have generated in the above steps. This becomes really important as we start looking at the back end of this, and we'll do this in the demo, but one of the more important steps to understand. And so we have the PCA example. Consider matrix X with n rows or observations and k columns or variables. Now for this matrix, we would construct a variable space with as many dimensions as the variable. But for our simplicity, let's consider this 3 dimensions for now. Now each observation, row of the matrix X, is placed in the k-dimensional variable space, such that the rows in the data table form a swarm of points in this space. Now we find the mean of all the observations and then place it along the data points on the plot. The first principal component is a line that best accounts for the shape of the point swarm. It represents the maximal variance direction in the data. Each observation may be projected onto this line in order to get a coordinate value along the PC1. This value is known as a score. Usually only one principal component is insufficient to model the systematic variation for a data set. Thus, a second principal axis is created. The second principal component is oriented such that it reflects the second largest source of variation in the data. While being orthogonal to PC1, PC2 also passes through the average point. Let's go ahead and pull this up and just see what that means inside our Python scripting. I'm going to use the Anaconda Navigator, and I will be in Python 3.6 for this example. I believe there's even like a 3.9 out. I tend to stay in 3.6 because a lot of the models I use, especially with the neural networks, are stable in 3.6. And then we open up our Jupyter. I'm in Chrome, and we go ahead and create a new Python 3. And for ease of use, our team in the back was nice enough to put this together for me. And we'll go ahead and start with the libraries. The first thing I like to do whenever I'm looking at any new setup, well, you know what, let's do the libraries first. We're going to do our basic libraries, which is matplotlib library, the PLT from the matplotlib library. Pandas, our data frame, PD, NumPy, our numbers array, NP, Seaborn for graphing, SNS, that goes with the plot that actually sits on matplotlib library, so the Seaborn sits on there. And then we have our ampersand, because we're in Jupyter Notebook, matplotlib library inline. The newer version actually doesn't require that, but I put it in there anyway just because I'm so used to it. And then we want to go ahead and take a look at the data. And in this case, we're going to pull in, certainly you can have lots of fun with different data, but we're going to use the cancer data set. And one of the reasons the cancer data set is it has like 36, 35 different features. So it's kind of fun to use that as our base for this. And we'll go ahead and run this and look at our keys. And the first thing we notice in our keys for the cancer data set is we have our data, we have our target, our frame, target names, description, feature names, and file name. So what we're looking for in all this is, well, let's take a look at the description. Let's go in here and pull up the description on here. I'm not going to spend a huge amount of time on the description because we don't want to get into a medical domain. We want to focus on our PCA setup. What's important is you start looking at what the different attributes are, what they mean. If you were in the medical field, you'd want to note all these different things, what they're measuring, where it's coming from. You can actually see the actual different measurements they're taking. No missing attributes. We page all the way to the bottom. And you're going to have your data, in this case our target. And if you dig deep enough to the target, let's actually do this. Let's go ahead and print target names. Real quick here, I always like to just take a look and see what's on the other end of this. Target names. Run that. And so the target name is it malignant or is it benign? So in other words, is this dangerous growth or is it something we don't have to worry about? That's the bottom line with the cancer in this case. And then we can go ahead and load our data. And you know what, let me go up just a notch here for easy of reading. It's hard to get that just right. I guess I'll have to do. So let's go ahead and look at our data. We're going to use our pandas, and we're going to go ahead and do our data frame. It's going to equal cancer data. Columns equals cancer, feature equals feature names. So remember up here, we already loaded the names up of the features in there. What is going to come out of this? Let me just see if I can get to that. It's at the top of target names. That's just this list of names here in the setup. And we can go ahead and run this code, and it'll print the head. And you can see here we have the mean radius, the mean texture, mean perimeter. I don't know about you, this is a wonderful data set if you're playing with it, because like most of the data that comes in, half the time we don't even know what we're looking at. We're just handed a bunch of stuff as a data scientist going, what the heck is this? And so this is a good place to start because this has a number of different features in there and we have no idea what these features means or where they come from, We want to just look at the data and figure that out. And now we actually are getting into the PCA side of it. As we've noticed before, it is difficult to visualize high-dimensional data. We can use PCA to find the first two principal components and visualize the data, this new two-dimensional space, with a single scatter plot. Before we do this, we need to go ahead and scale our data. Now, I haven't run this to see if you really have to scale the data on this, but as just a general runtime, I almost do that as the first step of any modeling, even if it's pre-modeling as we're doing here. In neural networks, that is so important. With PCA visualization, it's already going to scale it when we do the means and deviation inside the PCA. But just in case, it's always good to scale it. And then we're going to take our PCA with the scikit-learn uses very similar process to other pre-processing functions that come with scikit-learn. We instantiate a PCA object, find the principal components using the fit method, then apply the rotation and dimensionality reduction by calling transform. We can also specify how many components we want to keep when creating the PCA object. And so the code for this, oops, getting a little bit ahead. Let me go ahead and run this code. So the code for this is from sklearn decomposition import PCA. PCA equals PCA and components equals 2. And that's really important to note that because we're only going to want to look at 2 components. I would never go over 4 components, especially if you're going to demo this with somebody else. If you're showing this to the shareholders, the whole idea is to reduce it to something people can see. And then the PCA fit, we're going to is going to take the scaled data that we generated up here, and then you can see we've created our PCA model with in components equals 2. Now, whenever I use a new tool, I like to go in there and actually see what I'm using. So let's go to the scikit webpage for the PCA. And you can see in here, here's our call statement. It describes what all the different setups you have on there. Probably the biggest one to look at would be, well, the biggest one is your components. How many components do you want, which you have to put in there pretty much. And then you also might look at the SVD solver. It's on auto right now, but you can override that and do different things with it. It does a pretty good job as it is. And if we go down, all the way down to, here we go, to our methods, if you notice we have fit, and we have fit transform. Nowhere in here is predict, because this is not used for prediction. It's used to look at the data. Again, we're in the describe setup. We're fitting the data. We're taking a look at it. We've already looked at our minimum maximum. We've already looked at what's in each quarter. We've done a full description of the data. This is part of describing the data. That's the biggest thing I take away when I come zooming in here. And of course, they have examples of it down here if you forget. And the biggest one, of course, is the number of components. And then, I mean, the rest you can play with. The actual solver, whether you're doing a full or randomized, there's different things. It does pretty good on the auto. And now we can transform this data to its first 2 principal components. And so we have our XPCA. We're going to set that equal to PCA transform scaled data. So there we go. There's our first transformation. And let's just go ahead and print the scaled data shape and the XPCA data shape. And the reason we want to do this is just to show us what's going on here. We've taken 30 features. I think I said 36 or something like that, but it's 30. And we've compressed it down to 2 features. And we decided we wanted 2 features, and that's where this comes from. We still have 569 data sets. I mean data rows, not data sets. We still have 569 rows of data, but instead of computing 30 features, we're now only doing our model on 2 features. So let's go ahead and plot these and take a look and see what's going on. And we're just going to use our PLT figure. We're going to set the figure size on here. Here's our scatter plot, XPCA, X underscore PCA of 1. These are our two different perceptions we're using. And then you'll see right here, C for color, cancer equals target. And so remember, we have 0, we have 1. And if I remember correctly, 0 was malignant, 1 was benign. So everything in the 0 column is going to be one color, and the other color is going to be 1. And then we're going to use the plasma map, just kind of telling you what color it is. Add some labels, first principal component, second principal component. And we'll go ahead and run this. And you can see here, instead of having a chart, one of those heat maps with 30 different columns in it, we can look at this and say, hey, this one actually did a pretty good job of separating the data. And a couple things when I'm looking at this that I notice is, first, we have a very clear area where it's clumped together, where it's going to be benign. And we have a huge area, it's still clumped together, more spread out, where it's going to be malignant. Or I think I had that backwards. And then in the middle, because we're dealing with something, in this particular case, cancer, we would try to separate, I would be exploring how to separate this middle group out. In other words, there's an area where everything overlaps, and we're not going to have a clear result on it. Just because those are the people you want to go in there and have extra tests, or treat it differently, versus going in and saying just cutting into the cancer so that the body absorbs it and it dissipates, versus actively going in there, removing it, testing it, going through chemo and all the different things. That's a big difference, you know, as far as what's going to happen here. And that middle line where they overlap is going to be huge. That's domain specific. Going back to the data, we can see here, clearly by using these two components, we can easily separate these two classes. So the next step is, what does that mean? Interpreting the components. Unfortunately, with this great power of dimensionality reduction comes the cost of not being able to easily understand what these components represent. I don't know what principal component 1 represents, or second principal. The components correspond to combinations of original features. The components themselves are stored as an attribute of the filtered PCA object. And so when we look at that, we can go ahead and look at the PCA components. This is in our model we built. We've trained it. We can run that, and you can see here's the actual components. It's the two components each have their own array. And within the array, you can see what the scores they're using. And these actually give weight to what features are doing what. So in this NumPy matrix array, each row represents a principal component, and each column relates back to the original features. What's really neat about this is we can now go in reverse and drop this onto a heat map and start seeing what this means. And so let me go ahead and just put this down. Oops, I already got it down here. We'll go ahead and put this in here. We're going to use our dfcomp data frame, and we do our PCA components. And I want you to notice how easy this is. We're going to set our columns equal to cancer feature names. That just makes it really easy. And we're dumping it into a data frame. What's neat about a data frame is when we get to Seaborn, it will pull that data frame apart and set it up for us the way we want. And so we're just going to do the Seaborn heat map of our data frame composition, and we'll use the plasma coloring. And it creates a nice little color graph here. You can see we have the mean radius and all the different features along the bottom. On the right, we have a scale, so we can see we have the dark colors all the way to the really light colors, which are what's really shining there. This is like the primary stuff we want to look at. So this heat map and the color bar basically represent the correlation between the various features and the principal component itself. So, you know, very powerful map to look at. And then you can go in here, and we might notice that the mean radius, look how on the bottom of the map it is. on some of this. So you have some interesting correlations here that change the variations on that and what means what. This is more when you get to PostScribe, you can also use this to try to guess as what these things mean and what you want to change to get a better result.
Hi everyone. Welcome to this exciting session by Simplilearn. Today, we have a really interesting topic for you. In this video, we'll be analyzing the upcoming United States presidential election using Twitter sentiment analysis in Python. In the course of this session, we will understand in brief about the upcoming election, the candidates fighting the 2020 US election, and throw light on the result of the 2016 US election. We'll look at the election forecast by some of the popular news agencies, as well as poll analysis websites such as 538. Before we begin, I want to make it clear that this video is solely for learning purposes. We at Simplilearn do not lean towards any party in the United States or are biased towards any candidate. The analysis is based on what people have tweeted, and we will understand the mood and sentiment of the public. The main objective of this video is to help you understand how to extract tweets from Twitter handles using Python libraries, store it in a CSV file, and perform textual analysis. The results obtained are purely based on the data that we have collected. Let's begin. The battle for the 2020 US presidential election has begun, with the 59th United States presidential election scheduled to be held on the 3rd of November 2020. This will decide who will be in the White House for the next 4 years. All 435 seats in the United States House of Representatives, 35 of the 100 seats in the United States Senate, and office of the President of the United States will be contested. Both the Republican Party and the Democratic Party have nominated their respective president and vice presidential candidates. The incumbent president, Donald Trump, is the Republican nominee, while the 47th Vice President of the United States, Joe Biden, is the Democratic Party's nominee. The current Vice President, Mike Pence, is the Republican Party's vice presidential nominee and is running for a second term in office. Senator Kamala Harris of California was chosen by Joe Biden as his running mate on 11th of August 2020. Now, let's see the results of the last US presidential election in 2016. The Republican ticket of businessman Donald Trump and Indiana Governor Mike Pence had defeated the Democratic ticket of former Secretary of State Hillary Clinton and US Senator from Virginia Tim Kaine. Donald Trump received a total of 304 electoral votes, while Hillary Clinton got 227 electoral votes. A significant number of central states in the United States were swept by the Republican Party. It was surprising to see that Donald Trump getting nearly 46.4% popular vote as compared to Hillary Clinton, who got 48.5% votes. Donald Trump's victory came after crucial wins in the battleground states of Florida, Ohio, Iowa, North Carolina, and Pennsylvania. Will Donald Trump be re-elected to the White House, or are we going to see a new president and a vice president of the United States is the big question. Let's see what our pollsters have to say and what has been their forecast for the upcoming election. According to 538, Donald Trump has not gained ground since the final debate on 22nd of October. At this moment, Joe Biden is favored to win the election and he leads in both national and state polls. The Economist is analyzing polling, economic and demographic data to predict the US elections. Their model thinks Joe Biden is very likely to beat Donald Trump in the Electoral College. As per their forecast, Joe Biden has 96% chance of winning the Electoral College, and there's 99% chance of Biden winning the most votes. The Democrats have 75% chance of controlling the Senate, while the Republicans have around 25%. The Democrats are highly likely to keep their majority in the House of Representatives. Now, according to The Guardian, Joe Biden is leading Donald Trump in the national polls for the presidential election. But to keep in mind, this does not guarantee the Democratic candidate Joe Biden's victory. Hillary Clinton also had a clear lead over Donald Trump in the polls for almost the entire 2016 campaign. She ended up losing the Electoral College. Now the BBC forecast tells that Biden is leading national presidential polls with 51%. He has hovered around 50% in recent months and has had a 10-point lead on occasions. So clearly, Joe Biden is set to be the next US president. Let's wait and watch what happens on the 3rd of November. The voters of America will decide on 3rd of November whether Donald Trump remains in the White House for another 4 years. Let's perform a Twitter sentiment analysis to understand the sentiments of people tweeting about Donald Trump and Joe Biden by tagging them in their tweets. We have our code implemented already. I'll run through each line of code and explain our analysis in detail. The objective is to check the polarity of each tweet to figure out if it's positive, negative, or neutral. We'll compare the tweets of Donald Trump and Joe Biden to see who people are favoring the most. Finally, we learn to create a word cloud. I have already extracted the tweets and stored them in 2 separate CSV files. It takes some time to fetch 10,000 tweets, hence it won't be possible for me to show it to you live. If you want to know how we extracted the tweets for Donald Trump and Joe Biden, then please put your email IDs in the comment section of the video. We'll share the code file and the source file with you. Now you would need to install the Tweepy library, fetch the Twitter keys and access tokens, and then authenticate the Twitter API. I've extracted 5,000 tweets each for Donald Trump and Joe Biden, converted it into a data frame, and stored it in a CSV file. So let me open and show you both the files. So here is my data set for Donald Trump. On the top you can see Trump_data 5000, which means there are 5000 tweets here. The first column has the number of tweets. It starts from 0 and goes all the way to 4999. The next column is the text column, which has the content of the tweet. You can see they have tagged @real Donald Trump. There are links as well. There are special characters like emoticons. And the third column is the user, which means it's the username who had put that tweet. Similarly, I have another data for Biden. You can see these are for Joe Biden, and here you can see the content. They have tagged Kamala Harris also. Similarly, we have the username. Now let me take you straight to my Jupyter notebook where I have implemented the code. Okay, so first and foremost, let's import all the required libraries. So we have the NumPy library for numerical computation. Then we have the Pandas library for data manipulation. Next we are importing 2 libraries, Matplotlib and Seaborn, for data visualization. Then we have TextBlob and word cloud to get the sentiment and to build the word cloud. And finally we are importing the Plotly library for creating graphs. Let me run this cell. In the current cell, we'll import the datasets using read_CSV function present in the Pandas library. So I have passed in my location where the data file is, so I have placed it on my desktop, and the index_col parameter or column parameter refers to the columns to be used as the row labels of the data frame. Here 0 indicates that the first column will be used as row labels. Let me run it. Okay, now we have imported both the data files. Let me go ahead and print the shape of one of the data frames. So I'll write print. Let's say we'll check the shape of Biden data frame. So I'll write print Biden.shape. I'll hit shift enter. You can see there are 5000 rows and there are 2 columns. One is the text column and the next column is the user column. Now let me go ahead and print the head of the datasets. So the head function will return the first 5 rows. I'll write Trump.head. You can see these are the first 5 rows from the Trump data frame. And similarly, if you want to check for Biden, I can write Biden.head. You can see it here. Now you can also use the info method. So let me show you that. You can write Trump.info, and this is the result. So it tells there are 5000 entries from 0 to 4999. There are 2 columns, and these are the number of rows, and similarly you have the data types. Okay, moving ahead, in the next cell I am displaying the 200th tweet present in the Trump data frame. So I have my data frame name mentioned, then I have my text column, and inside one more square bracket I have put 200, which means I want to see what's there in the 200th row. If I hit enter, so you can see this was the tweet: fake shit, fake president. Next, let me show you the tweet number 1000 for Biden. So I'll write Biden, and inside square brackets I'll give the text column, and the number is 1000. If I hit shift enter, so this is the tweet. Now the text blob function is used in natural language processing. The sentiment property returns a named tuple in the form of sentiment, in brackets, polarity and subjectivity. Let's check the sentiment of the 200th tweet made for Donald Trump. If I hit shift enter, you can see this was the polarity. Now minus 0.399 means the polarity was negative, and you can see the subjectivity is around 0.933. Similarly, let's check for Biden's tweet number 1000. So I'll write text blob, which is my function name, and inside brackets I'll give Biden, then pass in my column name, that is text, and I'll give the row number, which is 1000, and then I'll give the parameter or the attribute sentiment. If I hit shift enter, you can see the polarity and the subjectivity. Now moving ahead, here I have defined a function that will add another column called polarity to our two data frames, Trump and Biden. Let me run this. Okay. In the next cell, I have used the apply function that will return the polarity based on the tweets. You can see we have the apply function. This might take some time to run it. Okay, we are done now. Let me now display the top 5 rows of the data frame. So what I'll do is I'll click on this cell, go to insert, and I'll hit insert cell below. Let's do one more. Okay, now here I'll display the head of the data frame once again so that you can see the polarity column added. You can see it here. So for Donald Trump, we have the polarity. You can see the tweet and the polarity. Now 0.0, which means these are neutral, minus is negative, and anything that's in positive value indicates it's a positive tweet or it has positive polarity. Similarly, let's see for Biden. I'll write Biden.head. Okay, so here you can see the polarity for Biden. Now this 0.5 means it's a positive tweet. Okay. Now I want to create another column called expression, where we will classify the tweets as positive, negative or neutral based on the polarity value. So I have used the np.where function, and the condition we have here is if polarity is greater than 0, it's a positive tweet, else if it is less than 0, it's a negative tweet, and if the polarity is equal to 0, it means it's a neutral tweet. Let me run this. Okay, so here you can see we have the column called expression, and it has classified the polarity based on negative, neutral as well as positive. Similarly, let's do the same for Biden data frame as well. Okay. Before moving ahead, if you want to get access to the source code and the datasets we have used in this demo, then please put your email address in the chat section. We'll send it to you via mail. Also, please subscribe to Simplilearn channel and hit the bell icon to never miss an update from Simplilearn. In the next cell of code, we have another function that will basically help us creating a bar plot based on the expression column from both the data frames. So this is my user-defined function name, and it has two parameters, reviews and title. You can see we have grouped the expression column and found out the count using the count function. Then we have created or converted it into a list. Similarly, below you can see here we have defined the color for the bars using RGB values. Now let me run it. Okay, so we have successfully created our user defined function. Now let me go ahead and call the function and pass in my two parameters, reviews and title. So here we have the function name, and under reviews we have the data frame name Trump, and the title we have given as analysis for Trump. Let me run this. Okay, so you can see we have a horizontal bar plot. On the top you can see the title of the plot, which is analysis for Trump, and as per the tweets it has classified as positive, neutral or negative. If I hover over, you can see there were 2,831 neutral tweets, 1,211 positive tweets, and similarly there were 958 negative tweets for Donald Trump. Now let me call that function once again. So I'll write exp_graph, which is my function name. Then I'll pass in my parameters. This time I'll take Biden, and the title I'll put is analysis for Biden. If I run it, okay, you can see the plot for Biden now. If I hover over, there were 1,290 positive tweets for Biden and 747 negative tweets. Okay, let's scroll down. Now let me check the number of rows that have polarity equal to 0, the number of rows that have polarity less than 0 and greater than 0 for both the data frames using the dot shape attribute. So first we have for Trump, now equal to 0 means we are checking the total number of neutral tweets. You can see the result. Now let's check for Biden. We have the result below. Let me run it. Okay. Now we'll drop those columns that have a polarity equal to 0 from both the data frames and display the shape. You can see we have the condition mentioned, and we have also used the drop function. So all the neutral tweets will be deleted, and I'm printing the shape of the data frame. There you go. So out of the 5,000 tweet, it has deleted all the neutral tweets or dropped all the neutral tweets, and this is the final result. In the current cell, we have defined another function called balanced_data. Now this will help us get an equal number of rows and columns and delete a specified number of rows. Let me run it. Alright. Now I'll call that function to delete 169 rows from the Trump's data frame and 37 rows from Biden's data frame. This will help us subset the data frames. You can see we have now 2000 tweets from each of the data frames. Up next, we'll create some visualizations to analyze the textual data. So first, I'm using the Seaborn library and creating a distribution plot for Donald Trump. If I hit Shift Enter, you can see this is the distribution plot. There are bars at the back and there's a trend line. Okay. Similarly, let me now create a box plot. So this is a box plot. Here you can see there are some outliers. Now let me add a few cells below so that I can show that plot for Biden. So I'll write SNS dot, I'll use the function dist plot, and under dist plot I'll give Biden underscore subset, and I'll pass in my column that is polarity. Let me run it. So this is the distribution plot for Joe Biden. And now let me also create the box plot. So I'll use the Seaborn library and the box plot function. I'll pass in my data frame, which is Biden underscore subset, and I'll give my column name, that is polarity. I'll run it. So here you can see the box plot for Joe Biden. Let me tell you how you can create a cross table using the group by function. So before coming to this cell of code, let me insert cell above. Okay. Now using group by function, you can create a cross table. So I'll use the Trump underscore subset data frame, and then I'll give my group by function, and inside group by function I'll give my expression column, and I'll count the number of expressions. If I run this, you can see this is a cross table. Similarly, you can do it for Joe Biden as well. I'll just replace the names. I'll write Biden, and the rest is the same. You can see this is the cross table for Biden underscore subset. Now moving ahead, let's find the polarity percentage for negative and positive tweets. To do this, I have defined a function called pol underscore percent, and we have two parameters declared, subset and total. Let me run this. Okay. Now here I am calling the above defined function and printing the polarity percentage for Biden and Trump. And I have mentioned my two parameters, subset and the total number. So these are the values. Moving ahead, now let's create a bar graph that will show the negative and positive polarity percentage for Donald Trump and Joe Biden. Let me hit Shift Enter. You can see we have a really good bar graph now. If I hover the mouse cursor, you can see Donald Trump had 27.825% of positive tweets and 22.17 negative. Similarly, Joe Biden had 31.6 positive tweets and 18.4 negative tweets. Now we want to find the public sentiment based on Trump and Biden tweets. Let me run this two cells first. Okay. Now for Donald Trump, the total positive polarity is a combination of Trump's total positive percentage and Biden's negative percentage. Similarly, for Joe Biden, the total positive polarity is a combination of Biden's total positive percentage and Trump's negative percentage. Let me run this. You can see the result here. Next, let's plot a horizontal bar graph to visualize the public sentiment. We have our X and Y labels defined. We also have set our bar colors with the help of RGB values, and we have the title as well. Now if I go up, you can see this is the public sentiment. So 26.88 is the percentage that is in favor of Joe Biden, and for Donald Trump you have 23.11. Now coming down, now in the next cell of code we have a user defined function that will basically plot a table which has the most positive tweets for Donald Trump and Joe Biden. The condition we are checking is that the polarity should be equal to 1. So if it's close to 1 or equal to 1, which means the tweet has positive polarity. Let me run it. Okay. Now let me go ahead and call the function now. Let me scroll over to the top. You can see these are the top 5 positive tweets for Donald Trump, and here you can see the top 5 positive tweets for Joe Biden. Likewise, let's check the polarity for most negative tweets. Here the condition will be the polarity should be equal to -1, which means it's highly negative. Let me run it. Okay. Now let's go ahead and call the function negative tweets. So I'll write neg underscore tweets, and then inside bracket I'll give my parameters, which is Trump underscore subset, and then I'll give my title as negative tweets for Donald Trump. Okay, now I'll just copy this. We'll also check for Joe Biden, so I'll just replace this with Biden, and let's say negative tweet for Joe Biden. Let's run it. Okay, if I go on top, here you can see the top negative tweets for Donald Trump, and similarly we have the top 5 negative tweets for Joe Biden. Alright, finally let's see how to create a word cloud. Now, word cloud is a method to show which words are most frequently occurring among the given text. I have defined a function called word cloud, you can see here, and it has two parameters, data and title. Inside the built-in function or the word cloud function, we have mentioned the max font size, the maximum words, scale value, there's also background color which is white. Okay, let's run it. Now this will create a word cloud. So let me go ahead and call the word cloud function and pass in the arguments. So I'll write word cloud, which is my user defined function, and I'll give my parameters Trump underscore subset, comma, I'll give my title as word cloud for Donald Trump. Let's say Donald Trump tweet replies. Okay. Similarly, let's do it for Joe Biden. I'll write word cloud Biden underscore subset, and then I'll give the title as word cloud for Joe Biden tweet replies. Okay, let me run it. There you go. You can see we have a nice word cloud. So on the top you can see the title which says word cloud for Donald Trump tweet replies. So here you can see some of the words like real Donald Trump, then there's president, love, right, all these. Similarly, if I scroll down, you can see the word cloud for Joe Biden tweet replies. You can see this is the handle Joe Biden, false. There are some other words like due, taxes, believe, even, will, it's fact. And you can see Kamala Harris name here. Okay, now that brings us to the end of this demo on Twitter sentiment analysis using text data. You learned how to classify tweets and find the polarity. We also looked at how to create interesting visualizations with this data and understood the mood of the public. Finally, you saw how to create a word cloud that had the most frequently occurring words in the tweets.
Who is a data science engineer? Are you a data science engineer, or are you going to be looking for a different field? What exactly is a data science engineer? Well, a data science engineer is someone who has programming experience in Python and R, expert level knowledge, ability to write proficient codes. And we have Python and R. I'm going to say Python or R. Once you become really proficient at one language, transferring those skills into another one is usually fairly easy. Now, R is a little different because it is an analytics platform. So going from Python to R, if you already know the data analytics in Python, moving to R is pretty easy. Now R doesn't have all the other code that you can access with Python. There's so many things you can do with Python that are not data analytics. So that's important to keep in mind, that you should probably be pretty well rounded in Python and really have a solid foundation in R, or have a solid foundation in R and be well rounded in another programming language where you really get the programming side of it. Strong SQL and big data experience. So you have to have a strong coding skill with hands-on big data experience. And of course we're showing SQL here, most commonly used, whether you're using a Microsoft SQL server or MySQL server. You can also start thinking Hadoop and Spark and big data access. Hadoop file system is not a huge jump. If you've already learned your SQL and you've already learned your basics in coding, Hadoop sits on top of all that and does a wonderful job creating huge clusters of data. But you really need to know your SQL, because that is so common in most of the large companies now accessing their data. And an ability to visualize models and troubleshoot code of the models. This is a kind of an interesting one because these models can get very complicated, so you got to be able to break them down into something that you can put the pieces together and digest each of the pieces. So being able to visualize these models is very important, and then being able to drill down and troubleshoot the different models or the pieces in those models. You need to be a versatile problem solver, equipped with strong analytical and quantitative skills. A self-starter with a strong sense of personal responsibility and technical orientation. This is an interesting one, because when you talk about data science engineer, it's such a new field that most companies don't have it well defined. They don't know what they're looking for. You might not even know what you're looking for. You might have an idea and you're looking for patterns, but where do those patterns lead you? So you really need that self-starter side to jump in there and figure out where to go and be able to communicate that back to the team. And there we go. We have a strong product intuition, data analysis skills, and business presentation skills. And this is what I was talking about, is you got to bring that back to the team. So if you don't have a strong product intuition, if you don't know what's going on with the company, what they need, and where you're going with your analysis, it's going to be a dead end. And you got to be able to present that to the shareholders, to your coworkers, which leads us to great teammate with excellent interpersonal skills. And this is kind of a strange one because you spend so much time behind your desk, so you have to be able to kind of float between you're studying all the data and being able to explain this to people in simple terms that they can understand. No one wants somebody to come up and say, yeah, the P score and the F score is this, that, and the other thing, and you might have two people in the room understand you. You have to be able to sit down and explain what that means and why. So let's take a look at the data science skill set. When we talk about data science engineer skill set, we're talking about database knowledge, statistics, programming tools, data wrangling, probably the least favorite and most used, machine learning, data visualization, and then to touch on big data. And so we'll start with database knowledge. The most common databases, of course, your SQL, structured query language. Think rows and columns. It's an essential language for extracting a large amount of data from data sets. So knowledge of the SQL is mandatory for data science engineers. And you can see there's tools required. There's the Oracle database. I mentioned MySQL Server, Microsoft SQL Server, Teradata. There are so many different forms of SQL. And it'll just keep coming back and coming back. So if you don't have a solid basic understanding of SQL, go get it. Very important because it will come up. If you don't know it, it's going to bite you. And statistics, of course, that's what this is all about, is figuring out and predicting things. So you need to know your statistics. Statistics is a subset of mathematics that deals with collecting, analyzing, and interpreting data. Therefore, data scientist needs to know statistics. So you need to understand your probabilities and what that means, and what the p-score means, and the f-score, and means, and mode, and median, all that information, standard deviation, all of those you need to be aware of. And then we get into the programming tools, and I mentioned this earlier a little bit, but you need to master any one of these specific programming languages. Programming tools such as R, Python, SAS are essential to perform analytics in data. And again, you can move in there and you can be an expert in just R. You can be an expert in just SAS and a little bit. You can be an expert in Python, because most of these, when we're talking about data science and data wrangling, you really kind of get down to the point where you really need to have a full programming language, at least the basics. And if you're going to be working in data science, Python right now is the main one. But there's also Java, C++. So you need to know a solid language, at least the basics of it, so you can understand how to do basic iterations and things like that. I always found that interesting that my sister, who runs a university data analytics center, that's the first question she asks her candidates who come and work for her is, how do you iterate through data? You'd be amazed at how many people don't understand that very basic concept in programming. So when we look at R is a free software environment for statistical computing and graphs, supports most machine learning algorithms for data analytics like regression, association, clustering, and etc. Python is an open source general purpose programming language, and there's our general purpose I was just talking about you need to know a little bit about. Python libraries like NumPy and SciPy are used in data science. NumPy and SciPy are very central to Python, and I'd throw pandas in there also, that module. Those are very central to working with Python and data analytics. And then SAS. SAS can mine, alter, manage, and retrieve data from a variety of sources. It can perform statistical analysis on the data. So where R is the open source platform, SAS is more like the paid for platform. And so it has some things more automated because people are paying for it, developing it, but it's also, if you really start using it as a company, you're going to have to pay for it, where R is free software. Python's also open source and free to use. So we're going to talk a little bit about data wrangling, and I mentioned earlier that is both the probably people's least favorite aspects of data science, and also probably one of the places you spend the most time. So when we talk about data wrangling, it is the process of transforming raw data into an appropriate format to make it useful for analytics. And it involves cleaning raw data, structuring raw data, and enriching raw data. And this gets interesting because you'll get stuck on something like, in Python, you might get stuck on something that is a date time based on an integer 64 NumPy set. You might not know what all those terms mean because you work in R or something like that. But you get the point that it's all one particular format, and then you have to figure out how to switch it so that the computer can see it correctly in whatever format you're using or whatever analytics platform you're using. Knowledge of machine learning techniques such as supervised machine learning, decision trees, linear regression, KNN, etc. is useful for few job roles. So this is kind of interesting because sometimes that's the center of the job role of a data scientist, and sometimes you just have to be able to apply the programming skills to it so you can get the answer and let somebody else fine-tune your machine learning techniques. So it really depends on what it is you're working with. And you can see here we have our nearest neighbor set up where it groups things together that look alike. Linear regression, you're drawing a line through the data, or a curve, so you can predict what the next value is going to be. And then our nice decision tree, which starts splitting things up and says, it's sunny out, yes, let's go swimming. No, it's raining, we're not going to go swimming. Yes, it's sunny out, we might go swim. It's raining, we'll stay indoors, yes. We'll walk the dog, no. So you have a decision tree that helps figure out how you get to the end result. So decision trees can be pretty powerful. And data visualization. Data visualization is the study and creation of visual representation of data. Data visualization uses algorithms, statistical graphs, plots, information, graphics, and other tools to communicate information clearly and effectively. This one you really have to master as a data science. This one you really have to master as a data scientist. And there certainly are so many different tools to use to visualize it. But when you're communicating, a picture is worth 1,000 words. When you can put a picture up and people can look at it and go, oh, I see what's going on, that's worth a lot more than saying, yeah, this is good. People hear that and they just kind of go, okay, it's good, but why? And you might say, okay, these numbers make it look good. No, people want something they can see. And there certainly is, Tableau is probably one of the most popular ones out there. View, Power BI, Google Data Studio. In Python, there's the PyKit and Seaborn. There's all kinds of different options for visualization. You need to master probably at least one or two of them so you understand how they work and how they're different. And then big data. Big data is a massive amount of data which cannot be stored and processed using traditional methods. Big data has various benefits like access to social data can enable organizations to tune their business strategies. Big data can improve customer experience. And so we're usually, when you say big data, we're almost always talking about Hadoop and Apache Spark. It used to be Hadoop is your file system, so that's how you store all your data going across the nodes, and there certainly are other ways to store it. When we talk about Hadoop, we're usually talking about at least 10 terabytes of data when you're dealing with a Hadoop file structure. And then you can use Spark, where Hadoop processes on and off the hard drive. So it's continually reading and writing to the hard drive. Spark is running in your RAM. And so when you're doing a very intensive data process, you'll run a Spark setup, which will spread those processes over multiple computers. And of course, now the two combine, and Spark sits on top of Hadoop, and you get your big data. There's also Talent. Tableau has its own server set up. There's Splunk. Cassandra, you'll hear the Cassandra database. Pintaho, I'm not even sure how to pronounce that one. It's not one I've worked with. Certainly there's a lot of options for big data. The two big players are, of course, Hadoop and Spark. And even your SQL servers and MySQL servers will spread across 5 different servers. And you can be talking about big data across 5 servers with those, pulling them into, say, Apache Spark to do your high-end processing. And then there's non-technical skills. Probably the most important one in data science and any of our data analytics is intellectual curiosity. Updating knowledge by reading contents and relevant books on trends in data science. There's so much going on in this field, and it's exploding now that it's hard to keep track of it all. So you really need to have that curiosity in the data science, probably even more so than a lot of other fields. But I would say in just today's world, you need intellectual curiosity because things are changing so rapidly in today's world, the way that's going with our technology. Understanding how the problem solved can impact the business acumen. This is the one where a lot of people kind of skip over. You have to have a little business sense. If you don't know how it's going to impact the business, you're going to be in trouble. Why do they want to even pay you to be there unless they know what's going on and they're getting something in return? So this is your bottom line for your paycheck, is what's going on with the business. How is this going to impact the business? What are you doing for them? And communication skills. Companies look for someone who can clearly and fluently translate technical findings to a non-technical team. And I've talked about this a bunch, and I can't even iterate this enough. If you are struggling with your communication skills, work on building them. They don't have to be, this isn't rocket science where you have to know all these complicated terms. What you need to do is take the complicated terms you know from data science and reduce that down to something that anybody can understand. So when you come up and you have, KNN, no one knows what KNN is, unless they're in data science. Nearest neighbor, looking for things that match together. You got to explain that to people who do not have the technical skill in the data science arena. And a data science engineer needs to work with everyone in the organization, including customers. So it's teamwork, and that's always one that throws people for a loop. But ultimately, you are analyzing your customer's information. And so sometimes getting in there and rolling up your sleeves, if let's say you're doing data analysis for a sales team and you're backing a sales team, you might have to get in there and go start making some sales and making some phone calls and see what it's like. What is that team doing when they call 15 people in cold calls? And then they do a follow-up 2 weeks later or 3 weeks later. Which one works better, 2 or 3? Does it work better to call and send a fax, call and send an email? When should you show up in person if it's that kind of business? So working with everybody, including the customer, is very important with the data with this kind of setup and non-technical skills for a data scientist. So let's take a look at some of the roles a data science plays in the job market. Let's drill in there just a little bit here. So when you have a data scientist, they're going to perform predictive analysis and identify trend and patterns that can help in better decision making. Companies hiring data scientists include Apple, Adobe, Google, Microsoft. I would say that's even expanding down to smaller companies, where you're talking about only 100 employees or something like that. They're starting to look at data scientists because they need them to come in and be a part of that team. And the role is understanding challenges of a system and offer best solutions. This should always be the goal of a data scientist, is to be looking at the whole system and then trying to find those patterns that are going to best enhance the company or the business or the whatever group. Maybe you're working with the sales team or the marketing team. And you can see languages. Pretty important to have these are a number of different languages, and again, it depends on your own specialty. There's all kinds of different variations, but we have R, SAS, Python, MATLAB, SQL, Hive, Pig, Spark. You should have at least a knowledge of all of these. Maybe a Python programmer never used R. Download it and go through the basics so at least you know what's going on in R versus Python. because R is pretty powerful for doing a very quick display. And then of course there's a lot of things you can do in Python. You have to be able to do queries on database from time to time, create and modify algorithms which can be used to reduce information from large databases. And usually this is one of those things you do at the beginning, you set it up, and then you kind of let it go until it breaks, and then you have to go back and fix it because your query isn't working. That certainly is a very common thing to have happen, especially if you're pulling data off the web and the internet. And then we have some more companies that are hiring data analysis like IBM, DHL, HP. And so we're talking about data analysis. The role is responsible for a variety of tasks such as visualization, optimization, and processing large amount of data. And so when we talk about a data analyst, we're still talking a lot of the same stuff, but you'll see we now thrown in JavaScript and HTML in here, because that's pretty common with a data analyst versus a data scientist. And you can see that SQL is still pretty solid, and also C++ is pretty big. So some companies also use Java, so I'd put Java in the languages also on that for a data analyst. And then you have a data architect, ensuring that data engineers have best tools and systems to work with. And so companies hiring a data architect are like Visa, Logitech, Coca-Cola. They create blueprints for data management with the best security measures. I cannot highlight that a data architect really spends a lot of time with security measures. That's big. How many hacks have we seen in the last year on large companies that have lost data from millions of their customers and how badly that affects them? And we're looking at languages. You see that SQL is pretty solid across all of these. Under a data architect, XML. That's one that a lot of the data science jobs you don't see as much, but you're going to see more XML with a data architect because there's a lot of XML files that have your security measures embedded in them. And of course your Hive, Pig, those are Hadoop systems for doing some basic queries. So instead of doing the high-end queries, you now have these simplified query systems built into Hadoop, and Spark. So if you're using big data, you're going to want to know your Spark also. And then we have our data engineer. The data engineer updates the existing systems with better version of the current technologies to improve the efficiency of the databases. Think admin here. A lot of work tracking down what version you're in of the different programs. What version of Python are you using? What version of R are you using? What version of C++? So companies hiring data engineers are like Amazon, Spotify, Facebook. And they develop, construct, test, and maintain architectures such as databases and long-scale processing systems. And here we have our languages, our SQL, R, MATLAB, SAS, SPSS, Python, Java, Ruby, C++, Perl, Hive, Pig. You pretty much as a data engineer at this level, when you're talking about admin and updating all these databases, need to know all the different stuff that's being used in the company. And you're testing out these structures to make sure they work. And so you really are talking admin level kind of setup. So if you like spinning up an admin onto a Google Cloud service or Amazon Cloud service, now you start to get an idea what we're talking about, because then you can test it out up there and then you can bring it back and update it to the company. Statistician creates new methodologies for engineers to apply. And so when we look at this is where we're digging into the math of which models to use, what setup's going to work, what kind of activation do we have on our neural network. These little tweaks are going to make a big difference. And we look for methodologies at a large level. What kind of data are we going to be looking at and how are we going to pull it together? Companies hiring a data engineer, or we're talking about statisticians, we're talking about LinkedIn, PepsiCo, Johnson & Johnson, and of course these companies probably hire a little bit of everything, but they have a lot of statisticians working for them. And so we look at the role, extract and offer valuable reports from the data clusters through statistical theories and data organization. And the languages across the board, we're still seeing SQL, R, MATLAB, SAS, SPSS, Data. That's a new one that we haven't seen in some of the other roles. Python, Perl, an older version. And that shouldn't be a surprise because a lot of these companies probably built a lot of the original packages on Perl. If you go look at Johnson & Johnson. And of course your big data, Hive, Pig, and Spark. And then our database administrator. I mentioned the other one is an admin. They're more an admin level for the software itself. So administrator is another level. Some of the tasks involved are monitoring, operating, and maintaining databases, installation, configuration, defining schemas, training users, etc. And this is interesting, training users, because when you build a database and you define all the different tables that are embedded in that database and how they're all connected, the end user's got to have that information, otherwise you're in trouble. And we have companies hiring data engineers, of course Tableau, Twitter, Reddit, The role ensures that all the databases are available to all relevant users. Again, a little security in there. What role do they have? Who is allowed in and not? And is performing correctly and is being kept safe. And you better be ready to spend some time in security, because again, that's a very big thing nowadays with the number of people who hack into these databases. And the languages are going to be covered. You have your C#, your Java, SQL, Ruby on Rails, XML. Again, there's that XML because a lot of your security is embedded in XML files. Python, all the main players, depending on what the company's using. Data and Analytics Manager. So when you see manager, that means that somebody's going to sit on top and organize the people underneath. So they're going to improve the business process as an intermediary between business and IT. Oh, you better have some really good communication skills for this one. Some of the companies hiring data engineers are Coursera, Motorola, Slack, and of course these companies are hiring data scientists in almost all of these fields. So the role oversees the data science operations and assigns the duties to the team according to skills and expertise. So that's a big one. You better be able to communicate what's going on, help your team members come out and be able to communicate with other people. So sometimes your job is just being able to get people to talk to each other. The big thing on that is the whole communication line going from one end to the other, because you can't communicate all the information that everybody's working on. You have to pretty much come in there and help people communicate what there's going on, and also know what they're up to without being micromanagement, because that will crash a company if you micromanage everybody. But if you just let them do whatever they want and they never talk to each other, that will also destroy the company. You got to find that nice middle ground. And you really have to have an overview of everything as a data and analytics manager. One of the things, it's good to have at least one or two solid bases of programming under your belt for a data analytics manager, but you do need to have a very general understanding of all the different tools being used so that you know what's going on with your different team members. Of course, SQL, R, SAS, Java, Python, MATLAB, all of those are big. Business analytics. So this is when you're talking about your BI or your business intelligence and your business analytics. Very important to know this is kind of a subdivision of a lot of the other stuff we've talked about, a lot of the other roles we've looked at. So you possess specialized knowledge of their business domain and apply that knowledge and analysis specifically to the operation of the business. So you might be a specialist in banking. You might be a genetics engineer, so you know about genetics. You might just be general business, helping the marketing. So a lot of companies hiring data engineer are Oracle, Uber, Dell, and the role acts as a link between the data engineers and the management executives. So it's very similar to when we go back up here and we look at data analytics manager. A business analytics is going to also kind of fill that role in between, but they're more specialized in business. And you better know SQL, because when we're talking about business specifically, most of the large companies are storing their data that's up and running right now that people are accessing to purchase something on the Home Depot website or the Uber. They're logging in. You better know your SQL. It's very central to business analytics. So let's go ahead and take a look at the data science engineer salary trends. And you'll see that our source is Glassdoor. That's where we're pulling a lot of our data from. Average base pay is around $117,000 in the U.S., the average salary. And when we look at India, we're talking about $950,000 a year. And those are based on, some of them you need to go ahead and dig deeper to find out what education level versus entry level. But those are a pretty solid base once you're in the industry and once you created your career in there. When we look at the job titles, the most common job title is data scientist. Business Intelligence Manager is the second greatest one. That's kind of good to note. That's why they put that up there as being its own little subcategory of data science managers, a business intelligence manager, because it's such a high level of jobs. And then we looked at some of the other ones: data architect, business intelligence architect. Again, your BI, your business intelligence, gets its own ranking because it's such a high level, it's a business. People want their businesses to make money, so that's who's hiring. Of course, data engineer, business intelligence developer, business intelligence consultant, business intelligence analyst, business analyst, and data analyst. So you can look at the data analyst as being the general one that doesn't go specific to business. So if you're looking just for your career as far as getting a job, probably should have some kind of business understanding in the background. And again, your companies want to make money, so they're going to hire someone who knows business, if banking business, if you specialize in banking, or retail, if you specialize in retail and marketing. And you can see here on the data science salary trends and the growth in data science job listings, it's continually going up. It's since 2014 to 2012, we've gone from 400 to 600. That's a pretty big increase. So, huge growth in this market. It's one of the biggest growing markets right now for jobs and careers. So let's go ahead and take a look at building a resume. Always exciting, putting ourselves out, selling ourselves. And if you looked at some of our other videos dealing with resumes, you'll see a trend here. The top part is so different than what resumes were in the 90s, in the 2000 to 2010. They've evolved. They've really evolved. It used to be 2000, 2010, maybe LinkedIn, maybe one other reference. Now you're going to see that we want those references. This is a sales tactic, which now has come into resumes. It used to be that if you were a real estate agent, every real estate agent I knew, I used to deal with real estate software for the real estate industry back in the 90s. Every real estate agent wanted their picture on their business card. They wanted their picture, if they could, put on their contracts. They wanted people to see the face. So that's really a big change, is to make sure that it stands out. You stand out. Here's a picture of somebody, so you're more than just a couple letters and a name. And of course, you need your contact information, should always be at the top. You have your summary. What are you focusing on? Be a little careful with your summary, because if you have everything in your summary and then they scroll down to experience and education and skills, they're going to stop. The second you repeat yourself in your resume, that usually means to the reader, hey, this person doesn't have anything more to offer me, I'm done. So be a little careful how you word your summary. Most companies appreciate when you come in here and you've adjusted this summary to be both about you and how you're going to serve that company. So it's worth researching that company to find out how those connect and put that in the summary. Take some time to do that. That's actually a pretty big deal. And the references are huge also, especially in data science. When you're talking about any of the programming or data science, data analytics, having a place to go where they can look it up and scroll down and see different things you're doing, whether it's LinkedIn in this case, which is the business profile most commonly used, GitHub where you have stuff published, Facebook. I'm always hesitant because that tends to push more towards social media type jobs and other jobs. But certainly there's people who have Facebook who do marketing and stuff like that. But these links, having these basic links here is important. People are starting to look for that for some other setup. Maybe you have a personal website. This is a good place to put that so that they now have a multitude of links that go back to you and highlight who you are. And then the next part, or next 4 parts, so for the next 4 parts, we have a combination of experience, education, skills, certifications. And you can see they're organized. If you have, a lot of people like to see what kind of degree you have. They want to know where it came from. And if you just got out of college, you're going to put education at the top. And then maybe you'll put skills after that, and then your experience at the bottom. If you've been in the field for years, my degree, just to give you my age, goes back to the early 90s. So I usually put education at the very bottom. And then because a lot of the stuff I'm trying to sell myself on right now is my skills, I actually put that at the top. And I'll put my education, my certifications at the bottom, my skills, and then my experience is, since it's a huge part of my resume, goes next. You can organize these in whatever order you want that's going to work best for you and sell you. So remember, you're selling yourself. This is your image. Probably don't wear an old tie-dye t-shirt with holes in it. Something nice because it is professional. And of course your summary. And then what do you have to offer the company? And again, when I put out resumes, and I haven't done a resume in a while, you go in there and you can take this and reorganize this. So if the company's looking for something specific, you might put the experiences specific to that company. You might even take experience, if you have like a long job history like I do, I've gone into a lot of different things, You might leave out those companies or those experiences that had nothing to do with data science because it just becomes overwhelming. Resume should only take about 30 seconds to glance over, maybe a minute tops, because after that point you've lost the person's interest. And if they want to dig deeper, they now have links, they have your website, they have LinkedIn, and they can now take this and they come back to it and they go, oh, okay, let's look at this person a little closer. So quick overview, this is your sales sheet selling you to the company. So always tie it to the company so that you have that, what am I going to give this company? What are they going to get from me? We've covered a lot on data science engineer in general, and we've gone over a basic resume. Remember, keep it simple, short, and direct. That is so important with that resume.
Today's topic of discussion is how to become a data scientist in 2021. So, here are the topics we'll be discussing today. A brief introduction to data science, laying the groundwork for a data science career, a short note on who is a data scientist. Later, we'll discuss the in-demand technical skills for data scientists, and then the salary of data scientists, after which we'll discuss the future of data science and data scientists. So now, let's have a brief introduction to the field of data science. There is no specific definition to describe data science. If you ask 500 people to describe what data science is, you'll probably end up getting 500 different responses because data science is a continually evolving field. Well, under Wikipedia, data science is an interdisciplinary discipline using computational methods, processes, algorithms, and systems to derive information and insights from both structural and unstructured data. In simple terms, data science is the domain of study that deals with vast volumes of data using modern tools and techniques. These tools and techniques are used to find the unseen patterns, derive meaningful information, and make business decisions. The data used for analysis can be from multiple sources and present in various formats. There is a saying, a jack of all trades and a master of none. When it comes to being a data scientist, you need to be a bit like this. But perhaps a better saying would be a jack of all trades and a master of some. Let's now discuss about laying the groundwork for a data science career. Let's now look at some of the prerequisites for getting a data science job. Have a relevant degree. A solid educational background is required to be a data scientist. Pursue an undergraduate degree in data science or any closely related fields like statistics, computer science, or mathematics. After the undergraduate course, a master's degree in one of the relevant areas is an added advantage. Creativity and critical thinking. Creativity in data science is very much needed in this field. You will need it for creating a storyline, for innovative modeling, for developing new tools, different ways to collect your data, and lots more. Parallelly, critical thinking is very useful in data science. A data scientist should be able to develop questions and at the same time question the data as well. Required technical and non-technical skills. We'll be discussing in depth the required technical skills later on in this video. Talking about the other necessary skills in this field, you will need problem-solving skills, risk analysis, and many more. Good communication skills. Having a strong command over your communication skills is very much needed in this field. The outcomes that are delivered through data science are quite complicated and hard to explain. You will have to translate your technical findings clearly and fluently to the other teams. You will need good presentation skills, storytelling skills, writing skills, and listening skills. In short, make sure you focus on building lasting relationships through your communication. Here are some of the roles in the field of data science. Data scientist, machine learning engineer, machine learning scientist, data engineer, data analyst, statistician, business intelligence developer, infrastructure architect, enterprise architect, applications architect. Data scientist is most likely one of the most sizzling job titles among the lot. And now, let's talk about who is a data scientist. In simple terms, a data scientist is the one who practices the art of data science. A data scientist analyzes business data to extract meaningful insights. In other words, a data scientist solves business problems through various methods. DJ Patil and Jeff Hammerbacher coined the term data scientist. A data scientist's work typically revolves around data, and his role will be a combination of three main subjects: computer science, statistics, and mathematics. It's time to discuss the in-demand technical skills for data scientists. To become a data scientist, you need various skills as mentioned earlier. Some of the significant technical skills you will need to master include programming. There are several programming languages for data scientists. Learning and mastering at least one of them is essential to realize various functions of data science. But at the same time, just a single language can't solve problems in all areas. Python is the most widely used programming language in the world today when it comes to data science. The next widely used language is R. There are still some data scientists who use R instead of Python. But if you're doing applied data science these days, then you've got to learn Python because that's the most valuable programming language for data scientists. Some other languages include JavaScript, Scala, SQL, etc. Talking about Python programming language, it is open source and easy to use language. You will need to understand the basic syntax of this language initially. You will need to know how to write functions, loops, and modules. You should be familiar with both object-oriented and functional programming in Python. It is a general purpose and dynamic programming language that supports multiple paradigms. One of the factors that make Python stand out from the rest is its flexibility. You can use Python for almost all the steps involved in data science. The next skill we'll be talking about is machine learning. The concept of machine learning has been around for a while now. However, the ability to automatically and quickly apply mathematical calculations to big data is now gaining a bit of momentum. You will need to learn techniques such as supervised machine learning, decision trees, logistic regression, and natural language processing. One of the crucial reasons why you need machine learning in data science is because of the high value predictions that can guide better decisions and smart actions in real time without human intervention. There are in fact a lot of advantages of machine learning in data science. It helps analyze large chunks of data, and it changes the way data extraction and interpretation works. To sum it up, machine learning and data science can work hand in hand. With machine learning being such a craze, data scientists need to learn it. This is why Simplilearn has introduced a revolutionary machine learning certification program that provides advanced level training on the applications and algorithms it uses. We have provided the link in the description box for the same. Do not forget to check that out. Here's to yet another essential skill in data science: math. Mathematics is the bedrock of any contemporary discipline in science. It's one of the major requirements for data science. Some of the major math topics you will need to know are calculus, linear algebra, probability, and statistics. Some other math topics that will help you solve data science problems are discrete math, graph theory, information theory, and many more. Up next we have analytical tools. They help you extract useful, meaningful insights from data and provide you with valuable frameworks for processing big data. Data analysis is a core practice of modern day businesses, and choosing the right analytical tools is very challenging as no tool fits every need. Anyway, some of the most used analytical tools in data science are SQL, Spark, Hadoop, Hive, and many more. Coming to data visualization. It is an interdisciplinary field that deals with the graphic representations of data. Data visualization plays two prominent roles: communicating results clearly to a general audience and organizing a view of data that suggests a new hypothesis of the next step in a project. Some of the data visualization tools are Matplotlib, ggplot, and d3.js. Data visualization encompasses techniques that are used to communicate data or information by encoding it as visual objects that are contained in graphics. Well, as big data keeps growing, data visualization becomes an increasingly crucial tool. Up next, we have data wrangling. This is the process of gathering, selecting, and transforming data to answer an analytical question. It will help the data scientists fasten decision making and hence get better insights in less time. Data wrangling is also known as data cleaning or munging. At last, we have business acumen. When you are a data scientist, you must have more business sense in analyzing the data. In other words, you need to know whether the insights gained from the data is of value to the business or not. Hence, business acumen plays a very vital role in structuring business data analytics. When we are talking about business knowledge, three things come into the picture: general business knowledge, industry-specific knowledge, and company-specific knowledge. Knowing these are very much important when you are a data scientist. So guys, this sums up the in-demand technical skills for data scientists. Well, let's now discuss the salary of data scientists. Before we go into the topic, we would like to introduce our new platform SkillUp, where you can find some of our best courses for free. We are offering more than 1000 hours of content for free, which can help you acquire more than 300 skills across a number of different categories. Take the next step to grow in your career by joining SkillUp by checking out the link in the description. When we are talking about the salary of data scientists, many factors come into the picture. The salary would depend on the experience he or she holds, the industry, the company size, educational background, and finally the region. According to Glassdoor, the average salary of a data scientist in India is close to 10 lakh rupees, and that in the United States is close to $1,13,309 in the IT field. The driving factor behind high data science salaries is that the companies and organizations are realizing the power of big data, and they want to use it to drive smart business decisions. Coming to our last topic of the day, future of data science and data scientists. With every passing year, data science is improving and expanding at a significantly faster pace. Data science has found its applications in almost every industry. Healthcare companies are using data science to build sophisticated medical instruments to detect and cure diseases. Video and computer games are now being created with data science, and that has taken the gaming experience to the next level. Similarly, data science has taken various other fields to a whole new level. The top 3 most common search terms in July 2020 are data science, machine learning, and artificial intelligence. According to the 2020 Emerging Jobs Report, LinkedIn listed data scientist as the top 3rd job with an annual growth rate of 37%. For 4 years in a row, data scientist has been named the #1 job in the US by Glassdoor. Pursuing a career in data science is a smart move, not just because it pays well and is trendy. It is because data is the pivot point on which the entire economy turns. However, you can also go through our video on the topic tips for becoming a data scientist for more information.
Thank you all for watching this video tutorial on Python for Data Science full course. I hope you liked it. If you have any questions, then please put them in the comment section below. Thanks for watching. Stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.